Hi everyone, I'm super excited to announce that my all-in-one AS level chemistry video is here. I have put so much effort into this, making sure that every single topic is taught in the clearest, most concise way, the way that you will be familiar with if you've been following me throughout your GCSEs and IGCSEs. I know that this content is difficult to understand, and unlike other subjects where there's an awful lot of learning off by heart involved, a lot of chemistry is understanding the concepts, and that's why I've spent so much time making sure that I'm teaching you in the most logical way possible. Throughout, you'll see snippets from my revision guide. This is something that I'm super proud of, and if you're interested in getting a copy, looking at previews, do check out the website swhlearning.co.uk where you'll find the online PDF. But yeah, it's time for us to just dive straight in, and I'm hoping that by watching this video you will feel so much more confident with your exam. So starting with the fundamentals, we're going to be looking at the structure of the atom. I'm sure you're aware that a proton and a neutron both have a mass of 1. Electrons are much smaller. They have a mass of 1 divided by 1840. In terms of their location within the atom, you'll find the neutrons and the protons located within the nucleus. Electrons are present in what we now call A-level orbitals. The charge on these various particles are as follows. Neutrons are neutral, so they have no charge. Protons are +1, electrons are -1. But how did we arrive at the structure of the atom? Well, now we need to take a brief look at its history. In 1803, Dalton suggests that elements were comprised of indivisible atoms. In 1896, Thomson came up with the plum pudding model. Now, plum pudding is similar to a cookie or Christmas pudding. He suggested that the plums were electrons embedded in a sponge made up of positive charge. Now, in 1911, Rutherford disproved Thomson's plum pudding model through use of the gold foil experiment. Here he fired alpha particles at gold foil and observed what happened. Now, he found that most of the alpha particles pass straight through the gold foil, and this told him that the atom is largely made up of empty space. So this goes against what Thomson said directly. After all, he said that there was an awful lot of matter found within an atom. Next up, he found that some alpha particles were deflected very strongly. This means that they must have come in contact with something which was positively charged, because an alpha particle comprising of 2 protons is positively charged, and he later discovered that that thing that was positive was the nucleus, which contained the protons. He found that very few of these alpha particles were deflected strongly, and this then told him that the nucleus must be very small. So it gave us this idea of the modern structure of the atom as being comprised of a very small positively charged nucleus surrounded by empty space, which we now know to be the various energy levels. In 1913, Bohr suggested that electrons orbit a positive nucleus in shells of fixed sizes. And in 1932, Chadwick discovers the presence of neutrons. And in present day, we know that the nucleus contains the protons and the neutrons, and that electrons exist in energy levels containing sublevels, which we now call S, P, D, and F. A brief recap: remember that atoms are neutral. This is because the atoms contain equal numbers of protons and electrons. The various vertical columns of the periodic table are known as groups. Here, elements have similar chemical properties, and that's because they have the same number of electrons in their outer shell. When you look at various symbols in the periodic table, remember these symbols represent elements. You'll usually find that the top number is the mass number. This is the total number of protons and neutrons. The bottom number is simply the atomic number. This is the number of protons. Elements are arranged in the periodic table in order of atomic number. So we'll start with our definition of an isotope. So it's atoms of the same element with the same atomic number, which remember is the number of protons, but different mass number. And what changes that mass number is the fact that the number of neutrons changes. So for example, chlorine has an isotope which has a mass number of 35, has a second isotope which has a mass number of 37. What's the difference between these two isotopes? Well, it's 2 neutrons, isn't it? Chlorine-37 has 2 extra neutrons, which makes sense if we consider that definition. So we'll dive in with this question. This is more of an IGCSE, GCSE type question, but it's good to get our eye in terms of what's going on with these types of questions. So a naturally occurring sample of the element chlorine contains 75% of the 35Cl isotope and 25% of the Cl37 isotope. Notice that in total, obviously your percentage should add up to 100%, which it does indeed do here. It says calculate the relative atomic mass of chlorine. So to find the relative atomic mass, you do the mass of the first isotope times its percentage, and then the mass of the second isotope that's mentioned times its percentage divided by 100. And that's obviously the case even if you have 3 or 4 isotopes. But here we only have 2 isotopes, so let's follow my instruction. Isotope 1 has a mass of 35. There's the percentage of it. Isotope 2 has a mass of 37 times its percentage. And then when you put that into your calculator, you get a value of 35.5, which makes total sense because that mass number sits somewhere in between the 2 mass numbers of the isotopes, so do check that your answer is sensible. Now let's make this more of an A-level style question. So here a sample of sulfur consisting of 3 isotopes has a relative atomic mass of 32.16. The following table gives the relative abundance of 2 of these isotopes. Use this information to determine the relative abundance and hence the mass number of the third isotope. So first of all, we need to work out the relative abundance of the third isotope. So that really means find its percentage. And as I've said, the relative abundances should add up to 100%. So first of all, calculate the total relative abundance here for the other 2 isotopes. That's simply 92.8%. So we do 100% minus 92.8 to get 7.2%. And then we use the equation from before in order to find out the mass number of the third isotope. So in this question, we know that the relative atomic mass is actually 32.16. The mass number of isotope 1 was 32. We're using the table times by its relative abundance. We're after the mass number of that third isotope, so there's our X value. We just calculated its relative abundance. So now it's just a matter of rearranging. So multiply both sides by 100. Do 32 times 91. Take 2,971.4 away from both sides. And then finally divide both sides by 7.2. And your final answer is actually 34. And the reason for that is because your answers should always be given to the lowest number of significant figures used in the question, which we can see is 2 significant figures. Let's look at a past paper question now. The relative atomic mass of a sample of rhenium is 186.3. Here's the information about 2 isotopes. Calculate the relative atomic mass of the other rhenium isotope. Show your working. So we know that in total the mass is 186.3. The first isotope has a mass of 185. There's its relative abundance. So the reason I picked this question is because it tells us that we have 2 isotopes, but look, the total relative abundance only adds up to 27 as opposed to the 100, which you're more used to. So just be aware, what they're saying here is they don't have all the isotopes present, they just have 2 isotopes of rhenium, so you want to actually divide these numbers by 27. So now we multiply both sides by 27. Take away 1,850 from both sides, and then finally divide by 17. So our final answer is 187.1. And then I chose this question because it is slightly more tricky due to this mention of a ratio. A sample of strontium contains 3 isotopes, 86, 87, 88 strontium. 82% of the sample is 88 strontium. The other isotopes are in a 1:2 ratio of 86 to 87 strontium, and that's probably the line of this question you might not like. Calculate the percentage abundance of 87 strontium in the sample and use your answer to deduce the relative atomic mass of the sample, giving your answer to 1 dp. So we have all of the isotopes present, which means we're going to have a total relative abundance of 100%. So now it's a matter of working out what percentage we have of each of these isotopes. So in total, we know we have 100%, which means that together these must account for 18%. Now, the ratio we've been told is 1 to 2. So how do we do that? Well, add up 1 to 2, so you get 3. Divide that 18 you just calculated to find that a ratio of just 1 part is 6%, and therefore that allows us to work out that 6% of it is 86 strontium, 12% is 87 strontium, and then altogether that adds up to 100%. And then it's exactly the same as what we were doing before. We're after the relative atomic mass, so that will be our X value. And then do check the wording of the question. They want it to 1 decimal place. Now, obviously the most difficult part of this topic is everything to do with those graphs. So I'm going to use lots of past paper questions to show you how to work your way through those methodically so you can guarantee yourself all the marks. But I'm just going to quickly chat you through how the mass spectrometer works and what the purpose of it is. And I'm using a page from my revision guide. I am so proud of this chemistry revision guide. It took me so long to work out the layout, exactly what I wanted to say, and I actually wanted to use it as my template for this A-level IB video. So the key thing here is to keep in mind the larger picture. What is the purpose of a mass spectrometer? It's to determine the relative atomic mass or relative molecular mass of a substance. Keep that in mind. Now, how is it actually carried out? Well, it's carried out in a vacuum. They could ask you why. To prevent ions colliding with molecules in the air. Remember, a vacuum contains no particles. It's very important that at the beginning of the mass spectrometer, our substance forms ions, and that's in part because of how a mass spectrometer actually works. And if we have a quick look at a diagram of a simplified mass spectrometer, remember, it's super important that our substance is ionized, and that's to allow it to be accelerated by the electric field and then to be detected at this end. And that detection, remember, causes that ion to form either an atom or a molecule again, and it produces a current, and it's the size of that current that will tell us how much of each isotope we have. So like I said, keep in mind the larger picture. Do be aware of this diagram. It's important that you're aware that this area here is where our sample is ionized, and I'm going to talk about the ways in which that sample may be ionized very shortly. Here's where that acceleration of the ion occurs. The ions drift through here, and then they are detected at this end of the mass spectrometer. So, to talk about the 2 different ways in which an ion may be formed, you have both electrospray ionization and electron impact ionization. So the electrospray works by dissolving our sample in a volatile polar solvent. The sample is forced through a hollow needle connected to a high voltage supply, and what this does is it causes the sample to gain a proton to form positive ions. So here's our proton, which remember is an H+ ion, because hydrogen, when it loses an electron, because it has so few subatomic particles, it becomes an H+ ion. Don't worry about that too much, but do be prepared to write this equation for any particular element they give you. With electrospray ionization, your sample in gaseous state is gaining a proton to form this species here. Electron impact ionization works differently. Here our sample is vaporized, so it becomes gaseous. An electron gun fires a beam of high energy electrons at the sample, causing an electron to be removed from each particle to form positive ions. So as you can see here, it's a slightly different equation. We've lost an electron in order to form that positive ion, and that tends to be the type of ionization they use in your past paper questions. So the second stage I've already mentioned is acceleration. This is when our positive ions are accelerated by the electric field towards a negatively charged plate. It's important that that plate has an opposite charge so that they can be attracted. All ions reach a constant kinetic energy, so lighter, more highly charged ions will reach higher speeds. Then ion drift occurs, and then finally the all-important detection. Those lighter ions reach high velocities, so arrive at the detector first. And those positive ions accept an electron to become the neutral atom, and it's this process here which is detected. So the larger the current produced, the more of a particular isotope which is present in a sample. So when you look at a graph, and we will look at those very shortly, where you see the highest peak, that will tell you that you have the most isotope present. So I'm going to zoom out to enable you to see the whole page. Remember these revision guides, which are just full of useful information, available on the SWH Learning website. But in all honesty, the best thing I can do now is to start taking you through some past paper questions, because you'll start to see how they're all similar and how you can actually score super highly, as long as you keep in mind that the whole purpose of the mass spectrometer is to find the relative atomic mass or the relative molecular mass. And so because of that, this equation here is going to be very important, which you'll be familiar with from GCSE and IGCSE chemistry. It's your abundance, so how much you have of each isotope, of isotope 1, times by its mass, plus the relative abundance of isotope 2, times by its mass. Obviously, it depends on how many isotopes you have present as to how far you go with this equation, divided by the total relative abundance. That could sometimes be 100, or it could be slightly different depending on the graph they give you. But again, don't worry, I promise this will all become clear when I take you through the past paper questions. Hang on in there, I promise it will clear itself up. The mass spectrum of a sample of tellurium is shown in the graph. Use the graph to calculate the relative atomic mass of this sample of tellurium. Give your answer to 1 decimal place. So this one is unusual because your relative abundance, so how much you have of each isotope, we don't have a scale, but they're all proportional to each other, which means you can, in effect, create your own scale. I'm going to call this 1, 2, 3, 4, 5, 6. And then to find the relative atomic mass, remember we do the relative abundance of the first isotope times by its mass. We assume, unless told otherwise, that each ion formed is a +1 ion, which means that we can use a mass that's exactly the same as the MZ ratio. So that becomes 1, 2, 4. Then we have our second isotope. And then we're going to divide that by the total relative abundance. So that's 2 plus 4 is 6, plus 7 is 13, plus 6 is 19. Pop that into your calculator and you will get a value to 1 decimal place. Do check the wording of the question, of 127.8, which makes sense because that relative atomic mass sits somewhere in between all of these MZ ratio numbers. Suggest what might cause the relative atomic mass of this sample to be different from the relative atomic mass given in the periodic table. Use your common sense here. If this number is different from the value in the periodic table, it must be because you have other isotopes present or different abundances of the isotopes. Write an equation for the reaction that occurs when a tellurium ion hits the detector. So we're starting with a tellurium ion. As I've said previously, we need to assume it's formed a +1 ion. So it's going to become a neutral atom through the addition of an electron to become a tellurium atom. State the MZ value of the ions that produce the biggest current at the detector when the spectrum in the graph is recorded. Give a reason for your answer. So the largest current will be produced by the isotope with the highest abundance. So just look at these various peaks. You can see straight away that it's going to be 128, and that's because it's the most abundant ion. The mass spectrum of tellurium has also a small peak at MZ64. Explain the existence of this peak. So that 64 is exactly half of 128. We've said that these must be due to +1 ions, so the only thing that can be responsible for an MZ value of 64 must be the formation of 2+ ions. But make sure you say which isotope is responsible. A TOF mass spectrometer can be used to determine the relative molecular mass of molecular substances. Explain why it's necessary to ionize molecules when measuring their mass in the spectrometer. The reason for that is fundamentally because the detector works by attracting ions. Remember, the size of the current indicates relative abundance, and the only way you can get those substances to be accelerated by the electric field is if they are ions, if they are charged particles as opposed to molecules. The following shows a simplified diagram of a mass spectrometer. State what happens to the sample in the parts labelled P and Q. So part P, this is where our sample is ionized. Part Q, this is where acceleration of those ions occurs by the electric field. In a mass spectrometer, the isotopes of an element are separated. 2 measurements for each isotope are recorded on the mass spectrum. State the 2 measurements that are recorded. So really that's asking, with that graph, what are the labels on the y and x axis? So on the y-axis, you'll have relative abundance. On the x-axis, you'll have that MZ ratio, the mass to charge ratio. A sample of element R contains the isotopes with the following mass numbers in a ratio of 1 to 1 to 2. Calculate the relative atomic mass, give your answer to 1 dp. So let's add those numbers up. We have 4. We're going to assume that our relative abundance adds up to 100. So we do 100 divided by 4 to get 25. So that means we have 25% of isotope 206, 25% of 207, 50% of 208. Same old equation. Divide by 100. So to 1 decimal place, the answer here is 207.3. Identify R, so use your periodic table. Look at the element with a mass number of 207, it's going to be lead. The mass spectrum of the isotopes of element X is shown in the diagram. Define the term relative atomic mass. So we'll quickly scribble down that definition. Worth learning these definitions off by heart. Average mass of one atom of an element divided by 1/12 of the mass of an atom of carbon-12. Use the data from the diagram to calculate the relative atomic mass of X. Give your answer to 1 dp. So same old. They've given us our relative abundance this time, so we're going to do 3 times 70, 4 times 72, 1 times 73, 5 times 74, and then divide it by the total of these peaks here, 3 plus 4 plus 1 plus 5. Identify the ion responsible for the peak at 72. So use your periodic table, have a look at which element is in question. It's germanium, and make sure that you use the 72 here to represent its mass number. Make sure it's an ion. Again, we assume it's a 1+ ion. Identify which one of the isotopes of X is deflected the most. Give a reason for your answer. So you're looking for the one with the lowest MZ value. So you're looking for the lightest one, so that must be the one with the lowest MZ value, the lowest mass. In a mass spectrometer, the relative abundance of each isotope is proportional to the current generated by that isotope at the detector. Explain how this current is generated. Remember, those summary equations here show that electrons are transferred to the positive ion. I now want to show you how to do time of flight calculations, TOF. Now, these always look super overwhelming, but they are absolutely fine if you follow a few key steps. Remember, they're worth between 5 and 6 marks, so it is worth making sure that you've got them sorted, and they do tend to come up in every single exam. So we'll start by looking at the question. A sample of rhenium is ionized by electron impact in a time of flight mass spectrometer. A 185 Re plus ion with kinetic energy this many joules travels through a 1.45 meters flight tube. The kinetic energy of the ion is given by the equation K equals half mv squared. Calculate the time in seconds for the ion to reach the detector, and we've been given Avogadro's constant. So as with all these questions, you do tend to need to use all the information they've provided. Now, just before you get going, do make sure you write down this formula triangle. If you studied IGCSE or GCSE physics, you'll be familiar, but you'll need it for A-level chemistry regardless. It tells us that time equals distance divided by speed. And that kind of makes sense because we know our final answer will be related to time, but we're in no way ready to get going with that formula yet. We're going to have to do some maths before we get to that point. Look, what's common to both equations is this V. So clearly we need to use this equation to find the V, which we'll then be able to substitute into this to find the all-important time. However, before we get going, the first thing you'll want to do, step 1 I'm calling it, is to find the mass of one ion of 185 Re plus. And we want to find that mass in kilograms. So how do we do that? I'm going to write it out nice and fully. You're going to use the mass number, so that's 185 they've provided you in the question, and you're going to divide it by Avogadro's constant, because what that does is it's taking the mass we've been given and telling us exactly the mass of one ion as opposed to 1 mole of the substance. So that's why you have to divide 185 by Avogadro's constant. And that gives us a very small number indeed. And make sure you get your units converted at this point. We need that in kg, so we divide it by a further 1000. So we're already scoring some marks here. Step 2, use Ke equals half mv squared to find that speed value. So the kinetic energy we were told was 1.153 times 10 to the minus 13. The mass we've just found times v squared. For me, you just want to simplify each side. So just do half of that number you just found. Then to get v squared by itself, you divide both sides by 1.5365 times 10 to the minus 25. So you'll find that to be v squared, and then finally you need to square root that answer to find v to get 8.66 times 10 to the 5. So close now. Right, we are finding time, so we do distance divided by speed. So the distance was 1.45 meters. Speed we've just found. Our final answer therefore for the time is 1.67 times 10 to the minus 6 seconds. So just to recap, make sure you have that physics formula triangle written down. Make sure you're aware that Avogadro's constant means the number of atoms or molecules in 1 mole of a substance. Step 1, you're going to find the mass of simply one ion of your substance, and you're going to do that by taking the mass and divide it by Avogadro's constant, being sure to convert it to kilograms. And that's because we have kilograms being used throughout the question, so we need to keep those units matched up. Step 2, we're going to use K equals half mv squared to find the speed. And then step 3, finally just plugging those numbers into time equals distance divided by speed, and you'll get your final answer here in seconds. Right, let's put this into practice now by looking at this past question. So a sample of strontium is analysed by TOF mass spectrometry. The sample is ionized using electron impact. The ions are accelerated to have a kinetic energy of this. An ion takes 9.47 times 10 to the minus 4 seconds to travel along a 95 centimetre flight tube. I'm just going to label that. That's time, that's distance. And I can see straight away, look, that's in centimetres. I'm going to just pop that into metres so that I don't forget to do it later. Use the information given to deduce the mass number of this ion, and here's Avogadro's constant. Right, so I'm just going to get started then. Here's that all-important triangle. We're kind of working backwards compared with the last question, but don't worry, because we're after the mass number. That was our starting point before, but it doesn't matter. We're actually just going to dive straight in. We know that we have both time and distance, so we're now going to find V, which then we can plug into this equation. That will enable us to find mass, and then we can unfold that mass using Avogadro's constant to find the final mass number of this ion. So the distance I've already changed to meters. So that's your number, meters per second. Then we're using Ke equals half mv squared. We know Ke, we've been told, is 7.02 times 10 to the minus 20 equals half times m, which is what we're after, times this number we just calculated. Make sure that number's squared. Then rearrange. So I'm going to just square that number, divide it by 2, and then to find m, you do 7.02 times 10 to the minus 20 divided by that number. And then last step, to find the mass, you get that number you just found. Make sure you pop in Avogadro's constant down here. And then obviously to find mass, we do 1.39 times 10 to the minus 25 multiplied by Avogadro's constant. So that gives us a number of 0.084 kg. Just be a little bit careful with units. You want your final answer in grams, so multiply that by 1,000 to get 84. So let's start by looking at the energy levels in further detail and working out how many electrons can go into each energy level. And as I've already told you, n equals 1 means the energy level or shell closest to the nucleus. N equals 2 will be slightly further out, n equals 3 will be further out again. In order to know how many electrons fit into each energy level, you're going to use the formula 2n squared, where n is the energy level in question. So 2n squared, when applied to the first energy level, so n equals 1, substitute that in, so n squared, 1 squared is obviously 1, times it by 2, so there are 2 electrons which can go into the first energy level. Let's take the second energy level, so n equals 2. 2 squared is 4, times 2 is 8. So the maximum that can be held in the second energy level is 8 electrons. For the third energy level, we're going to do 3 squared, which is 9, and then times that by 2, so 18 electrons can go into the third energy level. However, it's not as straightforward as that, and I'm sure lots of you have heard of the word sublevels, and that's where I'm going now with this video. When we're talking about sublevels, we must understand the word orbital. Now, an orbital is just a fancy way of describing an area in space where you stand a very high chance or high probability of finding an electron, and there are various different orbitals you need to know about. These are the s orbital, the p orbital, the d orbital, and the f orbital. So starting with the s orbital. The s orbital is spherical shaped, and that means you stand a 99% chance of finding an electron within this sphere shape. The s orbital can hold a maximum of 2 electrons. We're looking at the p orbital now. This is dumbbell shaped, and it exists within 3 planes, and you've got to try and imagine this like a mathematical graph. So you remember that there's the x-axis, the y-axis, and then lastly the z-axis is coming towards you or moving away from you. So it's 3 planes. and each of those planes can hold a maximum of 2 electrons. And so because there are 3 planes, it means that a p orbital can hold a maximum of 6 electrons. So going back to the s orbital, spherical shape can hold 2 electrons, p orbital can hold 6 electrons, the d orbital can hold a maximum of 10 electrons. Now we need to go into greater depth because we know we need to start drawing electronic configurations. So we're just going to take a step back and look at n equals 1 again, so the first energy level. I've told you that that can hold, based on 2n squared, it can hold a maximum of 2 electrons. I told you that an s orbital can hold a maximum of 2 electrons, which is why the first energy level only has the s sublevel. It's the only thing it can contain, which is why when you start filling it up, you start saying 1s2, because it's the first energy level, so 1. It contains an s sublevel, hence the s, and it contains 2 electrons, hence the 2. So 1s2, and that will actually correspond to the element helium. Now we're going to look at the second energy level, so n equals 2. Based on 2n squared, we know that it can hold a maximum of 8 electrons. How does that work in terms of sublevels? Well, the first sublevel, so the s sublevel, will take 2 of those electrons out of the equation, meaning there are 6 left. That's why we turn to the p orbital. I've already told you that the p orbital can hold a maximum of 6 electrons, which makes sense. 6 plus 2 is 8. So in the second energy level, you're reaching the s sublevel and the p sublevel. So energy level 3 contains a maximum of 18 electrons according to 2n squared, and we know this is divided up as an s orbital, which takes away 2 of those electrons, a p orbital that takes away 6 of them, and then the d orbital that contains a maximum of 10 electrons. So now I've given you the overview, we're now going to switch to the iPad so you can look how we're going to draw the orbital diagrams, electronic configurations, and then the condensed version involving noble gases. Right, I'm going to show you a foolproof way of working out how you write out electronic configurations, and this way always works and stops you having to learn endless lists of elements. So just start by listing the various energy levels. So n equals 1, obviously that's the energy level or shell closest to the nucleus. N equals 2, n equals 3, n equals 4, and n equals 5, and then I'm going to show you how to draw the diagram that will help you work out your configurations. So just start by writing 1s, because remember the first energy level only has an s sublevel, which is why we're putting the s, and it's in energy level 1, which is why it's 1s. And then just copy that down, making sure you use the appropriate number for the energy level in question. Looking at energy level 2, we now reach the p sublevel, so I'm going to write p is in energy level 2, which is why it's 2p. I can copy that down again. We're reaching energy level 3 now, that moves into the d sublevel, which is why we're writing 3d. And then in energy level 4 we reach the f sublevel, so 4f, 5f. Now I'm changing colour and I'm going to just show you what you need to do now. So you need to write arrows onto this. Be very specific how you draw these arrows. They need to be diagonal, going from right to left. And this is why it's essential that you've lined up everything perfectly. And this will show you the order that you fill. So I'll give you an example now, and we're going to use the element fluorine. Looking at fluorine now, so using the periodic table, I see that fluorine has an atomic number of 9, which means it contains 9 electrons. Have a look over here on the right hand side. I know that the s sublevel can contain a maximum of 2 electrons, p contains a maximum of 6, d contains a maximum of 10, and f is 14. So using my diagram now, I can see based on the arrows that the first thing I need to write is 1s2, because the s sublevel contains a maximum of 2 electrons. Following the arrows, we see the next arrow points at 2s, so 2s2. Add those 2's together, that's 4. Take them away from the 9 electrons, meaning that there are 5 electrons that still need to be placed, and I can see according to my diagram that needs to go into the 2p sublevel, and it's going to be a 5. I just want to show you how this can be drawn as an orbital diagram. So I've literally just used boxes to represent each orbital. So we've got 1s, 2s and 2p. I'm now going to show you how to draw various orbital diagrams. So do bear in mind, especially if you're studying IB, you need to be aware of certain principles, and this will be applicable with A-level. You're probably just not aware that they've got special names. So first of all, the Aufbau principle states that electrons fill the lowest energy orbital that is available first. We've actually already followed that principle by writing it out as 1s2, 2s2, 2p5. We know that it occupies the s orbital first of all, the s sublevel first of all. Then we need to follow a second principle, which is the Pauli exclusion principle, that states that any orbital can hold a maximum of 2 electrons. Yeah, that makes sense because look, there's the first electron, there's the second electron, so there's 1s2 complete, and look, is that box, that orbital is holding a maximum of 2 electrons, and so I'll just keep filling. So we know that the 2s sublevel is full. Then we know that Hund's rule of maximum multiplicity, this just states that electrons fill all the orbitals singularly before occupying them in pairs. So I'll show you what that means. We know from my electronic configuration that 2p has to have 5 electrons in it. So according to Hund's rule of maximum multiplicity, they occupy singly first. So there's the first 3 electrons in. Then we go to occupy them in pairs. So there's the 4th electron and there's the 5th electron. And so by writing it out in this way, I know that I've obeyed Hund's rule of maximum multiplicity. If this is sounding confusing, don't worry, I'm going to show you so many examples, you're going to be sick to death of it. You might want to know why I've drawn my electrons like this, kind of up and down arrows. That's just because the electrons have an opposite spin, and that's actually part of the Pauli exclusion principle. We're now going to use the example of potassium to carry on practicing. So using the periodic table, potassium has an atomic number of 19. This means its electron number is 19. So using the diagram above, we can see we start with 1s2, let's follow the arrows, 2s2, 2p6, 3s2, 3p6, and let's just count how many electrons we have, 4, 10, 18, so we just need one more, and we see that the arrow points from 3p to 4s, which is why it's 4s1. Now we're going to practice the orbital diagrams. So there's the 1s, here's 2s, this will be the 2p, remember it has 3 orbitals, this will be 3s, this will be 3p, and lastly 4s. So let's, according to all those ridiculous principal names, work out how we're going to fill this. So we know that the 1s sublevel is full, so there's the first electron, there's the second electron, same with 2s, there it goes. And then according to Hund's rule of maximum multiplicity, we have to occupy them singly first of all, and then we go and occupy them in pairs. It doesn't make any difference, I mean it's full, but it's good to get used to how you're actually filling them. Moving into the 3s sublevel, 3p sublevel, and lastly 4s. It's just a single electron. And I might label them because that would make sense. We do need to know some exceptions to this rule, and actually there's only 2 you need to know about: chromium and copper. Let's look at chromium first of all. So using the periodic table, we see it has an atomic number of 24, which means its electron number is also 24. According to this diagram, we would therefore write the electronic configuration like this. And it's nice and quick using this approach. Right, let's see where we've got up to. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20. Okay, so we're trying to reach 24, which is why we would imagine it would be 3d4. However, I'm now going to write out what it actually is. Let's look closely at why this occurs, and it's actually helpful to look at the orbital diagram for D. So remember that can contain a maximum of 10 electrons. So we would see that as 5 boxes. Now if we start filling it, according to Hund's rule, the electrons fill singularly. And if you have a look at this, according to the way we would imagine you would fill, which is 3d4, that's where it would stop. But for some reason, relating to energy, which I'm not going to go into here, the D sublevel would much prefer to have electrons in every single orbital as opposed to leaving that final orbital blank, which is why we then put a 5th electron here at the detriment of 4s containing a full number of electrons. Let's now look at copper. So copper's atomic number is 29, so it has 29 electrons. So we're going to do exactly the same and work out what we would imagine the electronic configuration to be, and then look at what it actually is. Let's see where we're up to. So 10, so we're up to 20. So we've reached 4s, so I'm following the next arrow, so it goes 3d, and that will be 9. So I've drawn out the actual electronic configuration, and we can see again, we've got this time that the 4s sublevel isn't complete, it only has 1 electron in it, and the 3d has gained an extra electron to make it 3d10. The reason being is because the 3d has less energy than 4s when it's completely filled. Now we need to look at how we draw electronic configurations but do condensed ones involving noble gases. So let's take potassium for example. So we can see that potassium is in group 1, and if you look at the noble gas that occurs before potassium, so look up a period, you can see that that would be argon, which is why argon forms the core. Now potassium has an atomic number of 19, whereas argon has an atomic number of 18. The quickest way of working out how you complete this electronic configuration is by saying that potassium is in the S block, it's in the 4th period. If you look at the difference in electrons from potassium and to argon, you see there's 1 electron difference, which is why it's 4s1. Right, let's have a look at drawing the condensed electronic configuration for nickel. Nickel has an atomic number of 28, so have a look in the periodic table and see which element, which noble gas occurs before nickel, and we see it is argon. Argon has an atomic number of 18, and so here's the noble gas core argon. So we have 10 electrons left over. Because argon is in period 3, it just tells you that everything is full up until then, so just make sure you start at the next sublevel, so that will be 4, so it's 4s. 2, looking at the diagram, we now enter the 3d sublevel, and we have 8 electrons left over, so it's 3d8. Now let's have a go looking at sulfur. So sulfur has an atomic number of 16. Look in the periodic table and see which noble gas occurs before that. It is neon. And neon, this periodic table is annoyingly wrong, has 10 electrons altogether, has an atomic number of 10. So let's work out how we're going to do this. We have our noble gas core, which is neon. It is in period 2, and therefore we need to start with the 3s as being the next sublevel that we fill. It's going to be 3s2, then using our diagram we see it turns to 3p, and we've only got 4 electrons left to deal with, so that's why it's 3p4. One more time, let's have a go this time with chlorine. So chlorine has 17 electrons, an atomic number of 17. Looking in the periodic table we see that it is neon again, so that's our core. Neon has 10 electrons, so the difference here is 7. So because neon was in the 2nd period, we are moving into the 3s sublevel, and we only have 5 electrons to find room for, so according to the diagram the next sublevel that will be filled will be 3p, and it's just 3p5. So we'll start with the definition. It's the energy required to remove a mole of electrons from a mole of atoms in the gaseous state. That definition absolutely needs lining off by heart. The unit of ionization energy is kJ per mole. The first ionization energy is the energy required to remove the first electron from a neutral atom. Let's do an example using sodium. So there it is in its gaseous state. We've removed 1 electron, so it has a +1 charge, and there's the electron it's lost. Now we want the second ionization energy, the energy required to remove the second electron from from a +1 ion, which makes sense as we know that's what was formed in the previous ionization energy. Again, here's an example. So we'll take that sodium ion from before, it's still in gaseous state. It's going to become a 2+ ion, show that electron that has been removed. And then guess what? The third ionization energy, let's steal that definition. And then I'll just rub out some key words. So it's the energy required to remove the third electron from a +2 ion. So here's an example. We have an Na2+ ion becoming an Na3+ ion. There's the electron that has been lost. Just as a quick point, the first electron being removed requires the least amount of energy to remove it. Why? Because it's being removed from a neutral atom, as opposed to the subsequent electrons being removed. They're being removed from a positive ion, so more energy is required to overcome the additional attractive forces between the nucleus and the electrons. So I'm just adding that label there, stating that the first ionization energy requires the least energy as the electron is removed from a neutral atom, as opposed to here, subsequent electrons are removed from positive ions. So more energy is required to overcome additional forces. And then another thing to be aware of is that ionization energies are always endothermic. Let's think about why. And that's because energy is needed to overcome the attraction between the negative electron and positive nucleus. So therefore energy is taken in. Because in my example here I've shown the sodium atom losing one electron, then the sodium positive ion losing another electron, and then so on and so forth, we can call these successive ionization energies. And it's actually these successive ionization energies which provides evidence for the existence of energy levels. So we're going to use the successive ionization energies of sodium to illustrate this point. So I'm going to write the electronic configuration of sodium so you can see exactly what's going on. Right, so we know that in the first ionization energy of sodium, one electron is removed from sodium in its gaseous state to form an Na+ ion. So this is what's happening here. The ionization energy, there's a log of it here just so we can see it more clearly on the graph. But that first electron is being removed from the 3s sublevel, and it's going to be the easiest to remove. As we can see here, it's lowest. It has the lowest ionization energy. So the first electron, which we know from the electronic configuration is 3s1, is the easiest to remove. And we can see this huge jump, so much more energy is required to remove the second electron. Ask ourselves why, because that second electron is being removed here from n=2, the second energy level, which is therefore much closer to the nucleus, much less shielded, more tightly attracted. Then with successive ionization energy as the third electron, fourth electron, etc. removed, you see this gentle increase in ionization energy, and that's because all 8 of these electrons are being removed from that second energy level. Look, it adds up to 8, so they're being removed from n=2, so they experience very similar amounts of shielding. So gentle increase between the second and ninth ionized energy because all 8 of these electrons are removed from n equals 2. The same energy level. And then we look back again. Here you can see a large increase in ionisation energy between the 9th and 10th ionisation energy, and that's because the 10th electron is being removed from a much lower energy level. It's removed from n equals 1. This is very close to the nucleus, very tightly attracted, so it needs far more energy to remove it. But then, again, that next electron will be removed from the same energy level, hence why we see an only slight increase in ionisation energy. And we can apply this in past paper questions where they sometimes give us lots of data relating to the first, second, third, etc. So successive ionisation energies. And you're looking at the numbers. You're really looking at significant increases in successive ionisation energies. So yeah, this is going up, it's kind of doubling. And then all of a sudden, from the 4th to the 5th, we jump from just over 4,000 kJ per mole to 16,000. So this marks a significant increase in ionisation energy. So when we try and work out exactly which element it must be in period 3, we've been told it's period 3 here, the first thing you can conclude is that the first 4 electrons, because of the gentle increase in ionisation energy, were removed from the same energy level, whereas the 5th and 6th were removed from a different energy level. So in order to identify this element, you want to look in the periodic table at an element which has 4 electrons in its 3rd energy level, and that element is actually silicon. And we'll kind of work backwards to understand why. I'll just write out silicon's electronic configuration. So we are looking for 4 electrons being removed from n equals 3. Sure enough, here are those 4 electrons. So we would expect a gentle increase in ionisation energy as the 1st, 2nd, 3rd and 4th electrons are removed. Sure enough. But then as we jump to the 2nd energy level, n equals 2, in order to remove the 5th electron, we can see a massive increase, and that's because that energy level is much closer to the nucleus. What about ionisation energies as we move across a period? Remember, a period is a horizontal row in the periodic table. So the general trend here is that ionisation energies increase in value across a period. Make sure you've got a detailed explanation for this. And that's because the nuclear charge increases within the atom's nucleus. Remember, that's related to the number of protons being present. And you can see that by looking at the atomic numbers increasing across a period. But the electrons are in the same energy level, and as a result of the increased nuclear charge, there's a stronger attraction between valence, so that's the outer electron, and the nucleus, meaning that more energy is required to remove that electron. Now, first ionisation energies provide evidence for the existence of S and P sublevels. So we'll use the first ionisation energies of period 3 elements to explain this. So as we would expect, based on what I just said, you'd expect a general trend of an increase in ionisation energy. Sure enough, as you move across the period from sodium to argon, you do see a general increase in ionisation energy, all for the reasons I just specified, to do with increased nuclear charge, the electron being removed from the same energy level. However, if they're being a bit mean, they could ask you about some of the more anomalous ionization energies, such as this decrease in ionization energy from magnesium to aluminium. We really need to understand why that occurs. So in order to understand that decrease, let's take each of their electronic configurations in turn. So magnesium is 1s2, 2s2, 2p6, 3s2. Aluminium is 1s2, 2s2, 2p6, 3s2, 3p1. The crucial thing here is looking at which sublevel that first electron is removed from. The first electron in magnesium is removed from 3s. You can see it being removed here, as opposed to the first electron from aluminium being removed from 3p. Now, as we consider the energy, you can see that magnesium requires more energy to remove one electron compared with aluminium, and that's because the 3p orbital here for aluminium is slightly higher in energy than the 3s, meaning that for aluminium it takes less energy to remove that electron. So the longer that arrow, the more energy required to remove the electron. So you can see here very clearly that the first ionization energy of period 3 elements really do help prove the existence of the S and P sublevels. So the first ionization energy of aluminium is lower than that of magnesium because for magnesium the electron is removed from the 3s sublevel. This requires more energy than aluminium. For aluminium, the electron is removed from 3p. 3p is higher in energy than 3s. So be really specific when you're pointing out these trends. Work out the electronic configurations for each of the elements and then really understand where that electron is being removed from. So we've talked about this decrease in ionization energy from magnesium to aluminium. Now let's consider why the ionization energy decreases from phosphorus to sulfur. There's going to be a slightly different explanation here. So the first ionization energy decreases from phosphorus to sulfur because, slightly different reason this time, let's take phosphorus's electronic configuration. I'm going to use the condensed noble gas notation here. There's phosphorus, here's sulfur. We need to understand how these electrons are occupying their orbitals. So that 3s sublevel is filled. What about 3p? We know we need to add 3 electrons here, but remember, when filling the orbitals, they fill them singly. Whereas if we now take sulfur, you have a pairing of electrons in the 3p sublevel. These electrons here repel, and what that really means is it makes it easier to remove one of them from the atom of sulfur, and this has a result of lowering the ionization energy for sulfur when compared with phosphorus. So our explanation is, in sulfur, the electrons are paired in one of the 3p orbitals. These electrons repel, so it makes it easier to remove an electron. So as a result, sulfur has a lower first ionization energy than phosphorus. And then lastly, what about first ionization energies as we go down a group while they decrease down a group. The reason for that is because that outer electron, the valence electron, is further from the nucleus, more shielded and therefore more easily lost. We know that the ions get bigger down a group, so as you see in this graph here, that first ionization energy decreases, and we're illustrating the point using group 2 elements, so we can see from beryllium down to barium a decrease in first ionization energy. Use your knowledge of electron configuration and ionized energies to answer this question. The following diagram shows the second ionization energies of some period 3 elements. Remember, with the second ionization energy, let's take magnesium for example. You're taking that 1+ ion. The second ionization energy means you're removing that second electron. So a summary equation could look something like this. Draw an X on the diagram to show the second ionization energy of sulfur. So let's have a look at sulfur's electronic configuration. So it has 16 electrons. So as we work out the electronic configuration, remember this is 1s2, then we move on to 2s2, 2p6, 3s2, 3p4. So I've drawn the electronic configuration for the sulfur atom. Let's work out what happens at the first ionization energy. And in order to do that, let's look more closely at this 3p orbital. So remember, you've got 3 orbitals, and those 4 electrons will be initially arranged singly before filling up doubly. So there's 3p4. Now with that first ionization energy, you are losing that first electron here. And if you've studied this carefully, you'll know that the first ionization energy sees an actual decrease in the ionization energy for sulfur. So you'll see a dip in the ionization energy, which is an anomalous thing. However, you've been asked about the second ionization energy, so it doesn't matter which electron you lose. This is just a normal situation where you're just losing an electron from one of those orbitals. So in this case, the ionization energy trend holds for the whole of period 3, which is that you'll see an increase. So in terms of your answer, because you're being asked about the second ionization energy, you'll see an increase. If you'd been asked about the first ionization energy, you would have seen a decrease, and that's why it's so important that you understand this so carefully, because after all, that's only worth 1 mark, and look how much work I've had to do for that. Number 2, write the full electron configuration of the Al2+ ion. So here's Al. Let's write out its electronic configuration. So 1s2, 2s2, 2p6, 3s2, 3p1. We're after Al2+, which means we need to lose 2 electrons. So I'm going to lose that 1 and turn that into a 1. So my final answer here is 1s2, 2s2, 2p6, 3s1. Write an equation to show the process that occurs when the second ionization energy of aluminium is measured. So we've already removed 1 electron, so we have a 1+ charge. The second ionization energy means that we're producing a 2+ ion, and don't forget to include your state symbols in the addition of that electron. Give 1 reason why the second ionization energy of silicon is lower than the second ionization energy of aluminium. Let's have a look at their electronic configurations in order to understand this. So here's their electronic configurations when they're just atoms. Let's have a look what happens with their second ionization energies. So here's the arrangement of the electrons in the orbitals beforehand. Just looking at that 3p sublevel, and then because it's important, we'll look at that 3s sublevel as well. So if we're looking at silicon, when we look at the second ionization energy, we're removing 2 electrons, which both come from that 3p sublevel. With aluminium, 1 is coming from the 3p sublevel, 1 is coming from the 3s sublevel, which the s sublevel is closer to the nucleus, more tightly attracted, and therefore will require more energy. So let's write that down. Remember, you can argue it either way, but let's say in aluminium, the second electron is removed from the 3s sublevel, which is lower in energy than silicon's 3p sublevel. Now, some calculations will want you to convert between the number of atoms to the moles to the mass, and I definitely think that using this arrow system at the top of this page is the most straightforward way of doing this. If you write it out, it basically leads you the right way to the correct calculation. The only thing you need to remember is the value of Avogadro's constant, which is 6.02 times 10 to the 23. And remember, that stands for the number of atoms or molecules which are present in 1 mole of a substance. So let's have a look at a few examples, and hopefully you'll see that this arrow system really works. So in this first example, we're calculating the amount in mole of water in a sample containing 2.30 times 10 to the 3 molecules. So we're looking for the amount in mole. We have been given the number of molecules, so we're looking for moles, which is in the middle of this arrow setup. We've been given the number of molecules, and now we just need to follow the arrowhead to work out what we need to do. And so clearly we need to take the number of molecules and divide by Avogadro's constant. Now let's make sure we lay out your work nicely. We are doing A level or IB now. So I've written number of moles of water equals, we know it's the number of molecules given, and we need to divide that by Avogadro's constant, 6.02 times 10 to the 23. And this gives us a value which is 0.382 moles. So for question 2, we're calculating the number of oxygen atoms contained in 3 moles of glucose, which is C6H12O6. So this time we're calculating the number of oxygen atoms contained in 3 moles of glucose, C6H12O6. This one's trickier because it's O6, but we'll only start making sure that we haven't made a mistake with that towards the end of this working out. So we're looking for the number of oxygen atoms. So looking at my diagram above, what I need to do that is put number of, I'm going to write molecules because we've actually got a molecule here, C6H12O6, equals the number of moles times Avogadro's constant. Let's substitute in the values. So it's 3 times 6.02 times 10 to the 23. Work that out, and it's 1.806 times 10 to the 24. But crucially, that's the number of molecules of glucose, but we need the number of atoms of oxygen. And you can see within that 1 molecule of glucose, there are 6 atoms of oxygen, which is why we need to multiply that number by 6 to get a value which is 1.08 times 10 to the 25. And this is an equation which you must know off by heart, which is PV equals nRT. It's not difficult to use, but it is important that every single term is in the correct unit. So let's first of all work out what PV nRT stands for. So P stands for pressure, and this must be in pascals. V stands for volume, which must be in meters cubed. N is for number of moles, so it doesn't have a unit. R is the gas constant, which you must remember the value of, which is 8.31. And lastly, T stands for temperature, which must be in Kelvin. And now we're going to look at a couple of examples so that you can actually see how you would correctly use this equation. So in this first question, we're being asked to calculate the volume in meters cubed of a balloon filled with 0.4 moles of hydrogen gas at a temperature of 22.9 degrees Celsius and a pressure of 1.20 pascals. So let's start by writing out the ideal gas equation, PV equals nRT, and now we're going to list each of those values and make sure they're in the right unit. So P stands for pressure, and it's 1.20 pascals, which is great. That's the unit we want. Volume we're after, so we're going to call that X. N is the number of moles, given as 0.400, perfect. R is the gas constant, which you need to know off by heart, which is 8.31. And then lastly, we've been given the temperatures being 22.9 degrees Celsius, but remember we need that in Kelvin. The way in which you convert a degree Celsius to Kelvin is by adding 273 to it. So let's just quickly do that now. And you get 295.9 Kelvin. So we're ready to go. We can just substitute in all of our values. So I like to just keep rewriting what it is I'm doing so I don't get confused. Pressure is 1.20. Volume we're after. N is 0.4, R is 8.31, T is now 295.9. So let's sort it out. So 1.2x equals, multiply these three numbers together on the right hand side to get 983.5716. How do you get x by itself? Well, you need to divide both sides by 1.2, and x equals 820 meters cubed to three significant figures. So the empirical formula is the simplest ratio of atoms of each element present in a compound. And just to make that really clear what that actually means, we need to look at the molecular formula at the same time, because although they sound very similar, and indeed they are very similar, they have slightly different definitions. So the molecular formula is the actual number of atoms of each element present in a compound. So let's take propene as our example here. So looking at its molecular formula, what is the actual number of atoms of each element present in propene? Well, we know it contains 3 carbon atoms. It obeys the general formula CnH2n, which is why its formula is C3H6. That is its molecular formula. However, if we look back at our definition of an empirical formula, we're looking for the simplest ratio. So basically we want to cancel this down. Now we can see by looking at the molecular formula of propene that 3 goes into it. So we want to cancel by 3, means we'd have CH2. And that is our empirical formula, and that's actually what we're going to be looking at calculating now. So in question 1, a compound contains 40% carbon, 6.73% hydrogen and 53.2% oxygen by mass. Determine the empirical formula. And we know, if you've been following me from GCSE, IGCSE, I like to use a table format for my mole calculations. So first of all, start by listing your elements. So we've got carbon, hydrogen and oxygen. Make a table, and you want to write mass, MR and number of moles down the left hand side. So the mass we've been given in the question, although it says all the masses in percentages, it doesn't matter because effectively they're all ratios. So you could have 40 grams of carbon and that would still be 6.73 grams of hydrogen, which is why we're allowed to write down the numbers exactly as they are. Then use your periodic table to look at their atomic masses. You'll see that carbon has a mass of 12.01, hydrogen has a mass of 1.01, oxygen has a mass of 16 exactly. Now using this formula triangle, which hopefully you'll be very familiar with, we have mass at the top, MR and number of moles at the bottom. So if we cover the one we're after, which is number of moles, you can see that that is given by mass divided by MR. So when we look at the third row of our table, that's the exact calculation we're going to be doing. So first of all, for carbon, divide 40 by 12.01 to get 3.33. To get the number of moles of hydrogen, do 6.73 divided by 1.01 to get 6.66. And lastly, for oxygen, do 53.27 divided by 16 to get 3.33. And now at this point, you want to have a look at those 3 numbers and then choose the smallest one and divide all the values by the smallest number. And as we can see, that will be 3,3. So we're dividing every single value by 3.33 to get our ratio of 1 to 2 to 1. Now don't forget to answer the question. We're looking for a formula, so we have a final formula which is CH2O. So slightly more complicated example in question 2, but it still remains similar, the method you need to use. So magnesium ribbon 10 centimeters long is placed in a crucible and its mass recorded. The crucible is heated strongly and air is allowed to enter. After cooling, the crucible and its lid and contents are reweighed. So let's make sure we're clear of what's happened here. Because we've got magnesium and it's being burnt in air, we know that we're going to be producing magnesium oxide, and indeed that's the formula we're after, but we need these results given in blue to help us work that out. So we have the mass of the crucible and the lid, which is 30.911 grams. We have the mass of crucible plus lid plus magnesium, which is 31.037 grams, and lastly the same but with magnesium oxide, which is 31.106 grams. So what we need is to find the masses of magnesium and oxygen. It's nice and easy to find the mass of magnesium. You simply need to take these numbers away from each other. So do 31.037 grams, take away 30.911 grams, and you'll get a magnesium mass, which is 0.126 grams. Next up, we want the mass of oxygen. Let's number them 1, 2 and 3. So 2 and 3 are exactly the same, apart from we also have oxygen in number 3, which is why you just want to take 2 away from 3 in order to work out the mass of oxygen. So do 31.106, take away 31.037 to get a mass of oxygen, which is 0.069. And now we're ready to do our empirical formula calculation. So as always, start with your elements. We've got magnesium and oxygen. Here's our table as before. So our masses we've just worked out for magnesium is 0.126 grams, oxygen is 0.069 grams. Using your periodic table to look up their atomic mass, you can see that for magnesium that's 24.31, for oxygen that's 16.00. To work out the number of moles, we do mass divided by mR, and you get a number of moles for magnesium of 5.2 times 10 to the minus 3. For oxygen, that is 4.3 times 10 to the minus 3. This is slightly more difficult, but look for the smallest number. It is this one. So we divide both numbers by that smallest number. To get obviously a 1 on the right hand side and 1.2 on the left hand side. Now because this is A-level IB, they're not necessarily going to be nice easy numbers like they were at GCSE, so we need to make both of these whole numbers, and the way you do that is you have a look and you see the 1.2 is the problem. So how would you make that a whole number? Well, you need to multiply it by 5 to get rid of that 2. So multiply both sides by 5 to get 6 versus 5, and that is your final answer. So the formula is Mg6O5. Now I want to show you how to balance ionic equations. So we'll start with this example here. It's very important that you check the state symbols. Only the aqueous compounds will dissociate into ions. As calcium carbonate here is solid, it will not dissociate. So our first step really is to separate all of these compounds which are aqueous into their constituent ions, making sure you have the right number of each. I'm just going to squeeze on that final 2Cl minus aqueous. Now we need to cross out the spectator ions. Now the spectator ion is just ions which remain unaltered on both sides of the equations. So it's really a game of spot the difference. You can see that Cl minus appears on both sides, 2Cl minus, so we can cross those out. 2Na plus appears on both sides and everything else is different. Now rewrite everything you have left over. And that is your balanced ionic equation, which shows your calcium ions reacting with your carbonate ions to form calcium carbonate solid. And you'll notice that the charges on both sides add up to 0, which is after all what you need. Percentage atom economy is given by the following equation. It's the mass of the useful product divided by the mass of all the reactants multiplied by 100. So it's not too complicated. Just make sure though that you use the wording of the question to identify the useful product. So the percentage atom economy is a theoretical measure of the proportion of the atoms used in a reaction that becomes the desired product if it is 100% efficient. An equation for the overall reaction in the production of sodium carbonate. So there's our useful desired product is the following. Calculate the percentage atom economy. So percentage atom economy We're going to use the equation from above, equals mass of useful product divided by mass of all reactants times by 100. So here is our useful product. So we'll find its MR divided by mass of all reactants. Just be a little bit careful here. You want to use the large numbers as well when you're working this out. So we're going to do the MR of 2 NaCl plus the MR of calcium carbonate. And then just use your periodic table to find the various masses. So here's sodium. Pop it into your calculator. So our final answer here is 48.8%. So remember, yield is all about how much you actually make. And when you have an equation and you know certain amounts of reactants, then you can certainly predict using mole calculations how much of the product you should make. But remember, because a lot of the time reactions are reversible, products lost, it's not 100% efficient, side reactions take place, all manner of things happen, which means you don't get the amount of product that you would expect. So what we can do therefore is work out the amount that we would expect to get, have the amount that they actually got, and pop them into this simple equation in order to work out percentage yield. And the fact that you multiply it by 100 means that it's a percentage yield. So enough talking. As with all chemistry, it's better if we just get going with some examples. So in question 1, a company processes 200 kilograms of limestone a day. It collects 98 kilograms of calcium oxide, the useful product. What is the percentage yield? And as always, we need a balanced symbol equation. So limestone is calcium carbonate. And we know that we're producing calcium oxide as the useful product, plus carbon dioxide will be left over. So calcium carbonate is CaCO3, calcium oxide is CaO, carbon dioxide is CO2. Double check that it's balanced. Yes, it is. So using my favourite table format, we're going to put mass, MR, number of moles, and remember you're using this formula triangle in order to help you work out the number of moles. So in order to solve this question, first of all, we're actually looking for the theoretical mass of calcium oxide. So we're looking for this value. So I'm going to put an X here and pop into the table with the information you've been given. So you know you have 200 kilograms of limestone, so 200 will go in there. Then use your periodic table to work out various MRs. So if you work out the MR of calcium carbonate, so add up calcium plus carbon plus 3 lots of oxygen, you get 100.086. Do the same for calcium oxide, so you're going to do 40.078 plus 15.99 to get a value which is 56.077. Now we can work out the number of moles of calcium carbonate using our formula triangle, so we need to do our mass, which is 200 kilograms, divided by 100.086, and that gives you 1.998. And then have a look, check the balanced symbol equation. There are no big numbers, which means you're allowed to copy that number directly across to be the number of moles of calcium oxide. And now because we have MR, we have the number of moles, we can work out mass. And from our formula triangle, we can see we just need to multiply the mass by the MR. And so X equals 112 kilograms. And that's why it didn't matter that I didn't change my units, because it's comparable. So we now look at our formula. We know we have our actual mass of product produced as being 98. The theoretical yield was 112. So what is our percentage yield? We'll just do 98 divided by 112 times by 100, and therefore our percentage yield is 87.5%. I'll now show you how to answer an excess versus limiting reagent. When you have a reaction, you'll never guarantee you have the exact right amounts of your two reactants, so there'll always be one that you have more of in comparison to the other. So we'll start with this question. 3.2 grams of copper is reacted with 0.4 moles of concentrated nitric acid. work out which reagent is limiting and which one is in excess. As always, you'll need your balanced symbol equation. The easiest way I've worked out to do these is to make one of the numbers, it doesn't matter which one, make that equal x. And then I promise this will become super clear as I work through this question. You're going to set yourself up using that favoured table of mine with mass mR, number of moles, remembering that you need this formula triangle. So we know we have 3.2 grams of copper, so I'm going to pop that there. My x is now my number of moles of concentrated nitric acid, so I'm going to put that here. Let's add the AR of copper using the periodic table. It's 63.5. We now have enough information to find the number of moles by doing mass divided by MR. So that gives us a number of moles of copper of 0.05. Check the mole connection, it's 1 to 4. So we multiply that number by 4 to find the number of moles of nitric acid needed to fully react with the 3.2 grams of copper. So just to get rid of the x here now, let's look at what we have. We've worked out that we need 0.2 moles of nitric acid, but we were given 0.4, which is obviously far more than the 0.2 we need. So we can see straight away that the nitric acid is in excess. And therefore, by definition, copper is the limiting reagent. Now, there are lots of different reasons why you carry out a titration. One could be that you want to produce a soluble salt which contains ammonium, potassium or sodium. Because of the way in which the soluble salts dissolve, you need to use a titration in order to work out very accurate volumes of both reactants. So that could be one reason why you want to carry out a titration. Another reason you want to carry out a titration is because you want to carry out a titration calculation in order to find out an unknown concentration. But what Amelia and I are focused on doing today is showing you how to accurately carry out a titration and to accurately find the volume of hydrochloric acid needed to neutralize a particular volume and concentration of sodium hydroxide, because that's really what a titration is. It's adding a very specific volume of one reactant to another, causing a neutralization reaction to take place, and we use an indicator in order to tell us the neutralization has occurred.
Okay, so we're going to put hydrochloric acid in the burette and sodium hydroxide in the flask. So I'm going to load the burette with the acid. Usually you wash it with acid 2-3 times, but this time we just do once. So the tap, of course, must be off, closed, and very slowly because it loads very quickly. Otherwise it will overflow. And
notice you can carry out a titration in either way. You could have the acid in the burette or the acid in the conical flask. Just depends on which indicator you're using.
Okay, because I want to start from 0, I'm going to lose a bit of acid in the beaker and also to get rid of the bubbles that sometimes forms in the tap. That's it.
Perfect. In order to avoid parallax errors, you need to make sure you read from the bottom of the meniscus, because if you look at liquid in a particularly narrow tube, you notice that it has a very curved shape, so you need to read from the bottom of what's known as the meniscus.
Then you add the sodium hydroxide to the flask, which has been previously washed with sodium hydroxide solution.
Multiple washes.
So this is 25 cubic centimeter of sodium hydroxide.
This is a glass pipette and it's used to produce very accurate volumes of solution.
Okay, then you add a drop of methyl orange.
So methyl orange is an indicator which, as you can see, turns orange in an alkaline solution. Remember that sodium hydroxide is strongly alkali.
And then I place it.
Yeah, so we're ready to begin our titration. Notice that the end point, that's when neutralization occurs, is when the methyl orange turns from orange to red. The whole point of using these indicators is they have a very sharp end point. They have a sharp change in color, which is why methyl orange, phenolphthalein, they're both ideal for use in titrations. Universal indicator is inappropriate because remember it shows a range of different colors. So Amelia is going to open the tap and start slowly adding hydrochloric acid to the sodium hydroxide. The beauty of a burette is that it can add drop by drop. So it makes it far more accurate than a measuring cylinder or a beaker. She's swirling the flask in order to mix the contents. So we place the tile underneath the flask in order to observe the colour change.
When now you have the drop, you will see pink and then disappear.
Yeah.
So it's not ready. It doesn't mean that that is the end point, because it must be a color that doesn't disappear when you swirl the flask.
Yeah.
See? Pink starting to appear and then disappear. So it means that we are close to the end point.
Mm-hmm.
Oh, that's it.
Oh yeah, it is pink.
This is the color we want.
So we've reached our end point. The solution, although it looks pink, in your exam you're going to have to say that it's red, and that means that the solution is slightly acidic. So the essential thing now is that we read the volume of the acid that was added. Notice that the burette runs from 0 centimeters cubed down to 50. So we're really trying to work out what this volume is here. So
yes, it's 25.
Yeah. So reading from the bottom of the meniscus, we can see that 25 centimeters cubed of acid was added.
So if you have this color, it means that you have been further.
Yeah. Acid-based titration calculations. A student carries out a titration to determine the concentration of hydrochloric acid. The student titrates the hydrochloric acid against a standard solution of sodium carbonate. The student prepares 0.15 mole dm to the -3 sodium carbonate in a 250 centimeters cubed volumetric flask. The hydrochloric acid is added to a 50 centimeters cubed burette. The student pipettes 25 centimeters cubed of sodium carbonate into the conical flask. The student's burette readings are shown in the table. Calculate the concentration of hydrochloric acid. Before we can get going using my favourite table, we do need to find out the volume of hydrochloric acid used, and this is where it's very important that we use concordant results. Just check the titer here. So this is really the difference in these two numbers. You're looking for results which are within 0.2 centimeters cubed of each other. So look through your titers. It's going to be run 1 and run 3. So let's find our mean titer. So our mean volume of hydrochloric acid added by simply adding 24.2 to 24.3 and dividing by 2 to get a value of 24.25 centimeters cubed. And now it's very straightforward. We're going to use the same method that I've been teaching you guys at GCSE and IGCSE. So we'll take our balanced symbol equation. Going to set ourselves up with my favoured table. Don't forget your formula triangle. And the other thing to remember is that you need to often convert your centimetres cubed to decimeters cubed. And in order to do that, you divide whatever number by 1000. But you're actually ready to go now. We're after the concentration of hydrochloric acid, so that means that's our X value. We just found the volume of hydrochloric acid added, which was 24.25. Because that's in centimeters cubed and I need it in decimeters cubed, I'm going to divide by 1000. Our sodium carbonate, we were told we had a concentration of 0.15. The volume added was 25 centimeters cubed. Again, that needs to be in decimeters cubed. But now I have enough information to find the number of moles of sodium carbonate. I do that by doing concentration times volume. Let's check the mole connection. It's 1 to 2, so I simply need to double that number to find the number of moles of hydrochloric acid. And then finally, to find the concentration, we do number of moles divided by volume. So we take this number and divide it by this number. And there is our final answer. Now we'll move on to discuss uncertainties, and all readings and measurements that you take have an inherent uncertainty, and good experimental design will attempt to reduce the uncertainty in the outcome of an experiment. A few key terms here which you're probably familiar with. A reading is the value found from a single judgment when using a piece of equipment. For example, if you read a thermometer temperature reading, the volume from a measuring cylinder, etc. The uncertainty in a reading is plus or minus half of the small division on the scale. I'll use this measuring cylinder to illustrate the point. This measuring cylinder is going up in increments of 2 centimeters cubed, which means the uncertainty here is plus or minus 1 centimeters cubed, because that accounts for half of the smallest division on the scale. A measurement now. These are the values taken as the difference between the judgment of two values, such as if you're taking a volume reading from a burette or a ruler. The uncertainty in a measurement is therefore the sum of both uncertainties from each reading. The percentage uncertainty, you'll commonly be asked, is when you take your uncertainty divided by your measured value and you multiply it by 100, and then the maximum total percentage uncertainty when using different apparatus across an experiment is the sum of all the individual equipment uncertainties. But don't worry, if we actually start doing some calculations, we'll be able to understand this far better than just looking at definitions. So 90 centimeters cubed of carbon dioxide was collected in a gas syringe with markings at over 1 centimeters cubed. Calculate the percentage uncertainty in the volume of gas collected. So here's our equation. Percentage uncertainty equals uncertainty divided by measured value times by 100. So what is plus or minus half the small division on the scale? Well, that's plus or minus 0.5 centimeters cubed. What was our measured volume? It was 90 multiplied by 100. So our percentage uncertainty is 0.56%. Let's take a slightly trickier example. A student carries out several acid-base titrations and records the results. The rough run has been excluded. The total uncertainty in each burette reading is plus or minus 0.05 centimeters cubed. Calculate both the mean titer and the percentage uncertainty for the mean titer. So our first step is to identify the concordant results. That depends on your exam board, but we've identified run 1 and run 3. So we're going to find our mean titer first of all by finding the average of these two values to get 23.95, and then to find our percentage uncertainty, we do our uncertainty, which we've been told is 0.05, divided by our measured volume. Just be a little bit careful. Remember, we took 2 readings, which is why we need to multiply that uncertainty by 2 and then times by 100 to find the percentage. So our final answer is 0.42%. Don't forget to be able to list ways in which uncertainties can be reduced. So we could use equipment with finer scale divisions, such as a balance that has more decimal places. Use a titer with a larger volume when carrying out a titration. And similar to that second point, use a larger mass when weighing a solid. Time for a super quick recap of ionic bonding. The crucial thing to remember here is that it occurs between metals and non-metals. Remember that the metal loses electrons in order to form positive ions. By doing so, it will gain a full outer shell, whereas the non-metal atoms gain electrons to form negative ions. If they ask you to define an ionic bond, it's the strong electrostatic forces of attraction between oppositely charged ions. Here's your bread and butter of ionic bonding. You'll be familiar with this example, sodium chloride. There's the all-important metal sodium. As you can see here, it's losing an electron to gain a 1+ charge over here. The chlorine atom gains an electron in order to gain a full outer shell. Because it's gained an electron, it gains a negative charge. Here are the new electronic configurations based on the movement of those electrons. Our second example here is magnesium fluoride. The magnesium, being in group 2, needs to donate 2 electrons Fluorine in group 7 can only gain 1 electron, which explains why you need 2 fluoride ions for each magnesium ion. And again, the new electronic configurations formed are shown here. Now it's time to turn our attention to a covalent bonding recap. The difference here is that covalent bonding occurs between two non-metals. If you're asked to define a covalent bond, it's the strong electrostatic force of attraction between a shared pair of electrons and positively charged nuclei. A single covalent bond contains a single shared pair of electrons. A double bond will contain 2 pairs, a triple bond will contain 3 pairs. As with ionic bonding, the purpose of covalent bonding is to gain a full outer shell. As we've just said, it does this through the sharing of electrons. Chlorine, which we know exists as a diatomic molecule, 2 atoms, and it's through that single covalent bond it's able to do that. Carbon dioxide is slightly different. Here you'll see a double covalent bond. But notice that for all these atoms, they have a full outer shell, which in this case means 8 electrons. Coordinate bonding. This is just a special type of covalent bonding. So again, you'd expect 2 non-metals and for electrons to be shared between atoms. But what sets coordinate bonding apart is the fact that the shared pair of electrons are both supplied by one atom. Remember, another name for coordinate bonding is dative bonding. So what sort of conditions need to be present for a coordinate bond to form? The atom which accepts the electron pair must be electron deficient. So by electron deficient, we mean that it doesn't have a filled outer main level of electrons. And then secondly, the atom donating the electron pair must have a lone pair of electrons not already involved in a covalent bond. So let's use the ammonium ion NH4+ here to illustrate the point. So remember, nitrogen is in group 5. So there's its 5 electrons. Hydrogen has only 1 electron in its outer shell. So to show that we have everything we need for a coordinate bond to form, you can see here's our electron deficient atom, the H+, and here's the lone pair of electrons present on nitrogen, which isn't already involved in covalent bonding. And then in terms of showing the bonds, remember you use an arrow to represent the coordinate bond formation, and the arrow points towards the atom which accepts the electron pair, hence why I'm drawing it in this way. I must remember to add the charge. Do remember that coordinate bonds have the same length and strength as normal covalent bonds. Now we're going to compare various structures. So starting with giant covalent structures, which we now describe as being macromolecular. These have very high melting and boiling points, e.g. diamond, which melts at approximately 4,000 degrees. That's ridiculously high. Silicon dioxide melts at around 1,600 degrees Celsius. Don't forget the second allotrope of carbon, so you've got diamond as being one of them, but also graphite, which also melts at approximately 4,000 degrees. So extremely high melting points here. Why is that? Well, diamond in particular has a tetrahedral structure, and that means that each carbon atom is bonded to 4 others. And so it's made up of very many strong covalent bonds. And each of these covalent bonds requires quite a lot of energy to break. Moving on to our second structure, which is giant ionic structures. Remember, for it to be an ionic structure, we need to have a positive ion being attracted to a negative ion. So remember that metals form positive ions, non-metals form negative ions. So we could use sodium chloride as an example here. also magnesium oxide, so metals and non-metals being combined here. Now they also have high melting points, not ridiculously high, it tends to be less than 1000 degrees. So for sodium chloride it's 801 degrees Celsius. For potassium chloride it's 770 degrees Celsius. Why do they have relatively high melting points? Well, that's due to strong electrostatic forces of attraction between oppositely charged ions require a lot of energy to break. Now moving on to giant metallic structures. So as the name suggests, these are just made up of metals. Now on the whole they have quite high melting points, e.g. aluminium has a melting point of 660 degrees Celsius. Magnesium has a melting point of 650 degrees Celsius. Why is this? Well, that's due to strong electrostatic forces of attraction between the positive metal ion and the sea of delocalized electrons. Now do be aware that the group 1 metals, they obviously have low melting points. We're talking about elements such as lithium, sodium, potassium. Remember, they're soft, they have low density, they're really unusual metals. We're not going to go into why now, but just so that you don't think that I don't know that those metals have low melting points. This is just a general video about the fact that metals in general have high melting points. I decided the best way to do this was to draw a summary of the steps I follow in order to get to my final answer. It will probably seem a little bit confusing at the beginning, but once we look at some examples, hopefully everything will become clear. When you're doing this, first of all, you want to draw a ball and stick diagram of whatever the compound is you have been given. So let's use methane, CH4, as our example. A ball and stick diagram in this case would have carbon in the centre and sticks would have hydrogen bonds coming off. So that's your ball and stick diagram. So for step 2, for the central atom, work out its group number. So in this case, from our ball and stick diagram, we can see that carbon is the central atom. Carbon is in group 4. So I'm going to make a note that it is in group 4. From the number of sticks, count the number of bonds, ignoring whether they're single or double. So we can look at the number of sticks surrounding that carbon atom. There are 4 sticks belonging to the 4 hydrogen atoms, meaning that there are 4 bonds. So I'm going to make a note and say that that is 4. Step 4. For positive ions, delete electrons. For negative ions, add electrons. Now, don't worry, this obviously isn't an ion. It's methane, it's neutral, so this isn't relevant at this point. However, further examples will show when this becomes relevant, but I wanted to write it as part of the summary. Step 6. Add all these numbers together. So we can see we're simply adding 4 plus 4 in the case of methane, which is 8. And then finally, we want to divide by 2 to work out the number of electron domains. So what's 8 divided by 2? Well, it's 4. So we have 4 electron domains. And now it's a matter of you learning the various names and angles and shapes for things which have, for example, 4 electron domains, 2 electron domains, etc., etc., which is what I'll now show you. But it is true that you will have to do quite a lot of rote learning. So, for example, you will have to learn that 4 electron domains is a tetrahedral shape and does have a bond angle of 109.5 degrees. So, unfortunately, there's no way of avoiding that. So we're going to go through these in order, starting with BeCl2. So if we look at my first step, I said we need to draw a ball and stick diagram, which looks like this. Now beryllium is in group 2, and that is the central atom, so that's 2 electrons. Count the number of sticks. We have 2 sticks, so that's 2 bonds, so that's another 2 electrons. It's not charged, which means we just need to add these up in order to work out that we have 4 electrons. My next step told me to divide by 2, and we know therefore that we have 2 electron domains. You need to learn the shape for 2 electron domains, and it is in fact linear, so we're just going to draw it out again. It will look very similar to the original ball and stick diagram.
and this has a bond angle of 180 degrees, which makes sense because it's in a straight line, and we say that this shape, as I've already said, is linear. Moving on, we're going to look at BF3. So our ball and stick diagram will show boron in the middle with 3 fluorine atoms coming off. Boron is in group 3, which means it has 3 electrons in its outer shell. Count the number of sticks, so the number of bonds, we can see that that is 3. It's an uncharged compound, which means we don't need to add or subtract electrons. So total those up, you have 6 electrons. According to my rules, we need to then divide by 2. So we know we have 3 electron domains. And you need to remember the shape for a molecule with 3 electron domains, and that is trigonal planar. And it will look like this once you finish drawing it. So again, similar to the ball and stick diagram. Because it's effectively a circle divided by 3, it means that the bond angle must therefore be 120 degrees. CH4, methane, which we've already met. We have a ball and stick diagram which looks like this. Carbon is in group 4, which means that there are 4 electrons in the outer shell. There are 4 sticks, so that's 4 bonds, so we're going to add another 4 electrons for that. It's a neutral compound, so no need to add or subtract electrons. Total those up, we have 8 electrons. According to my instructions, we therefore divide by 2, so we know we have 4 electron domains. The name for a shape made up of 4 electron domains is tetrahedral. This is a more complicated diagram to draw, so you need to use dotted lines and wedges to show the 3D nature of the molecule. So it looks something like this, with a bond angle of 109.5 degrees. Now do remember that the wedge represents the hydrogens coming out of the page. The dotted line shows the hydrogens going towards the page or into the page. Now things get more complicated if we take ammonia, for example, NH3. So drawing our ball and stick diagram, it will look like this. Nitrogen, the central atom, is in group 5, so it has 5 electrons in its outer shell. Now we need to count the number of sticks, and we can see that there are 3 sticks corresponding to the 3 hydrogen atoms, so that's why I write 3 electrons here. It's a neutral atom, so all we need to do is now add up the total here. We don't need to subtract or add electrons. Then we divide by 2, and we know that there are therefore 4 electron domains. However, only 3 of those electron domains are occupied by hydrogen, as you can see from the diagram, meaning that we have 1 domain left over, which we know contains 2 electrons, which we therefore know exists as a lone pair, which we draw like this. And it's really important to notice that lone pairs repel more strongly than bonding pairs, and this will become important when we look at the new bond angles. So working out the shape here, well, we're going to have a structure which is called pyramidal. We show the lone pair here above the nitrogen. We need to show the 3D nature of the compound. And because the lone pairs repel more strongly, it means that those hydrogens move closer together, which is why their bond angle is 107 degrees. Moving on to water now. Again, this isn't a straightforward example, so ball and stick diagram will look like this. Oxygen is the central atom. It is in group 6, which means it has 6 electrons in its outer shell. Now we're going to count the number of sticks, so that's the number of bonds. So there's 2, because we can see the 2 hydrogen atoms, so we add 2 electrons, add those up, and meaning that we have 8 electrons, we divide by 2 to work out the number of domains, and therefore we have 4 electron domains. But we know that only 2 of those are occupied by hydrogen, meaning that there are 2 domains left over, which we'll see as 2 lone pairs. And again, you need to learn what this looks like. So So you're going to have oxygen with 2 lone pairs coming off it, 2 hydrogen atoms, and again a reduced bond angle of 104.5 degrees due to the presence of those lone pairs. This has a strange name, which is that it is V-shaped, or you could describe it as bent. Let's look at the effect of ions now, so a charged particle, to see what that middle chunk of my summary was really talking about. So, starting with our ball and stick diagram, and I'm going to include the fact that it is a charged ion. So nitrogen is the central atom. Remember, nitrogen, you can use your periodic table for this, will show you that it is in group 5, which means it has 5 electrons in its outer shell. Now count the number of sticks, or the number of bonds to hydrogens, and we can see that that is 4. However, we have a positive charge here, and remember from the summary that a positive charge means that you have to remove an electron for each positive charge, which is why I'm going to say -1 electron here. So when we add that up, we do 5 plus 4 is 9, we minus 1 to get 8, and then as with before, we divide by 2 to work out the number of domains, so we have 4 electron domains. Check the bonds. Well, we've got 4 hydrogen atoms, which means they're occupying all the electron domains, so we have no lone pairs. So actually this is quite a nice straightforward example. Because we've got 4 electron domains, no lone pairs, it means we have a bog standard tetrahedral structure. Nitrogen in the middle, hydrogens, dotted lines, wedges. Because it's tetrahedral, it will have a bond angle of 109.5 degrees, and just include that square bracket and the positive charge. Right, I hope you guys aren't losing the will to live, but I'm determined that I'm going to give you a very comprehensive talk through of this topic. So PF5, so phosphorus in the middle, and then I'm just going to casually arrange my fluorines around the outside. So check in the periodic table, you see that phosphorus is in group 5, meaning that it has 5 electrons in its outer shell. Count the number of fluorines attached. Well, there are 5, so we're going to add those 5. It's not charged, so we can simply just add them together to work out that there are 10 electrons. Divide by 2 to work out the number of domains of electrons. We just need to remember what the shape is for 5 electron domains, and it's actually called trigonal bipyramidal. So once you know the method, it's quite straightforward. It's just quite a pain learning all the names and the bond angles. And this is what this will look like once you've finished drawing it out. And do pay attention to the 3D nature of it. And you need to learn a couple of bond angles here. Clearly that angle there is 90 degrees, but the angle between these two over here, because it's trigonal, it will be 120 degrees. SF6 now, so sulfur is in the center. Let's arrange our fluorines again. So sulfur is in group 6, meaning that there are 6 electrons in the outer shell. Count the number of sticks, so the number of bonds, and we can see that there are 6 bonds. It's a neutral atom, so we don't need to add or subtract electrons. We simply add them together to get 12 electrons, divide by 2 to find out the number of domains, so it's 6 domains, nice and straightforward. They're all occupied by fluorine, so we have no lone pairs. You need to learn that the shape for 6 domains is known as octahedral, and this is how you draw the shape. The bond angle here is 90 degrees. And the absolute last example I'm going to show you is XCF4. So let's arrange our Fs around our xenons. So our ball and stick diagram is complete. Xenon is clearly the central atom. It's in group 0 or group 8. I'm going to say group 8 because we know it has 8 electrons in its outer shell, therefore. Now fluorine, count the number of sticks, so that's 4. It's neutral, so no need to add or subtract. So we have 12 electrons. Divide by 2 to calculate the number of domains. So we have 6 electron domains, where we can see that 4 are occupied using fluorine. There are 2 left over, which means that there are 2 lone pairs, because each domain is made up of 2 electrons. And you get a very strange shape which looks like this. (90°), and we call this shape square planar. Right guys, I really hope you found this helpful. I hope I've given you a foolproof way of working out what shape each molecule will be. Honestly, if you follow those steps, it works every single time. Just make sure you put effort into learning the various shape names, so linear, trigonal, planar, tetrahedral, etc. And remember, you need to note the fact that the lone pairs cause greater repulsion, so you'll see a reduction in the bond angle.
Now we're moving on to electronegativity, starting with the definition. Electronegativity is the power of an atom to attract a pair of electrons towards itself in a covalent bond. General trends you need to be aware of. Electronegativity increases up a group. Electronegativity increases across a period. We use the Pauling scale for measuring how electronegative an element is. An element with a score of 0 is the least electronegative, and as it moves towards 4, that is the most electronegative. So several things to point out right here, just this small chunk of the periodic table to consider. As we've already pointed out, the ability of the atom to attract a pair of electrons towards itself increases up the group. So hydrogen is more electronegative than sodium. Obviously hydrogen isn't in group 1, but it's still useful to consider the fact that it is more electronegative than sodium, and these numbers here correspond with that. As we go across the period, we can see that the electronegativity increases, so fluorine is much more highly electronegative compared with lithium, and it's actually in this right hand side of the periodic table you'll find the most electronegative elements. That really does include nitrogen, oxygen and fluorine. Fluorine is the most electronegative atom. Noble gases do not generally form covalent bonds. Why? Because they have a full outer shell, so therefore that's why no Pauling scale number is assigned here. Lastly, we'll point out the reasons for the electronegativity increasing up a group, because there are fewer electron shells, as we know. You could write out the electronic configuration to prove this, which means that less shielding occurs, the atoms are smaller, the nuclear charge is therefore stronger, attracting the electrons towards the nucleus. Then electronegativity increases across a group, and that's all to do with the number of protons in the nucleus increasing. So the nuclear charge increases whilst the energy levels remain constant, so the shielding remains the same. So that's why elements towards the right hand side of the periodic table will be more able to attract the electron pair towards them. Now, the crucial thing to be aware of with London forces is that they are the weakest of intermolecular forces. Now, London forces are found between non-polar molecules, and London forces are all due to the redistribution of electrons. So in non-polar molecules, electrons can be unevenly spread, and this produces temporary instantaneous dipoles. So temporary because they're not permanent, instantaneous, they occur extremely quickly. Because we have dipoles, we mean that part of the molecule will be electron rich at one particular time, which means that it will be negatively charged, and the other side will be electron deficient, so that will be positively charged. But these are all relative, they're not really that either negative or positive. Now, this temporary instantaneous dipole can induce or cause another dipole to arise in a neighbouring particle, which means that you can have a weak attraction between the two particles, and that's what a London force really is. because this is a fairly complicated concept to understand, let's have a look at hydrogen, which is an example of a molecule that has London forces. So hydrogen is diatomic, remember, consists of 2 atoms, and because there's only 1 electron in the outer shell of hydrogen, you end up with this situation. Notice that, as always, for London forces, we need it to be a non-polar molecule, which it is. Now, just to write a quick description of what we can see in this hydrogen molecule, we can see that it consists of a positive nucleus, because remember, it contains a single proton surrounded by an electron cloud, and this electron cloud is able to change position. So each hydrogen molecule consists of a positive nuclei surrounded by an electron cloud. Now this electron cloud is able to change position. So that means that at any one snapshot in time, one part of the hydrogen molecule might have a slightly higher electron density and the other part might have a slightly lower electron density. And this is what induces the temporary dipole. So let's try and show this with a pictorial representation. Here's the nucleus of each of the hydrogen atoms which make up that hydrogen molecule. Because the left-hand atom has become electron rich, you can see it's a bit bigger, it has a delta negative charge. The right-hand atom has become slightly electron deficient, so it has a delta positive charge. How would this be attracted to a second hydrogen molecule? Well, in this case, the left-hand atom again is electron rich, so it's slightly negative. It's a bit bigger. The right-hand hydrogen is slightly positive. So we can see that we have opposite charges here, and therefore there will be an attraction. And this is what London forces are all about. So remember that hydrogen bonding is a type of intermolecular force, so it occurs between molecules, and in order for it to take place you need obviously hydrogen and a highly electronegative element, and we need to be really specific here. Those elements we're talking about are fluorine, nitrogen and oxygen. Hydrogen bonding needs one of these elements to be present. What does the term electronegative mean? Well, if an element is highly electronegative, the atom has a tendency to attract a shared pair of electrons towards itself. So it becomes electron rich. So really we're going to now write a nice little paragraph about what hydrogen bonding is. So I've effectively said it, but we're going to write it out nicely so you have good notes on the topic. So we're going to write a description of hydrogen bonding. So it occurs when hydrogen is bonded directly to a small, highly electronegative element. Remember that element has to be either nitrogen, oxygen or fluorine. We know that highly electronegative elements have a tendency to attract shared pairs of electrons. So let's write that now. The electron pair is drawn away from the hydrogen by the electronegative element. And what that means is that you leave behind a proton in the nucleus with no inner electrons because those electrons have been drawn away. The reason we say a proton in the nucleus, be clear, remember that hydrogen only has 1 electron and really 1 proton. You can check this in the periodic table. Remember, it has an atomic number of 1, which tells you that it has only 1 proton and 1 electron. So as that oxygen or nitrogen or indeed fluorine draws away that single electron, obviously all you're going to be left with is a single proton. What happens next is that proton attracts the non-bonding pair of electrons from the fluorine, nitrogen and oxygen, and this results in a much stronger dipole-dipole attraction.
So I'm going to show you a little picture to represent water's hydrogen bonding. So remember, the oxygen has drawn away the electrons from hydrogen, so it becomes slightly negative, because remember, electrons are negatively charged. That hydrogen is now deficient in electrons, so it's slightly positive, and therefore you end up with hydrogen bonding forming because opposites attract. So the slightly positive hydrogen is attracted to the slightly negative oxygen. And this hydrogen bonding explains why water's boiling point is so much higher than other molecules. So water's boiling point is obviously 100 degrees Celsius. If we take methane, CH4, has a ridiculously low boiling point of a minus 162 degrees Celsius. And the reason for this, the reason why water is a liquid at room temperature, whereas methane is obviously a gas, is due to the fact that hydrogen bonding in water is much stronger than the London forces found in methane.
Notice in endothermic reactions, heat energy is taken in and less energy is needed to make the bonds than break the bonds. An exothermic reaction now, you kind of use the exact opposite wording. So just learn the definition once and switch it around. So heat energy this time is given out. More energy is needed to make the bonds than break the bonds. If they ask you for examples, photosynthesis is a good example of an endothermic reaction. Reactions such as combustion and neutralization are both examples of exothermic reactions. You could be asked to draw an energy profile. I'm just going to point out the key things to notice. So you always write your reactants and products on horizontal lines. The reactants always come before the products. Now notice with an exothermic reaction, the change in energy is negative. With endothermic reactions, the change in energy is positive. The difference between the reactant energy level and the top of that peak is known as the activation energy. Notice that it differs for endothermic and exothermic reactions. If they ask you to define activation energy, is that it's the minimum amount of energy required for a reaction to occur. And then how do catalysts work? Well, you want to link your explanation with activation energy, and you just say that first of all they speed up the rate of reaction without being used up. And how do they do that? By providing an alternative reaction pathway with lower activation energy. And if you're asked to label on these sorts of diagrams how a catalyst works, you just want to draw a new peak slightly lower, because by doing that you've lowered the activation energy. So now we're going to go through some example questions. So a student uses this apparatus to measure the temperature change when lithium iodide dissolves in water. He measures the steady temperature of the water before adding the lithium iodide. He then adds the lithium iodide, stirs the mixture until all the solid dissolves, and records the maximum temperature reached. The diagram shows the thermometer readings before and after dissolving the lithium oxide. Use the readings to complete the table. Temperature in degrees Celsius after adding lithium iodide. So make sure you're reading it nice and accurately here. It's 22.3 degrees. Temperature in degrees Celsius before adding lithium iodide, 16.7 degrees. Your temperature change therefore is the difference in those numbers, so it's 5.6 degrees. In a second experiment using the same mass of water, the student records a temperature increase of 4.9 degrees Celsius. Use this expression to calculate the heat energy change in this experiment. So our mass of water is 100 grams. You need to multiply that by the specific heat capacity times the temperature change to get 2058 joules. In this experiment, 6.3 grams of lithium iodide were used to calculate the amount in moles of lithium iodide in 6.3 grams. You need this formula triangle. It states that mass is number of moles times MR. We're after the number of moles, so we do mass divided by MR. So 6.3 divided by 134, as we're given that value in the question, to get a value which is 0.047. C. In a third experiment, the student obtains these results. Heat energy change in joules, 2,400. Amount of lithium iodide in mole, 0.048. Calculate the molar enthalpy change in kJ per mole. So let's write out what we're doing. Molar enthalpy change. And even if you don't know the equation, hopefully the fact that the units are these helps you see that you need your energy on the top, and then you need to divide it by the number of moles underneath. Notice the difference in the units, kJ and joules, so you need to divide this number by 1000 to get 2.4. The number of moles stays the same to get a value which is 50. The temperature change in this experiment shows that dissolving lithium iodide in the water to form lithium iodide solution is an exothermic process. Complete the energy level diagram to show the position of the lithium iodide solution. Label the diagram to show delta H, the molar enthalpy change. So we know it's an exothermic reaction, which means our products will be at a lower energy than our reactants. Doesn't really matter where you draw it. So there are your products drawn to the right. Label it lithium iodide solution, and then don't forget to put your delta H on. A 25 centimeters cubed sample of 2 molar hydrochloric acid was mixed with 50 centimeters cubed of 1 mole solution of sodium hydroxide. Both solutions were initially at 18 degrees Celsius. After mixing, the final temperature was found to be 26.5. Use this information to calculate a value for the standard enthalpy change for the following reaction. Assume that the density of the final solution is this, and that its specific heat capacity is the same as that of water. So to begin with, Q equals mc delta T. Our mass, remember, is the mass of solution, so add the two numbers together. 50 plus 25 is 75. We've been told the specific heat capacity is the same with water, so we can just use 4.18. The temperature change is the difference between 18 degrees and 26.5, which is 8.5. Pop that into your calculator. So there's our Q value. Now we need to find the moles of hydrochloric acid used, which we find by doing volume times concentration. The volume we added was 25 centimeters cubed. Remember, we need that in decimeters cubed when we use this equation, so we divide by 1000. The concentration we were told was 2. So there's the number of moles of hydrochloric acid. And then finally, our enthalpy change is given by delta H equals Q over N. Q we just found. Be careful with your units, you need that to be in kJ, so we need to divide that by 1000 and then divide it by the number of moles we just calculated. So our final answer here is minus 53.3 kJ per mole. Remember, it's minus because the temperature of the reaction went up, telling us that it's an exothermic. From an experimental point of view, remember, in these type of reactions which are exothermic, you see an increase in temperature. However, to gain a best estimate for the temperature immediately after mixing, you'll actually find that it's higher than what your thermometer tells you, so you need to extrapolate backwards in order to gain a truer reading. The enthalpy change for a chemical reaction is the same whatever route is taken from reactants to products. People don't like this topic. I promise by the end of this video you will feel so much happier about it. And the whole thing is really underpinned by this statement. The enthalpy change is the same whatever route is taken from reactants to products. And so I'm going to show you an example now. So let's take this example. What Hess's law means is that if you have a reaction such as this one going from A to B, doing that reaction one step will have the same enthalpy change as going via an intermediate C. So here's the enthalpy change going from A to B. So we're going to call that delta H1. Delta H2 is going from A to C, and then going from C to B is delta H3. And so according to Hess's law, delta H1 is the same as doing delta H2 plus delta H3. So to reiterate, the enthalpy change from A to B is exactly the same as if you went via an intermediate C. Now in general, there are two types of Hess's law questions. Number one, using enthalpy changes of formation, and number two, using enthalpy changes of combustion. So here are the two types of question, and we're going to focus in first of all on enthalpy changes of formation. So as always, we need to start with a definition which needs learning off by heart. So the enthalpy of formation is the enthalpy change when 1 mole of a compound is formed from its constituent elements under standard conditions, that's key, with all reactants and products being in their standard states, again key. So we're going to use the following reaction as an example. So it's iron oxide, which is a solid, reacting with calcium, again a solid, forming iron by itself and calcium oxide. That's nicely balanced. The first thing we do is reconsider our definition of enthalpy of formation. So it's the enthalpy change when 1 mole of a compound is formed from its constituent elements under standard conditions. So because it's a formation question, it therefore makes sense to have this original equation at the top with the constituent elements underneath. And that's exactly what I'm going to do here. So here's one of the elements, iron, followed by calcium, and then followed by oxygen. Notice that oxygen, we're looking at our reactants and products being in their standard states. Oxygen, remember, is a diatomic molecule, it's gaseous, and that's why we've got that little G there. The other thing to be aware of, because we're looking at enthalpy of formation, it's forming those reactants and products from the constituent elements, hence why my arrows are pointing upwards. Now for ease, I'm going to label these reaction pathways A, B and C. And so in terms of our route that we're going to take, remember, going from the reactants to the products, so effectively pathway A, is the same as going this way. Because we're going against the arrowhead is minus B, but we're going towards that arrowhead for C, so it's plus C. Which, remember, according to maths, can be written like this. And now we just need to fill in some values using the enthalpies which will be given in the question. Notice that by definition, the enthalpy change of formation of elements is always 0, as you can see for the calcium and iron here. So in this particular question, we're interested in calculating the enthalpy change from the reactants to the products. So remember, that's A equals C minus B. So looking at C here, we've got 2 lots of iron plus 3 lots of calcium oxide. So we'll do a mini calculation here. So that's 2 times 0 plus 3 times minus 635. Remember, these numbers have come from here. Pop that into your calculator and you'll get a value which is minus 1905. Looking at B over here, we're just going to take the number for iron oxide, which is minus 824, and then we're going to add 3 lots of the enthalpy of formation of calcium, which is 0. And then to finish this off, we're doing C minus B, so that was minus 1905, minus, careful with your negatives, so minus 824, to get a final value which is minus 1081 kilojoules per mole. And that's your enthalpy of formation example. Now we're going to consider enthalpy changes of combustion. Our definition here is the enthalpy change of combustion is the enthalpy change when 1 mole of a substance is completely burnt in oxygen under standard conditions. So looking at that more closely, we're completely burning. That means, remember, complete combustion means the products here are carbon dioxide and water as opposed to carbon or carbon monoxide. Again, we need standard conditions. So this time, the bottom of our triangle needs to have the products of combustion. So I'm going to write here, always appears. Remember, that's our working out triangle. So always appears at the bottom of the triangle. And because combustion produces that carbon dioxide and water, our arrows will point downwards this time. So in this example, we're going to be looking at the formation of butane according to this equation. Look, there are all our elements in their standard states as usual. Because it's complete combustion, we know that they're going to be producing carbon dioxide and water. Our arrows point downwards. Let's label the 3 arrows A, B and C again. In order to do A, follow the arrows round, is going to be B minus C because we're going against that arrowhead. So we'll need the enthalpy of combustion for these elements and compounds. So starting with B, we've got 4 lots of carbon and 5 lots of the hydrogen. So that equals minus 3006. Let's look at the side for C. It's just this value here, which is the enthalpy of combustion of butane, minus 2877. Pop that into your calculator and you'll get a final answer, which is minus 129 kJ per mole. Vanadium is an important metal. Ferrovanadium, an alloy of iron and vanadium, is used to make a strong type of vanadium steel. Pure vanadium is used in nuclear reactors. The table shows some standard enthalpy of formation data. In the oldest method of extraction of vanadium, V2O5 is reacted with calcium at high temperature. Use data from the table in the equation to calculate the standard enthalpy change of this reaction. State the type of reaction that V2O5 has undergone. Suggest one major reason why this method of extracting vanadium is expensive, other than the cost of heating the reaction mixture. So lots to do here. So let's start by writing out that equation. Because it's an enthalpy of formation reaction, remember we want to put our constituent elements at the bottom with the arrows pointing up. That's a fail-safe method. Then we list calcium, vanadium and oxygen. So we're after X. In terms of the standard enthalpy of formation of calcium, remember for any element by definition that's 0, so we just take the value given above for the vanadium oxide, so that's minus 1560. And then on the right hand side we're just interested in the calcium oxide, so we need to acknowledge that large 5, so it's 5 times minus 635. Then it doesn't matter what route we take, but we're after X, so we're going against that arrowhead, so we need to do minus 1560 and then follow that round in the same direction. So it becomes X equals minus 1560 plus 5 times minus 635. So the answer here is minus 1615 kJ per mole. Then if we have a look at what type of reaction that vanadium oxide has gone through, well, it's lost oxygen, so it's a reduction reaction. And then lastly, the major cost. As you look at the inputs and the reactants, look, we've got calcium. Calcium is a pretty reactive metal, which means we need to use electrolysis to extract it, because it's more reactive than carbon, so you can't use reduction with coke. And remember, high electricity costs are a big no-no. Methane reacts violently with fluorine according to the equation. Some mean bond enthalpies are given. The student suggested that one reason for the high reactivity of fluorine is a weak F to F bond. Is the student correct? Just try to answer the calculation using these data. So we'll start with that large equation, which we know is an enthalpy change of minus 1904. So in order to get this value up here, they must have done bonds broken minus bonds formed. So let's do that calculation here. Bonds broken. If you imagine the CH4 looks like this, it's just methane. You can see there that we've got 4 lots of that CH bond. So we're going to do 4 times the CH bond, which we know from the table is 412. So I'm going to multiply that by 4 to get 1648. And then we need 4 lots of the FF bond, which we don't know. And then what about bonds formed? Well, we've got 4 lots of the CF bond, which is 4 lots of 484, 1936, and then 4 lots of the HF bond. So that's 4 times 562. So if we add those up, you get a bonds formed value of 4184. So pop that into an equation. So we know that our final answer is minus 1904, which must have been due to the bonds broken minus the bonds formed. So once you've worked all of that out, you'll get 4x equals 632, which means each FF bond, you need to divide that number by 4, is 158 kJ. And if we go back to our question, is the student correct? Is the fluorine highly reactive because it has a weak FF bond? Well, we need to work out, does it have a weak FF bond? Well, look at the value. It's 158 versus 412, 484, 562. So yeah, it's significantly weaker. Collision theory states that for a reaction to occur, particles must collide with enough energy to overcome the activation energy and in the correct orientation. Remember, the activation energy is the minimum amount of energy required for a reaction to occur. We're now going to look at the Maxwell-Boltzmann distribution. In terms of your Y and X labels, X will be energy and Y is the number of molecules with a particular energy. So the Maxwell-Boltzmann curves have a very particular shape, one which looks like this. And it's important that you can recognize what different parts of the graph are telling you about the particles or molecules' energy. So down here, because E is very low, we can say that some particles have very low energy, and the reason for that is the collisions that occur cause these molecules to slow down. Be aware that there are no particles with zero energy. The peak of a Maxwell-Boltzmann distribution curve is representative of the most probable energy that the particles have. It's important that you can identify that in the exam. Point C on the graph is the mean energy. This is higher in value compared with the most probable energy, and the reason for that is there's no upper limit to the energy a particle can have. We're going to label the activation energy EA. So to remind you, this is the minimum amount of energy the particles require for a reaction to take place. So that means that anywhere to the right, it means that the particles that exist here have the sufficient energy required to react when they collide. Notice that the curve never meets the x-axis again, as there is no maximum energy a particle can have. So to reiterate, down here, there are no particles with zero energy. The peak represents the most probable energy. C is the mean energy, and this is higher than the most probable energy. You'll often find the activation energy marked on, and that means that any particle existing to the right, so in this part of the curve, must have enough energy to react when the particles collide. D represents the fact that the curve never meets the x-axis, as there is no maximum energy a particle can have. Now we need to consider the effect of temperature on the Maxwell-Boltzmann distribution. So we're going to start with our original curve. We're going to call this T0 because that's our original temperature. What happens now if we were to lower the temperature? And then what happens if we were to increase the temperature? So I'm going to call this one T1 and T2. So let's describe and explain what's happening at T1. So T1, that's when the temperature is lower than the original temperature. We still need to show that activation energy, so I'm using my dotted red line to represent the minimum amount of energy required for the reaction to occur. So at the lower temperature T1, what can we see about the graph? We can see that the peak of the curve is higher and to the left of the original curve. What about our pink line T2? Remember, that's the higher temperature. Well, to describe the graph, we can see that the peak is lower and to the right. So let's really try and explain, particularly with that higher temperature, what's going on. I'm hoping you can see by just filling in this portion of the graph under the curves, you can see that when you increase the temperature, much more particles have energy greater or equal to the activation energy, and this means that there are more successful collisions in a given time, meaning that the rate of reaction increases with higher temperature. And they do love to ask you this in the exam. So our explanation, so at higher temperatures we have higher rates of reaction. What is our explanation for this? Many more molecules or particles have energy equal to or greater than the activation energy. So more successful collisions occur per unit time. So just be prepared to draw these graphs. Here's your original temperature. As I said, if the temperature is lowered, you'd expect that peak to be higher and to the left, meaning fewer molecules have energy equal to or greater than the activation energy. By increasing the temperature, what happens is many more molecules have sufficient energy to overcome the activation energy, and you'll see that peak displaced to the right and being slightly lower. The total area of each of these curves, remember, must equal the same because the number of particles doesn't change. I don't want to talk about this too much because after all it's a recap of GCSE and IGCSE chemistry knowledge. We've already discussed, however, the effect of temperature on the rate of a chemical reaction and how we can use the Maxwell distribution curves to represent this. So we've talked about how increasing the temperature means that the particles have more kinetic energy and therefore collisions are more frequent per unit time, and you're more likely to have particles with energy equal to or greater than the activation energy. Increasing the concentration merely means having more particles in the same volume, so the successful collisions are more frequent per unit time. Increasing the surface area through making a solid a powder, for example, this will mean that more collisions occur per unit time, increasing the rate. Increasing the pressure means that there are more gas particles in the same volume, so successful collisions are more frequent. We'll now have a quick look at the effect of adding a catalyst. So here's our Maxwell-Boltzmann distribution again. We have the number of molecules on the y-axis, the energy here. Now what adding a catalyst does is it reduces the activation energy, hence why you can see that line representing the activation energy has moved to the left. And what that means is that you have many more molecules with the energy which is either equal to or greater than the activation energy. Look, the area of this part of the curve has increased. The shape of the curve, however, remains the same because after all, we haven't altered the temperature. And here's your simple definition of a catalyst. It's a substance which increases the rate of a chemical reaction without being chemically used up or changed. This question is about the Maxwell-Boltzmann distribution of molecular energies in a sample of gas shown in the figure below. Which letter best represents the mean energy of the molecules? Remember, the mean energy occurs slightly to the right of the peak, so the answer here is C. What does the area under the curve represent? It's the total number of particles, so you do really need to know what the various parts of the graph are telling you. The answer here is B. The diagram shows below a Maxwell-Boltzmann distribution for a sample of gas at fixed temperature. EA is the activation energy. On this diagram, sketch the distribution for the sample of gas at a higher temperature. So what did we say? We said that the peak would occur to the right and slightly lower. They'll be looking for you to start that curve at the origin, which I've done. So yeah, I'm happy with that. With reference to the Maxwell-Boltzmann distribution, explain why an increase in temperature increases the rate of a chemical reaction. So by increasing the temperature, you increase the number of molecules with energy greater or equal to the activation energy, meaning that there are more successful collisions per unit time. chemical equilibria, we'll do an IGCSE, GCSE recap, and then we'll get really into the nitty-gritty to do with case C. So remember, first of all, that this arrow represents that the reaction is reversible, which means it occurs in both a forward and reverse direction. In reversible reactions, equilibrium, the forward and reverse reactions proceed at equal rates. The concentrations of reactants and products remain constant. This does not mean they're necessarily equal. The system must be closed, and that means that neither the reactants or products can escape. And that is your definition, really, of a dynamic equilibrium. Remember, adding a catalyst doesn't affect the position of equilibrium. It just means the equilibrium is established faster. Don't forget Le Chatelier's principle, which states that if a change is made to a system equilibrium, the position of equilibrium moves in the direction that opposes the change. And that statement there is incredibly important if we consider the effect of temperature and pressure on the position of equilibrium and fundamentally the yield of either the products or reactants. So if we use this reaction here, which is ethanol reacting with ethanoic acid in a reversible reaction to produce the ester ethyl ethanoate plus water. Now at the beginning of the reaction, clearly you'll have the highest concentration of the reactants of both the ethanol and the ethanoic acid. So their concentrations up here will be high. The concentration of the products will be low because the reaction hasn't started yet. Then as the reaction takes place, reactants react, therefore their concentration decreases, and as their concentration decreases, the concentration of products increases, and then you'll reach a point whereby the concentration of reactants and products remains constant. You'll be familiar with the Haber process, I'm sure. This is the manufacture of ammonia, NH3, and it involves nitrogen gas reacting with hydrogen to produce the ammonia. Make sure that that's balanced, and delta H here is minus 92 kJ per mole. And that's incredibly important, remember, because that tells us that the forward reaction is exothermic, which means the reaction gets hot. So in order to increase the yield of ammonia, that's to increase the yield of product, what do we want to do to the temperature? We want to decrease the temperature. And the reason for that is, according to Le Chatelier's principle, any change you make to the reaction conditions, the position of equilibrium shifts to oppose the change. So by decreasing the temperature, it will favour the direction which increases the temperature. So in this case, the exothermic forward reaction, because after all I said that releases heat energy, the reaction vessel gets hot. So our reason for that is because the forward reaction is exothermic. Sometimes they ask you about compromise conditions. Remember, by decreasing the temperature, despite the fact you're increasing the yield of ammonia, decreasing the temperature has the knock-on effect of lowering the rate of reaction because it means that particles have less kinetic energy. So in the end, we use a compromise temperature of 670 Kelvin because that gives a sufficiently high yield as well as a sufficiently high rate of reaction. Now let's consider the effect of pressure. So again, to increase the yield of ammonia, this is when you need to count the number of moles of gas on each side of the equation. So we look at the large numbers. There's 4 moles on this side versus 2 moles on this side. So to increase the yield of ammonia, we want to increase the pressure. Again, why? Because according to Le Chatelier's principle, the position of equilibrium shifts to oppose the change we've made. So if we've chosen to increase the pressure, the position of equilibrium will shift in favour of the forward reaction because that has fewer moles of gas on the right-hand side. So there are fewer moles of gas on the right-hand side. So the position of equilibrium shifts to the right. Let's consider collision theory and rates of reaction. Well, actually, we don't have the same issue here with an increase in pressure compared with the decrease in temperature. Why? Because increasing the pressure is good because it increases the rate of reaction. So we have no compromise here. But the problem with high pressures is they're extremely expensive and also dangerous because you have to reinforce all the reaction chambers. So instead, we use a compromise pressure of 200 atmospheres, which gives a good balance of high yield, high rates of reaction, but reduces costs and danger. Last up, we have an ion catalyst, which is added. As I've already said, this has the effect of increasing the rate of reaction. It does not affect the position of equilibrium though. It just means that equilibrium is achieved faster. This is a whistle-stop tour of Le Chatelier's principle. Do watch my IGCSE and GCSE videos on the same topic if you're less sure and you want to take it slightly more slowly, because we're now ready to have a look at Kc. Now, the equilibrium constant is concerned with concentration. It's really key, you know that. So we're going to be very interested in concentration throughout this video. Kp is a different expression and it's used for when we're dealing with gases and pressures, not concentration. Initially, we're going to determine an expression for Kc. You need to follow these rules. Kc is the concentration of products divided by the concentration of reactants, all raised to the power of the molar coefficient. I promise that's easier than it sounds. So to help us with that, let's take a reversible reaction where hydrogen gas is reacting with iodine gas. Notice that everything needs to be in the same state. You need a homogeneous reaction for this. So they're all in gaseous state, and because it's to do with equilibrium, we must have that reversible reaction. So let's determine an expression for Kc for this particular reaction. Remember, we use square brackets like this to represent concentration. So let's reread our definition. It's the concentration of products. So there's our product in that concentration bracket, divided by the concentration of reactants. So our reactants are both hydrogen and iodine, raised to the power of the coefficients. So let's check the coefficients. 1 and 1, so we don't change this value. The crucial thing here is the 2, and we raise it. So we make a power out of it, which is why this is the final answer. So this is your expression for Kc. The next question we need to ask ourselves is, does Kc have a unit? Because we're obsessed with units in chemistry. And unfortunately, you have to work this out individually for each reaction because it varies. So how to find the unit? Substitute in the concentration unit, which is mol dm to the minus 3, for each reactant and product. So let's take a different reversible reaction. We've got nitrogen and hydrogen reacting to produce ammonia, which hopefully you recognise is the Haber process. Make sure it's balanced. Let's write an expression for Kc. So we want the concentration of products, so that's the NH3 raised to the power of the coefficient, so that's 2, divided by the concentration of the reactants. Again, raise any coefficients as a power. So there's the expression for Kc. Let's work out the units now. So we know we've got concentration unit mol dm to the minus 3, and we've got that little power, so it's to the 2, divided by mol dm to the minus 3 for the nitrogen, mol dm to the minus 3 raised to the power of 3 for the hydrogen. Now we need to cancel this down, so we managed to get rid of this one. This turns into a 2, so let's simplify. So you need to be quite good with your indices here, because it's effectively upside down. We put that little minus there to represent that. And then what do you do with these powers? Well, you have to multiply them. So this requires knowledge of GCSE and IGCSE maths. And then if you're being really good, you just rearrange that a little bit, because the convention is to have the positive number first. but don't stress too much if you don't want to. So we've looked at writing an expression for Kc, working out the units of Kc. Now we're going to actually calculate a value for Kc. So in order to calculate Kc, you want to find the equilibrium concentrations of each reactant and product and substitute these values into your Kc expression. So here we have the Haber process again, and we've been told that the equilibrium concentrations in the manufacture of ammonia are the following: so nitrogen 18.6 mole dm to the minus 3, hydrogen 0.9 and ammonia 1.5. So let's write our expression for Kc again. It's good practice. So there's the concentration of ammonia, concentration of nitrogen, and then hydrogen. So substitute in our values, so we know we've got to do 1.5 squared for ammonia divided by 18.6 for nitrogen multiplied by 0.9 for hydrogen raised to the power of 3 to get a final value for Kc, which is 0.16, and then the same units we calculated before. So that looks like this. Sometimes you're not given equilibrium concentration, sometimes you're just given starting concentrations. You need to work out the equilibrium concentration by doing the following. You want to use the molar ratio to work out the ratio of each component when equilibrium has been reached. And so if all the volumes are the same or the volumes are not given in the question, then you can just substitute the number of moles you've been given into your Kc because the volumes all cancel out anyway. And I'm writing a little note here as to why you can do that, because the volumes cancel out. If volumes are given in the question, you need to calculate concentration as usual. So remember, in order to do that, you use this formula triangle, NCV. So to work out concentration, you do number of moles divided by volume. Remember that volume needs to be in decimeters cubed. The next thing we want to consider is, what does the value of Kc tell us? Well, if Kc equals 1, then it means that the position of equilibrium lies in the middle. If Kc is less than 1, then the position of equilibrium lies towards the reactants. And then, as you might expect, if Kc is greater than 1, then the position of equilibrium lies towards the products. Can we actually alter the Kc value? Well, the first thing to point out is that changing the concentration or pressure has absolutely no effect on Kc. Really important that you're aware of that. And the reason for that is because when you make those changes to the system counteracts the change according to Le Chatelier's principle. So if you increase the concentration of products, the position of equilibrium will shift towards the reactants. And what this does is cause a rebalance of your equation for Kc, meaning that its value does not change. However, if you change the temperature, Kc is altered. So the answer here is yes, if you change the temperature. So please, please, please be aware that concentration and pressure changes have no effect on Kc, but changing the temperature does have an effect. And why is that? When you change the temperature, the system acts to counteract the change in temperature. And I'm going to use a quick example to show you how this works. So going back to our trusty old Haber process again. The forward reaction here is exothermic, which remember means it gets hot. So we favour the forward reaction by lowering the temperature. So you need to check out my other video if you're not happy about that. So we'll grab that Kc expression for this again. So let's consider if we increase the temperature. Remember, in this particular reaction, because the forward reaction is exothermic, it means that if we increase the temperature, the position of equilibrium will shift to the left. So what does that do? Well, it increases the concentration of our reactants, and therefore this number here gets bigger, meaning that Kc decreases. So you do have to juggle this. If we consider if we decrease the temperature, this time the position of equilibrium shifts to the opposite, so to the right hand side. So therefore we make more ammonia. So the ammonia concentration increases, which means this number gets bigger, and therefore Kc increases in value. One last thing is to point out that adding a catalyst has no effect on Kc value. And that's because it speeds up the forward and reverse reactions equally. Now, in order to calculate Kc, you do need to be able to calculate the equilibrium amounts, so the amount in moles of reactants and products, given the initial amounts of reactants, and honestly the best way to do that is using what I call a rice table. So I'm going to show you how to do that here. So in this question, 1.5 mole of NO are mixed with 1 mole of chlorine, and the mixture is left to reach equilibrium at a given temperature. The equilibrium mixture contains 0.35 moles of NaCl. Calculate the amount in moles of NO and Cl2 in the equilibrium mixture. So your first step with this is to write out your balanced symbol equation. And now we use rice to help us work methodically through this. So R stands for your reaction equation, so that's what I'm going to label that as being. Then we have ICE. Underneath, I'm just going to list what RICE stands for. So R is your reaction equation. As you can see, I've already written that in the table above. I stands for your initial moles, so what you start with. C stands for your change in moles. And E stands for your number of moles at equilibrium, so your equilibrium moles. And now all you have to do is start working your way through the wording of the question to fill in the table. So we know we start with 1.5 moles of NO. Chlorine we start with 1 mole. And because the reaction hasn't gotten underway yet, we start with 0 moles of our product. What else do we know from the question? The equilibrium mixture contains 0.35 moles of NaCl. So it's now straightforward for us to work out what happened. What's our change in moles? Well, from our initial to our equilibrium moles, we have gained 0.35 moles. And that's so helpful because now we can work out how many moles we have lost of the NO and the Cl2. Just check the mole connection. Because remember, when we do mole calculations, we're able to carry across numbers. So if we have gained this much product, it means that we have lost the same amount of reactants. So that's minus 0.35 moles. So 1.5 minus 0.35 becomes 1.15. And then just be careful here with the mole connection. It's 2 to 1. So in terms of how much we've lost here, we just need to make sure we halve that number. So it's minus 0.175 moles. And therefore, to work out equilibrium moles of chlorine, just do 1 minus that number you just found. So that's 0.825 moles. So you've done all the hard work. We're now going to use this question to actually find a value of Kc together with the units. So here a mixture of carbon monoxide and hydrogen reached equilibrium in a container of volume 250 centimeters cubed at temperature T. At equilibrium, the mixture contained 0.34 moles of carbon monoxide, 0.19 moles of hydrogen, and 0.061 moles of methanol. Find Kc and give the units. Right, they have told us the equilibrium moles, so we don't need to use the rice table here because they've done that for us. We're going to start by writing our expression for Kc. So remember, that is the concentration of our product, which is methanol, divided by the concentration of the reactants, making sure you raise any of them to the power. So that 2 came from here. After all, we need the concentration, so we're going to use this formula triangle in order to find the concentration. So our concentration of methanol, using that formula triangle, is the number of moles, 0.0610, divided by the volume, which we were told was 250 centimeters cubed. Just be careful, that needs to be in decimeters cubed, which is why I'm dividing by 1,000. Let's do the concentration of carbon monoxide. Very similar. There we are, dividing it by its volume again. And then finally the concentration of hydrogen, 0.19 moles. Okay, perfect. So we'll steal that expression. Let's substitute in all our values. Remembering to square the concentration of hydrogen based on the Kc expression we worked out. So Kc equals 0.311. And then lastly, the units. Again, we're using the expression of Kc, substitute in our concentration units, cancel them down. So our final answer is 0.311 moles to the -2 dm to the 6. When a 0.218 mole sample of hydrogen iodide was heated in a flask of volume V, the following equilibrium was established. The equilibrium mixture was found to contain. Calculate the number of moles of iodine and the number of moles of hydrogen iodide in the equilibrium mixture. Draw out a Rice table then. So here's our R. So we know we started with 0.218 moles of hydrogen iodide. By definition, we won't have any of our product at the beginning. The mixture was found at equilibrium to contain 0.023 moles of hydrogen, which means we've gained 0.023. Check the mole connection, it's 1-to-1, so again, we can write the same for the iodine. And now, what about the change in moles of our reactant? Just check the mole connection, it's 2-to-1, so we need to double that number here. Obviously, the reactant gets used up, so that's why we're minusing that number. So that's 0.172. So we're ready to just input those numbers here. So calculate the number of moles of iodine at equilibrium. We can see it's 0.023 moles. The number of moles of hydrogen iodide is 0.172 moles. Write an expression for Kc. So there's our concentration of our products multiplied together, divided by the concentration of reactants raised to the power. State why the volume of the flask need not be known when calculating a value for Kc. All you have to write here is because the volume cancels in the Kc expression. And you can see that here. Calculate the value of Kc at 700 Kelvin. We'll steal that expression. You don't need to find the concentration, you can just use the number of moles at equilibrium here. Substitute those in. And then calculate the value of Kc at 700 Kelvin for the equilibrium. This equation is the opposite way round. You could plug all your numbers in. You could write a new Kc expression, plug your numbers in, but honestly the easiest thing to do here is just do 1 over your answer from before. It's the same, to get 55.9. When we're looking at oxidation states, it all relies on us understanding what oxidation and reduction are. So remember, oil rig will help you with this. So oxidation is the loss of electrons, whereas reduction is the gain of electrons. And that is key. However, at this high level, it's not always easy to see how electrons have been transferred in redox processes. And remember, redox processes are ones where oxidation and reduction occur at the same time. And therefore oxidation states are a made-up tool made up by us in order to help us identify which species have been oxidized and which have been reduced. And basically there's a whole set of rules you need to follow, and if you follow those rules you'll be able to first of all work out the various oxidation states, and secondly work out what has been oxidized and what has been reduced. So to put that into words, oxidation states are a useful tool for allowing us to identify which species has been oxidized and which has been reduced. So here are oxidation state rules, or you could have said our oxidation number rules. It means the same thing. And our first rule you have to learn is that elements which are not combined with other elements have an oxidation state of 0. So let's look at some examples. Oxygen, phosphorus, sulfur as elements by themselves have an oxidation state of 0. For number 2, the oxidation state or oxidation number of any uncombined ion is the same as its charge. So taking sodium ion for example, its oxidation state will be +1. Calcium, its oxidation state will be +2. So its oxidation state or number is the same as the charge on its ion. Rule 3, the sum of all the oxidation numbers in a molecule is 0. Such as water, carbon dioxide, hydrogen chloride, etc. So the sum of all the oxidation numbers, so that means the individual oxidation numbers here. So the oxidation number of hydrogen and the oxidation number of oxygen, 2 lots of hydrogen plus the oxidation number for oxygen will equal 0. Carbon's oxidation number plus 2 lots of oxygen's oxidation number will also be 0, and so on. NB, linked to this point, we need to consider ions, and we're looking at more complicated ions, so ones which contain 2 or more elements. So I'm going to call that, in a complicated ion, the sum of oxidation numbers is equal to the charge of the ion. So taking the ion SO42-, so the sulfate ion, what that means is if you add the oxidation number of sulfur to 4 lots of oxygen, you'll still have a net charge of 2-. For the nitrate ion, if you add the oxidation number for nitrogen to 3 lots of oxygen, you'll have a net charge of 1-. Next up, a couple of elements which you just have to learn the numbers for. So hydrogen, try and remember that that always has an oxidation number or state of +1. The exception is hydrogen combined as a metal hydride. And here it has an oxidation number of -1. So you must learn that exception. Fluorine is the second element you need to know the oxidation number off by heart, and its oxidation number is always -1. Oxygen now, this is slightly more complicated. It usually has an oxidation number of -2. However, there are a few exceptions. So firstly, in peroxides it has an oxidation number of -1 instead of -2. And secondly, when it combines with fluorine, it has an oxidation number of +1. In order for this to make more sense, let's write the peroxide formula, and that's H2O2. So hydrogen will have an oxidation state of +1, and oxygen in this case, according to our exception, will be -1. By the way guys, some teachers might have taught you this in terms of which elements are more electronegative. So you treat covalent compounds as ionic compounds. Obviously that method works too, but this for me is the most straightforward thing to do, because you just have to learn a load of rules and it will make sure you get the answer right every single time. Anyway, rule 7, looking at chlorine now as the element. Remember that it always has an oxidation number of -1. There is an exception here. So when it's combined with fluorine, it switches the sign of its oxidation number to being positive, and the same is true for oxygen. Now, the number it turns into will very much depend on the compound you find it in, and we will look at some examples to make sure that actually makes sense for you guys. And then the last rule, which is fairly straightforward, and hopefully you remember this from GCSE and IGCSE, for groups 1 to 3, the oxidation number is the same as the group number. E.g., sodium is in group 1, so its oxidation number is +1. We're going to look at ammonia. Now, according to rule 3, the sum of all oxidation numbers in a molecule is 0. We know that overall this charge on the ammonia will be 0. And that's helpful because now we need to work out the various oxidation numbers of both nitrogen and hydrogen. So according to rule 4, we know that hydrogen has an oxidation state of +1. We know that there is no overall charge, so because we have 3 hydrogens, we have a +3 charge. So what must the oxidation number of nitrogen be? Well, it must be -3. Guys, there's just a quick correction I want to make, which is along rule 6, where I said that when oxygen is combined with fluorine, that it has a +1 oxidation state. Indeed, that is correct sometimes, but it can actually be variable depending on the compound it's in. So just if you change your notes and just write positive here, that will make it much better. And it's very similar to what we wrote for 7, so sorry about that. Following on from our oxidation state rules, we need to be able to look at redox reactions and look at the equations and decide what has been oxidized and what has been reduced. So we're going to have our rules side by side so we can refer to them, because we'll need to know what the various oxidation states are in order to do these questions. Looking at our first equation, therefore, we've got sodium, which is a solid, oxygen, which is a gas, forming sodium oxide. And we need to compare the various oxidation states of the elements on both sides of the arrow. So starting with sodium, well, according to rule 1, elements not combined with other elements have an oxidation state of 0. So here we know sodium has an oxidation state of 0. Looking at it in sodium oxide, so according to rule 8, for groups 1, 2 and 3, the oxidation number is the same as the group number. So sodium is in group 1, which is why its oxidation number here is +1. Looking at oxygen now oxygen is an element not combined with any other elements. According to rule 1, its oxidation state is therefore 0. And then combined with sodium, so as sodium oxide, we know according to rule 6 that it has an oxidation number of -2. And do check that the overall net charge is 0 on these things to make sure you're doing it right. And now let's just have a look at what's happened with the numbers. So sodium has gone from 0 to +1, which means that it has lost electrons in order to become positive. And because it's lost electrons, according to oil rig, we know that sodium has therefore been oxidized. Oxygen has gone from 0 to -2, which means it's gained electrons, so it has been reduced. And then depending on how they ask the question, you can add a couple more statements. So although sodium has been oxidized, it means it has automatically acted as a reducing agent because it has caused oxygen to be reduced. So you can write sodium has been oxidized, and you can also write sodium acts as a reducing agent. Concurrently, if oxygen has been reduced, it means it's automatically acted as an oxidizing agent. Let's look at a second example where copper oxide reacts with hydrogen to form copper plus water. So starting with oxygen, let's work out its changes in oxidation state. According to rule 6, it has an oxidation state of -2. There are no exceptions here, so we're going to put a -2 here. And looking on the right hand side, again, oxygen will have an oxidation number of -2. So here nothing's happened to it. It hasn't been oxidized or reduced because its oxidation state has remained the same. Copper now, well, we know the net charge of copper oxide is 0, so by definition copper must therefore have an oxidation state of +2. And then on the right hand side, it exists as an uncombined element. According to rule 1, its oxidation state must therefore be 0. Hydrogen now, hydrogen exists as an uncombined element on the left hand side. Its oxidation number is therefore 0. On the right hand side, it exists in water. The net charge must be 0. So that means that each hydrogen has an oxidation number of +1. And now we can work out what has been oxidized and what has been reduced. So copper has gone from +2 to 0, which means it has gained electrons in order to become effectively more negative. So copper has been reduced. And we might as well write the matching statement here, which is that it acts as an oxidizing agent. Looking at hydrogen now, hydrogen's gone from 0 to +1. In order to become positive, it must have lost electrons. According to oil rig, it's therefore been oxidized. And automatically acts as a reducing agent. Let's do a third example now. So lead oxide plus hydrogen forms lead plus water. So starting with oxygen, we know it has an oxidation number of -2. It's found in water. Now again, it has an oxidation number of -2. Lead now, we know that lead oxide must have a 0 net charge, which is why lead is +2. Lead on the right hand side exists by itself as an uncombined element, which is why its oxidation state is 0. Lastly, hydrogen. Hydrogen on the left hand side is an uncombined element, its oxidation state is 0. Found within water, it has a oxidation state of +1. And by the way, this is all found within the rules that we were looking at earlier. Now let's work out what's been going on. Looking at lead, it's gone from +2 to 0, which means it must have gained electrons to become less positive. Because it's gained electrons, we know it's been reduced. And we also know that means it acts as a oxidizing agent. Oxygen has remained the same. It has neither been oxidized or reduced because its oxidation number has remained at -2. Hydrogen, however, has gone from having a 0 oxidation state to a +1 oxidation state. In order to become positive, it must have therefore lost electrons, and therefore hydrogen has been oxidized. And as such, acts as a reducing agent. We're now going to put everything together we've just learned in order to use redox half equations to write balanced equations. So in order to balance a redox equation, we need to follow these steps. Firstly, we're going to start by assigning oxidation states to all atoms in the question. That's what we were just doing. Then we're going to deduce what's been reduced and what's been oxidized. And now step 3, we're going to provide the half equation for the reduction process and the oxidation process. And then this will be what's new to you guys, is adding electrons to either the left or right side of the equation in order to balance the oxidation states. Step 4, we're going to add waters and protons, H+ ions, to balance the O, the H and the overall charge. Then we're going to balance the two half equations, so the electrons lost on one side equals the electrons gained on the other side, a little like a simultaneous equation. And then finally, we're going to add the two half equations together to write the overall redox equation. Let's put this all into practice now by attempting the following question. So according to step 1, we need to assign oxidation states to all atoms in the question. So ion over here is quite straightforward. We can see straight away from the charge on the ion it's +2. Now remember, oxygen is assigned an oxidation state of -2. There's 4 of them, which gives us -8. There's an overall charge of -1, which means that manganese there must be +7. Iron over here is straightforward, and again the same is true for manganese. Let's break up our page into 2 to separate out the reduction oxidation sides. Check the oxidation states to see what's been oxidized, what's been reduced. The iron has gone from +2 to +3, so oxidation has occurred. Manganese over here has gone from +7 to +2, so reductions occurred. Write everything down, separating your reduction oxidation sides. So we are up to stage 2. We've deduced what's been reduced and oxidized. We've assigned oxidation states. We now need to add electrons in order to balance the oxidation states. So for manganese, we're going from +7 to +2, which means we need to add 5 electrons to this side. Iron's gone from +2 to +3, which means we need to add an electron here. Our next step was to balance your oxygen, hydrogens and your overall charge through the addition of water and H+ ions. So down here we can see 4 oxygens on the left-hand side, none on the right, which means we're going to have to add 4 waters to the right. The problem is now that we have 8 hydrogens on the right hand side, none on the left, so we're now going to add 8 H+ ions to the left. Happily, we have no such issues here because we've got no extra oxygens or hydrogens. We're getting there now, guys. We need to balance the two half equations so the electrons lost on one side equal those gained on the other, like a simultaneous equation. So we have 5 here, only 1 here. So it's really the equivalent of multiplied by 5 to this one. So by doing that, we can see now that those electrons will cancel out. And then we just combine everything to get our final equation. So keeping everything on the left-hand side of the equation that was there before. Do write it out nice and carefully. You wouldn't want to introduce errors at this late stage. And then I'm just going to add my state symbols back in. Let's go full steam ahead with another example. Feel free to pause the video in order to attempt this yourself. So I'm going to start by assigning oxidation states. So oxygen is -2. We have an overall charge of -1, which means that that nitrogen there is +5. Copper here is just 0. Nitrogen here is +2 and +2 over here. So let's work out what's been oxidized and what's been reduced. The nitrogen's oxidation state has reduced from +5 to +2, so it's been reduced. The copper's gone from 0 to +2, so it's been oxidized. Let's split it up. So here's where reduction's taking place. Here's where oxidation has occurred. Let's sort out the electrons. So for nitrogen, we're going from +5 to +2, which means we need to add 3 electrons here. Copper's gone from Cu to Cu2+, which means we need to add 2 electrons right here. Now let's check for oxygen and hydrogens. We have 3 oxygens here, only 1 here. So that means we need to add an additional 2 waters. Through the addition of 2 waters, we now have surplus hydrogens here, which means we need to add 4 H+ ions over here. And then handily on this oxidation side, everything is chill. And now we're ready for our simultaneous equation step. We've got +3 here and +2. The common number that both of these go into is 6, which means we need to multiply this equation by 2 and this one by 3. Rewrite it all. And now just cancel out our electrons and rewrite everything again, keeping your reactants to the left. And you will get quicker and quicker at this the more you practice it. Periodicity now. Now an element is classified as being an S, P, D, or F block element based on its position in the periodic table. And remember, its position in the periodic table is dictated by its proton number or atomic number. So we can see elements that exist over here are S block elements, P block elements, D block elements, and F block elements. If we consider the physical properties now of period 3 elements, this is period 1, period 2, period 3. So we're really concentrating on sodium through to argon. The trend is that the largest atomic radius exists on the left-hand side of the period. The atomic radius decreases as you move across the period. What is the reason for that? It's because the number of protons in the nucleus increases, so that nuclear charge is stronger, but you have the same amount of shielding due to the same number of energy levels. And while we're on this, remember as you descend a group, the atomic radius increases, and that's due to the number of electron shells increasing. Now I want you to take a look at the melting points as you move across period 3, why the various melting points exist for these elements. So starting over here towards the left-hand side of period 3, the metallic elements of sodium, magnesium, and aluminium. These will all form metallic bonds, and the strength of these metallic bonds increases as the number of delocalized electrons increases. So remember, sodium forms Na+ ions, so I'll have 1 delocalized electron per ion, Magnesium Mg2+ has 2 delocalized electrons. Aluminium over here at group 3 has 3 delocalized electrons, and that's why you see that increase in melting point. Silicon here is a giant covalent structure with many strong covalent bonds, so a lot of energy is required to break those covalent bonds, so you see that much higher melting point. And then as we move from phosphorus to sulfur to chlorine, because these are simple molecular structures, these molecules are held together by London forces or van der Waals forces. The reason why phosphorus has a low melting point compared with sulfur is because phosphorus exists as P4 molecules, whereas sulfur exists as S8 molecules, which are larger, and therefore the strength of the van der Waals forces increases for sulfur compared with phosphorus. Chlorine here is a Cl2 molecule, so a smaller molecule compared with both sulfur and phosphorus. Weaker van der Waals forces exist here between the molecules. And then argon here, because it's a noble gas group 0, it's monatomic, so it has the weakest van der Waals forces of all. And this is taken from my revision guide, so you can actually see all the explanations that I just mentioned. And now we'll have a look at the group 2 alkaline earth metals. As we turn our attention to the group 2 alkaline earth metals, we are going to zip through various properties to do with atomic radius, ionization energies, melting points, their reactions with water, as well as their solubilities. Now, this page is taken from the SWH revision guide. I'm going to quickly zip through this because, after all, I've talked in great detail about various atomic radii, ionization energies previously in this video. As we descend group 2, we can see that barium has a larger atomic radius compared with magnesium, and the reason for that is an IGCSE reason due to the number of electron shells increasing. Now, as you descend the group, the first ionization energy decreases. Now notice magnesium has the highest first ionization energy, barium has the lowest, and that's because more shells means that there's a weaker attraction of the ion to the lost electron, meaning that less energy is required to remove the electron. In terms of melting point, we'll find that magnesium has the highest melting point, barium has the lowest. That's because as you descend the group, you have an increased atomic radius, and then as a result, the metallic bonds weaken. Like group 1 elements, as you descend the group, the elements become more reactive with water. The general equation remains the same as group 1. The group 2 metal reacts with water to form a metal hydroxide and hydrogen. Here's your balanced chemical equation, and here's an ionic equation where we've removed the spectator ions. Using oxidation states, you'll notice that the metal is oxidized. It goes from a 0 oxidation state to a +2, hence oxidation has occurred. Water causes that metal to become oxidized, so in this case it's acting as an oxidizing agent. An extra reaction to be aware of is that magnesium reacts rapidly with steam to form magnesium oxide, and that's when you need to wear protection on your eyes because a bright white light is seen. Now looking at the solubilities of those group 2 hydroxides, group 2 sulfates, in water, starting with the group 2 hydroxides, you'll notice that the solubility increases down the group, meaning that at the top of the group, magnesium will be almost insoluble, strontium hydroxide is sparingly soluble, and barium hydroxide is very soluble. The insoluble metal hydroxides form white solids. Here we have a quick note on how we test the solubility of the group 2 hydroxides. We mix the group 2 salts with sodium hydroxide, and then we'll observe the group 2 metal hydroxide formed, and we'll see a white precipitate for an insoluble one and a colourless solution for soluble hydroxide. So you'll see colourless down here whilst a white precipitate forms up here. Now the metal 2 sulfates. This time the sulfate solubility decreases down the group, and you'll notice that barium sulfate is almost insoluble, and we'll talk about the uses of barium sulfate shortly. Remember, it's used in medicine as a medical imaging technique. When we want to test for the group 2 sulfate solubility, we mix the soluble salts with sulfuric acid. The metal sulfates formed will either be a colourless solution or white precipitate. So in terms of when we look more closely at these, magnesium's role will be in the extraction of titanium, and also in its role as an indigestion treatment or medicine. For barium, again, it will be medicine, but this time in imaging. So that will be your barium meal. And then we'll be talking about the use of barium chloride as a test for sulfates. And then in terms of calcium's role, we'll be looking at its role in agriculture to neutralize acidic soils, and then also in its role in industry, removing sulfur dioxide from flue gases. So obviously we need to talk about this in far more detail, but this is the whole blurting type of revision technique where you learn all the content but then make sure you've got an idea of the bigger picture, so that if someone mentions magnesium, okay, fine, I need to know that it's to do with titanium extraction. It's used as an indigestion medicine. Barium, oh fine, that's to do with medicine, imaging, looking at the digestive system. It's used as a test for sulfate ions, and then calcium is used in agriculture and industry in order to remove acidic oxides as well as neutralizing acidic soils. So those two roles are quite tightly linked. So now let's go into the in-depth chemistry. So starting with magnesium. We already mentioned its two roles. Titanium extraction. As an indigestion aid or medicine. So titanium is a really useful metal. We like using titanium because it's strong, it has low density, it's highly resistant to corrosion. Now, in terms of extracting titanium, purifying it, unfortunately, remember with extraction of metals, it totally depends on the reactivity of the metal. But if it's very unreactive, such as gold and silver, it's found native, Lyra, in the Earth's crust. If the metal is less reactive than carbon, then you can basically use a blast furnace, such as in the case of iron oxide, and you use carbon monoxide to reduce that iron oxide to make iron. And then if it's more reactive than carbon, then you have to use the expensive electrolysis process, but that's super annoying because you've got high energy costs. Now, titanium isn't particularly reactive, so you would expect to use this process, you'd expect to use reduction with carbon, but unfortunately, when you react it with the carbon, it forms titanium carbide, which is very brittle. So let's make the note, titanium can't be extracted by reacting with carbon because titanium carbide is formed, which is very brittle. So that means it breaks very easily when a force is applied. So therefore, in terms of how you actually go about extracting titanium, it's in the following steps, and obviously one of those steps must involve magnesium, because after all, this part of the specification is all about the uses of group 2 elements. So first of all, you treat the titanium with chlorine to form TiCl4, and then this is where the magnesium comes in. The magnesium is used to reduce TiCl4 in the following equation. And you do have to learn these equations. Let's check that reduction taking place by looking at the oxidation numbers, oxidation states. So this chlorine here is -1, which means that titanium is +4, and the titanium on the right-hand side is 0, hence reduction has occurred to that TiCl4. Look at the oxidation states of magnesium, where you've got 0 over here, -1 for the chlorine, which means that must be +2 for the magnesium, so here we can see oxidation taking place. So just to really point that out, the magnesium acts as a reducing agent. By definition, remember, reducing agents are always oxidized, which we can see has taken place here. So magnesium acts as a reducing agent. It has caused TiCl4 to be reduced. That's enough on titanium. Now let's talk about the role of magnesium as an indigestion, medicine or treatment. So you need it in the form of magnesium hydroxide. So magnesium hydroxide is used to neutralize excess stomach acid, which remember is hydrochloric acid. The reason it can be used like that is because the magnesium hydroxide is insoluble. So if we look at the equation of what takes place, it's just a generic neutralization reaction which produces magnesium chloride and water. Make sure it's balanced. In this form, this medicine is known as milk of magnesia. And just to point something out, remember carbonate would also work. So for example, if we were to take magnesium carbonate, effectively you'd also get a neutralization of that hydrochloric acid, but the issue here is that you produce carbon dioxide, which remember is a gas. So that produces lots of bubbles, which, let's be honest, if you've got a bubble party happening in your stomach, that's not going to make you feel any better. So our go-to remedy is milk of magnesia. So that's magnesium done. Let's move on to barium. Let's start with its medicine role. Now, in its role in medicine, it's barium sulfate, BaSO4, and again, its use relies upon it being insoluble. So barium sulfate is known as a barium meal, and what's cool about it is that it absorbs X-rays to give an image of the gut, so you can see basically if there are any blockages or not. Now the key thing here is that it's insoluble, which means that although usually barium compounds are highly toxic, because it's insoluble, they're not absorbed into the body. Now we'll look at the second role of barium, which is that it's used to test for sulfate ions. You might have met this at IGCSE and GCSE. So what is the test for sulfate ions? Well, you need acidified barium chloride, and then the positive test for sulfate ions with that barium chloride is a white precipitate. And if you were to look at the ionic equation, you've got those barium ions reacting with the sulfate ions to form barium sulfate, which is a white precipitate, a solid. So this is insoluble again. Remember that we need that acidification with something like hydrochloric acid in order to react with any carbonate ions which could interfere with the test and produce carbon dioxide. So that acid reacts with any carbonate ion impurities. And then lastly, calcium. Let's divide its uses into agricultural uses and industry uses. So in agriculture, calcium hydroxide is known as slaked lime. It's added to acidic soils in order to neutralize them so that that pH is increased, and that helps crops grow, because crops really don't like acidic soil. What about the industrial use of calcium? Well, this is in the form of calcium oxide and calcium carbonate. These are used to remove toxic SO2 gas from factory chimneys. And I'll just show you some equations. So here's the first equation with calcium oxide, and now we'll look at when calcium carbonate's used. Some past paper practice. There are many uses for group 2 metals and their compounds. State a medical use of barium sulfate. State why this use of barium sulfate is safe, given that solutions containing barium ions are poisonous. So the use is as a barium meal. And why is it safe to use in this way? Because barium sulfate is insoluble. Magnesium hydroxide is used in antacid preparations to neutralize excess stomach acid. Write an equation for the reaction of magnesium hydroxide with hydrochloric acid. So here is your formula of magnesium hydroxide. Remember, magnesium is 2 plus, hydroxide is OH minus. There's hydrochloric acid. It makes MgCl2 plus H2O. Get that balanced. Solutions of barium hydroxide are used in the titration of weak acids. State why magnesium hydroxide solution could not be used for this purpose. Again, because it's insoluble. You can't be titrating something that's insoluble. Magnesium metal is used to make titanium from titanium 4 chloride. Write an equation for the reaction of magnesium with titanium 4 chloride. So this is what I was saying in the video, you do have to learn this. And then again, make sure it's balanced. Group 17, the halogens. And we'll be looking at trends in properties, specifically trends in electronegativity and the boiling points. Again, if you've been watching me, you'll know that I like to kind of blurt some summaries at the beginning before we get into the more in-depth content. So we'll just start by saying that the boiling points increase down the group. Bear that in mind. Whereas the electronegativity decreases down the group. And we'll talk about why now. But yeah, I'm going to grab my highlighter and remind myself. So let's start by reminding ourselves what the term electronegativity means, because otherwise we won't understand why electronegativity decreases down the group. So in case you're asked to define this, electronegativity is the power of an atom to attract a pair of electrons towards itself in a covalent bond. So if we consider that definition, the power of an atom to attract a pair of electrons towards itself in a covalent bond, what's going to be doing that attracting is obviously going to be the positively charged nucleus. So ideally speaking, you want a small atom, don't you? So that attraction force is stronger. So to really spell that out, electronegativity decreases down the group because there is an increasing distance between the nucleus and bonding pair of electrons, and that's due to increased shielding. Remember, these are the group 7 or group 17 elements, so we're starting at the top with fluorine, chlorine, bromine, iodine and astatine. According to what we've just said then, fluorine is the most electronegative. Astatine is the least electronegative. And remember, this goes some way to explain why fluorine can be involved in hydrogen bonding, because remember, hydrogen bonds form between hydrogen and highly electronegative elements, which you have to learn, remember, are fluorine, nitrogen and oxygen, and that's the only time hydrogen bonds will form. What about if we consider the boiling points now? So the boiling points of group 7 increase down the group. Don't just rote learn these things, guys. Just remember to use facts that you're probably already aware of. So the fact that fluorine and chlorine are both gases, bromine is a liquid. Remember, we're talking at room temperature here. iodine and astatine are both solids. So that tells us automatically that the boiling point increases down the group. But why is that? Well, it's because the number of electrons, and therefore the number of electron shells, increases down the group. Fundamentally, that means that the halogen molecules, because remember they're all diatomic molecules, this means that the molecules are larger. And then if we consider intermolecular forces, the intermolecular forces that are important here are the van der Waals forces. So with the molecules being larger, there's a larger electron cloud to distort. So we're going to say that there's more van der Waals forces. Which require more energy to overcome them. The boiling points of the halogens increase down group 7 because the covalent bond strengths increase. No, remember with the boiling points you're breaking intermolecular forces. Covalent bonds occur within the molecules, so that's not the reason. Bond polarities increase. Again, that's false. You've got two of the same atom, haven't you? The surface area of the molecules increases. Remember that's true because as you descend that group, the atoms have more shells of electrons. The electronegativities increase. No, that's false. They decrease down the group. Do make sure you go through the other options if you're not entirely sure, just proving why they're all wrong, and that will help you zoom in on the right answer, even if you're not 100% sure. Explain why chlorine has a lower boiling point than bromine. So chlorine is a smaller molecule with fewer shells of electrons. So fewer van der Waals forces between molecules. So less energy is needed to overcome them. Remember, oxidizing agents cause other substances to be oxidized, which means to lose electrons. And by definition, therefore, oxidizing agents are themselves reduced at the same time, which means they must have gained electrons. Always bear in mind what's happening with electrons in these sorts of reactions. Now, just to recap a little bit, remember halogen displacement reactions from IGCSE and GCSE, because this is tightly linked. At GCSE, you learnt that a more reactive halogen displaces a less reactive halogen, or halide ion, really. So just remember, fluorine is the most reactive halogen, and then as you descend the group, the elements become less reactive. So we can say that if fluorine was to react with sodium bromide, the fluorine would displace the bromide to form sodium fluoride plus bromine. So that's all balanced, and I've added state symbols. If we look at the ionic equation, just if you're not happy with this, just draw out all the ions like this. So I'm separating out those ions. So now you want to delete the spectator ions, so look to see which ions remain the same on the left and right hand side. They are spectators. So our final ionic equation looks like this. So for F2 to become 2F minus, it must have gained 2 electrons. So it must have been reduced. For 2Br minus to become Br2, it must have lost 2 electrons. So that has therefore been oxidized. So you can see how these are therefore redox reactions, because both reduction and oxidation have taken place. So just to really point this out then, because that fluorine has been reduced, remember what I said at the start, by definition an oxidizing agent must be reduced. So here's our oxidizing agent in this case. Remember, they could ask you about color changes. So in this case, that bromine will be orange. If chlorine had been produced, it would be pale yellow or green, and then iodine would produce a brown solution. So here's a summary of all the halogen displacement reactions. So remember, a more reactive halogen will displace a less reactive halogen from its compound, which is why you always get a reaction with fluorine because it's the most reactive. So for example, it will react quite happily with sodium chloride, sodium bromide, sodium iodide. Chlorine is less reactive than fluorine, hence why you get no reaction here, but it's more reactive than bromine and iodine. Bromine is only more reactive than iodine, so that's the only time you get a reaction. Iodine is the least reactive compared with these elements, so you'd expect no reaction. So to really summarize what I was just saying and make it very centric to A-level and IB, we're going to say halogens react by gaining electrons. So by definition, the halogen is reduced, such as in the case here. Halogens therefore act as oxidizing agents. Remember, I've already said that as you descend the group, the elements become less reactive. That means they also become weaker oxidizing agents. So fluorine is the most reactive and the strongest oxidizing ability. Astatine has the weakest oxidizing ability. As you descend, group 7, oxidizing ability decreases. Chlorine behaves as an oxidizing agent in the extraction of bromine from seawater. In this process, chlorine gas is bubbled through a solution containing bromide ions. Write the simplest ionic equation for the reaction of chlorine with bromide ions. So there's Cl2, there are the bromide ions. Chlorine is more reactive or acts as a stronger oxidizing agent, so actually you're going to produce bromine plus chloride ions. Make sure that's balanced. State one observation that would be made during this reaction. While we make bromine, so we'd see an orange-brown solution. In terms of electrons, state the meaning of the term oxidizing agent. Causes another substance or species to lose electrons. Which of the following is not a correct trend of group 7? The first ionization energy of the atom decreases. That's absolutely true because remember, those atoms get larger, they have more shells of electrons, so it's easier to remove an electron. The oxidizing power of the element increases. No, we said it decreases. We said that at the top of that group, you'd find the strongest oxidizing agent. The electronegativity of the atom decreases. That's true. Remember, fluorine is the most highly electronegative element in that group. The boiling point of the element increases. Yes, remember, astatine and iodine at the bottom of the group are solids at room temperature compared with fluorine and chlorine, which are gases. Which of the following statements is true? Bromine liberates iodine from aqueous sodium iodide. That's true because bromine is more reactive than iodine or is a strong oxidizing agent. We're now going to consider their ability to act as reducing agents. And underpinning this, remember, is the fact that by definition, if something acts as a reducing agent, it must be oxidized in the process. So I'm going to write that. The halogen is oxidized which remember means that it loses electrons. So bear that in mind the whole time, because it will help you understand what's going on when we look at the huge number of equations. So starting with the bold statement that the reducing ability, so their ability to act as reducing agents of the halide ions, increases down the group. So if we consider the elements, fluorine, chlorine, bromine, iodine, astatine, by definition, astatine is the strongest reducing agent. Whereas fluorine is the weakest. But what is our explanation for that? Well, as you descend the group, remember the atoms get bigger, so the number of shells of electrons increases. This means that the ionic radius increases. The amount of shielding of those outer electrons, those valence electrons, increases. The electrostatic force of attraction between the nucleus and valence electron weakens. And then the all-important point, which is that the valence electron is more easily lost, and that takes us back to our original definition of oxidation, which is all about losing electrons. So the halide ion is more easily oxidized. The halide ion acts as a stronger reducing agent. So if you're asked in the exam to explain why the reducing ability of the halide ions increases down the group, you need to be talking about the number of shells of electrons increasing, meaning the amount of shielding increases, so the attraction between the nucleus and the valence electrons weakens. That valence electron is more easily lost, the halide ion is more easily oxidized, the halide ion acts as a stronger reducing agent. And now let's talk about observations. So how do we observe, or how can we see that the reducing ability of the halide ions increases down the group? Well, we react those solid sodium halides with concentrated sulfuric acid. Bear in mind that we can prove that the halide ion's reducing power increases if we look at the various equations involved and we consider sulfur's oxidation number. Because the greater that decrease in oxidation number of sulfur, the greater the halide's reducing power. Let's take these various halide ions in turn then. So we're going to descend the group starting with sodium chloride, so the chloride ion. Remember, we're expecting as we descend that group that this chloride ion will be a weaker reducing agent compared with the halogens, which are lower down in the group. And we're going to prove that now. So the sodium chloride reacts with that concentrated sulfuric acid, and you will need to learn these equations. In terms of observations, we will see steamy fumes of HCl produced. In red, I'm going to put the oxidation numbers. So hydrogen is +1, oxygen is -2, which means that sulfur here is +6. What about on the right-hand side? Sulfur is again +6, so I'll highlight that to show that there's no change in oxidation state, indicating that the chloride ions are very weak reducing agents. Just as an aside, by the way, we can infer that this is not a redox reaction. And it's actually because that oxidation number of sulfur hasn't changed, so we can't say that oxidation and reduction have both taken place here. So we've dealt with sodium chloride. Moving down a halide ion, we're going to take on sodium bromide. Here, two reactions take place. Here's the second reaction as an ionic equation. And now let's look at the combined full equation for that second reaction. I'm going to label various oxidation states. So in this equation up here, in that first equation, look, that sulfur hasn't changed its oxidation state. So again, it's not a redox reaction. But if we look down here, I'm just going to grab my highlighter. We can see that sulfur's gone from +6 over here to +4 over here, which means that reduction's taken place. The bromine's gone from -1 over here to 0 here, so that means oxidation has taken place, and therefore we can say that this is a redox reaction. Really spelling this out. So that is oxidation, this is reduction. In terms of observations that take place, we produce Br2, so we will see a brown liquid. Now we're considering the iodide halide ion in the form of sodium iodide. Oh, we have multiple reactions taking place here. So that sulfur hasn't changed oxidation state. There's no redox reaction in this first reaction. Reaction 2 now. So there's reduction taking place because we've gone from +6 on sulfur to +4. Looking at iodine, we've gone from -1 to 0. So that's oxidation. So this is a redox reaction. Our observation here is a choking gas, which is sulfur dioxide. Reaction 3. There's sulfur being reduced again. There's iodine being oxidized. So that is a redox reaction. Our observation here is that sulfur produced is a yellow solid. I promise we're nearly there. What about equation 4? So our sulfur has been reduced, its oxidation has fallen from +6 to -2. The iodine has gone from -1 to 0. So that's oxidation, so another redox reaction. In terms of observations, we get a black solid, which is I2. We also get an eggy smell from this stinky hydrogen sulfide gas. And just to bear this all in mind, remember this series of equations is showing to you that as you descend group 7, those halide ions become stronger reducing agents. Question 1, which of these species is the best reducing agent? So 2 things to notice. First of all, we need a halide ion, not the halogen. And second of all, we want the element which appears lowest in group 7, so that will therefore be the iodide ion, I-. Which one of the following statements concerning halogen chemistry is true? Sodium chloride produces chlorine when treated with concentrated sulfuric acid. This is why I said it's so important that you learn these equations, because that first equation I showed you did not have chlorine being produced. Sodium chloride produces chlorine when treated with bromine. This is all to do with halogen oxidizing ability. Do you remember when we looked at a previous video to do with halogen displacement? So a more reactive halogen displaces a less reactive halogen. Bromine is less reactive than chlorine, so this is false. Sodium bromide produces bromine when treated with concentrated sulfuric acid. That's true. That was in the sodium bromide set of equations that I've just written about. Sodium bromide produces bromine when treated with iodine and aqueous potassium iodide. Again, that's false for the same reason that this one was false. So the answer here is C. Concentrated sulfuric acid can be reduced by some solid sodium halides to H2S, gives the oxidation state of sulfur in H2S. So remember, hydrogen ions are always +1. The compound is always neutral, which means that the answer here is -2. Give one solid sodium halide which will reduce concentrated sulfuric acid, forming H2S. Remember, it's the elements that sit lower in that group which have a stronger reducing power, so NaI is a good answer here. State one way in which the presence of hydrogen sulfide could be recognised. Remember, it's by its horrible smell of bad eggs. A different solid sodium halide reacts with concentrated sulfuric acid without reduction, forming a halogen-containing product X. Suggest an identity for X. So you want a halogen which acts as a weaker reducing agent, so you need to look towards the top of the table. So the solid sodium halide will be something like sodium chloride or sodium fluoride. So in terms of what will that product be, it will be hydrogen chloride or hydrogen fluoride. Identify the solid sodium halide which produces X. Already answered that, NaCl. State the role of sulfuric acid in the formation X. It's acting as an H+ or proton donor. So we need to be aware of the tests for chloride ions, bromide ions, and iodide ions. In terms of the method, which you do need to specify, number 1, you need to add nitric acid. And they could ask you why you do that, and that's in order to remove any other carbonate ions which could interfere in the test. And the second step is to add silver nitrate. Now this is really important. So if we look at the results, which again you'll have to specify, if you have chloride ions, the result here will be a white precipitate. And make sure you remember to include the word precipitate. Now, if you have bromide ions, you'll see a cream precipitate. Sorry, I'm struggling to draw cream. And lastly, if you have iodide ions, then you'll see a yellow precipitate. Now, one thing I wanted to just point out to you to help you remember these colours is as you descend group 7, so from chloride here to bromide underneath and then iodide underneath, notice that the colours get darker. So we go from white to cream to yellow. So make sure you pick those out of the periodic table over here to help you. Remember that they get darker, and lastly that they are colours of dairy. So I like to think of it in terms of white milk, cream coloured cream and yellow butter, and that really helps me remember those colours. Now let's look at the ionic equations. So number 1, when we were testing for the chloride ions, now if we look up, we know we're adding those chloride ions to silver nitrate. The nitrate ion here is acting as a spectator, so we're only interested in the silver part of this. So if we add silver ions Ag+ to the chloride ions, which is Cl-, they're both in aqueous solution, so that's our state symbol. They're going to form a precipitate, so a solid, of silver chloride, which we know is a white precipitate. If we take our bromide ions, if we take our silver ions and we add it to those bromide ions, also an aqueous solution, we're going to make solid silver bromide, which we know is a cream precipitate. And then lastly, our iodide ions, which we're going to add to silver again. And our final solid is silver iodide, which is a yellow precipitate. In reality, however, these dairy colours are hard to distinguish. So at A level, a further test is needed. You add ammonia, and what you find is that when you have silver chloride, the silver chloride dissolves in dilute ammonia according to the following equation. Here's our precipitate, here's our dilute ammonia. With silver bromide, you find that it dissolves in concentrated ammonia, and they will expect this level of detail from you. And then what really distinguishes the silver iodide is that it doesn't dissolve in either concentrated or dilute ammonia. It is insoluble in both. How about the uses of chlorine and chlorate? Chlorine reacts with cold water to form chloric acid and hydrochloric acid according to the following reaction. So here's your chloric 1 acid. If we check the oxidation states, chlorine goes from 0 to +1, and over here it becomes -1. As the chlorine is both oxidized and reduced according to the increase and decrease of those oxidation states, we say that a disproportionation reaction has occurred. We can use the chloric 1 acid here to kill bacteria. We can use it to make bleach. As we can see, it's a reversible reaction. And then in sunlight, another reaction to be aware of is when chlorine reacts with water to form hydrochloric acid and oxygen according to the following equation again. Now, chlorine is obviously a toxic gas, but if used in very small quantities, it can be used in water treatment to disinfect water and kill any bacteria present, which could be pathogenic. And now a third reaction, chlorine reacts with cold, dilute, aqueous sodium hydroxide to form sodium chloride, sodium chlorate 1, and water. Check our oxidation states again. Chlorine goes from 0 to -1 over here and +1 over here. So it's another example of a disproportionation reaction because it's being both oxidized and reduced. And this sodium chlorate here is another active ingredient in bleach. So how do we test for group 2 ions? The approach you're going to use here is to test the group 2 chlorides. So obviously that contains your group 2 ion combined with chloride, and you can use two approaches. You can either add excess sodium hydroxide or you can add excess sulfuric acid. If you take the first approach of adding excess sodium hydroxide, you'll find that magnesium hydroxide and calcium hydroxide both form a white precipitate. Now, strontium hydroxide forms a slight white precipitate. If you have barium ions, you won't get a white precipitate. There'll be no change. But what about if you want to use excess sulfuric acid to distinguish your group 2 ions? If you have magnesium ions, you'll see no change. Calcium sulfate forms a slight white precipitate. Strontium sulfate and barium sulfate both produce a white precipitate.
This is quite an unusual test. In terms of the method you need to specify, again you're going to use sodium hydroxide, but instead of producing a precipitate, you're going to produce a choking colourless gas. And can you hazard a guess as to what that gas is? Well, it's likely to be ammonia. However, you need to prove that it is ammonia, so how do you do that? You hold the gas over damp red litmus paper, and then that litmus paper should turn blue. And that tells us that we have ammonia, and that therefore that original substance must have contained ammonium ions.
Testing for hydroxide ions, OH-, because they're alkali, they'll turn damp red litmus paper blue.
Now we're ready to move on to testing for sulfate ions, which, remember, these are SO42-. So in terms of the method, firstly you want to add hydrochloric acid, and next up you add barium chloride. Just a list of ingredients you have to add. One of the ways I find is easiest to remember this combination is the chloride and the chloric are the same. So rather than adding nitric acid, you're going to add hydrochloric acid, and the clue is in the barium chloride. In terms of the result, so what you'll see in this situation, you'll get a white precipitate. And what is that white precipitate? Well, it's barium sulfate. BaSO4, and then to show that ionic equation, we've got barium in aqueous solution again being added to that SO42- sulfate ion to get BaSO4 solid. Our final test is for carbonate ions, CO32-. Our method this time, you can kind of get away with adding any acid here, but let's just say we're going to add hydrochloric acid. And then what you should see next is that it should start to fizz. And that fizzing in any chemistry experiment indicates a gas being given off. And if it's a test for carbonate ions, then we should imagine that this gas is CO2, i.e. carbon dioxide. And so therefore we need to test for carbon dioxide. So you bubble gas through lime water. And if that lime water turns cloudy, then you know that gas is carbon dioxide. And so going back to our original point, we therefore know that the original solid must have contained carbonate ions in order for that gas to be positively identified as CO2. So in conclusion, original substance must have contained carbonate ions.
It's now time to introduce organic chemistry. This is chemistry relating to the element carbon. Now remember, homologous series are families of compounds with the same chemical properties. They show a trend in physical properties. They have the same functional group and the same general formula. Now this is a table which lists all the homologous series in order, starting from the highest priority up here with the carboxylic acids, moving all the way down to the cycloalkanes, which have the lowest priority. And that's important when it comes to naming organic compounds, so you know what order to write their names so that scientists all around the world know exactly what substance you're talking about. As these yellow boxes point out, an X stands for any halogen, so that could be fluorine, chlorine, bromine, iodine, for example, and R just means the rest of the molecule. But as we look down here, we can see various functional groups. You've got the carboxylic acids with their functional group COOH, and then the R just means the rest of the molecule. Hopefully you've met esters before when you were studying either IGCSE or GCSE. Here are your aldehydes. Don't forget the arrangement of atoms. Each carbon atom forms 4 bonds, hence why this is the functional group of the aldehydes. Carbon here is forming 4 bonds, oxygen forms 2 bonds, hydrogen forms 1 bond. If we take that carboxylic acid now, again we're obeying our rule of carbon forming 4 bonds, oxygen forming 2 bonds, hydrogen forming 1 bond. Do keep an eye on these suffixes and prefixes. Again, this will be incredibly important. You're probably familiar with ol representing an alcohol, potentially even oic acid representing a carboxylic acid. Now, there are a variety of different formulas you need to be comfortable with using. So if we use propene as our example, we'll start with the molecular formula of propene. Remember, this is the actual number of atoms of each element present in a compound. The molecular formula of propene is C3H6. The empirical formula now of propene, this is the simplest ratio of atoms of each element present in a compound. So we're going to take our molecular formula and cancel it down, so it becomes CH2. That is the empirical formula. What about the general formula? You'll have met the general formula of alkanes and alkenes before. For alkenes like propene, the general formula is CnH2n, where N indicates the number of carbon atoms. So in the case of propene, we know that N equals 3, and that's how we arrive at our molecular formula of C3H6. The structural formula gives a little bit more information about how those atoms are arranged without drawing them out fully in a displayed formula. So this is the structural formula of propene. It allows us to see that it is unsaturated and has that carbon-carbon double bond. The displayed formula now allows us to see the arrangement of atoms in space. So I'll start with the double bond. There's the third carbon. And now I'll arrange my hydrogens around the carbon. And then finally the skeletal formula shows us the bare bones of the displayed formula. When drawing the skeletal formula, each end of a line or junction represents a carbon attached to hydrogens. All other functional groups are drawn in full. But just to show you the skeletal formula of propene, there's the carbon-carbon double bond. Each end of a line or junction represents carbons attached to hydrogens, and if there were other functional groups such as an alcohol functional group, the OH, you would see that written in full. Skeletal formulas do require a little more practice. So introducing the IUPAC system, and this enables chemicals to be recognised and used worldwide. So it's how do we name organic compounds? We're going to use a combination of these rules as well as the table listing the homologous series starting from the highest priority. We'll do lots of practice so you can really understand how we can apply these rules, but it's worth you seeing them. Point 1, determine the length of the longest carbon chain. And remember, it's useful to use monkeys eat peanut butter to help us remember these stem names. After that, pent, remember, means 5. Pentagon, hex means 6. Hexagon, so it becomes slightly more straightforward. But yeah, if you have 1 carbon, it's methane. 2 carbons, ethane. 3 propan, 4 butan. Step 2 tells us to find the functional groups, so we'll be able to identify whether it's a carboxylic acid, ketone or alkene, for example. Step 3, we're going to number the longest chain of carbons, and it's important that we ensure that the carbon bonded to the principal functional group is given the smallest number possible, and that principal functional group we'll be able to determine through cross-referencing using the table I just showed you. Step 4, determine the suffix. Remember, this is the last part of the name. If there's only one functional group, it will be named as the suffix of the compound. you need to include the carbon number where the functional group is attached. So for example, if you've got the OH of the alcohol functional group, you need to specify that it is attached to the second carbon on that long chain of 4 carbons as indicated by butane. Step 5, determine the prefixes. So that's the start of your name. If there are 2 or more functional groups, the highest priority group will form the suffix. Other functional groups and carbon side chains are included in the name as prefixes. I know this looks nasty, but examples is when we're going to be able to unpick this and understand it better. These are written in alphabetical order and also require the number of the carbon they're attached to. Adapt for any double or triple chains. So when they're identical side chains, such as 2 methyl groups, we'll use dimethyl. If you have 3, it will be tri, and tetra means 4. However, practice makes perfect, and it will be far better if you can see how we arrive at these names. So here is example 1. Looking at step 1, we are now going to determine the length of the longest carbon chain. We can see here that it is 3. What is the principal functional group? We can see it's an alcohol, so it's OH. We have no other functional groups. And now look to see if there are any additional chains. Immediately we can see yes, we have 2 methyls. So to start formulating its name, let's go in with the longest carbon chain. We know that it is prop due to the 3 carbons. We have the principal functional group of the alcohols, so we need to mention that here. Count the carbons, first, second, third. It's on the first carbon, so it's propan 1-ol. And then to deal with these 2 CH3 groups, remember these are known as methyl, they're both on the second carbon. So the name of this compound becomes 2,2-dimethyl propan 1-ol. Let's take a look at the second example now. So first of all, determining the longest carbon chain. Count them, it goes 1, 2, 3, 4, 5, 6. What is our principal functional group? Obviously an alkane. We also have chlorine here. Have a look down this table. We can see the alkanes appear before the halogenoalkanes, which indicates that a halogen is involved. So that's why the alkane is our principal functional group. Let's list our other functional groups. So we've got 2 lots of chlorine attached. What additional chains do we have? We've got 2 CH3s, and don't forget we need to remember to put our prefixes in alphabetical order, and we need to keep the numbers as low as possible. Right, let's name this beast now. So the longest carbon chain is 6. I've numbered them. I'm going to start here with this carbon being my first carbon. Because we have 6 carbons, I know I'm going to have hexane featuring. Because the alkane is the principal functional group, I now need to deal with that as part of its name. There's 2 methyl groups here and here. They're on the second and the 4th carbon. Di means that there's 2. And then lastly, let's sort out these Cls. There's one on the second and one on the 4th. There's 2 of them again. So we're going to go 2,4-dichloro, 2,4-dimethylhexane. Okay, time to look at another example. So the longest carbon chain here, 1, 2, 3, 4. What's our principal functional group? Let's look at what functional groups we have. We have CN and we have OH. So we have a nitrile and we have an alcohol. The nitrile appears higher in this table, so we know that's going to take priority. Our other functional group is the alcohol. We've got no additional chains. So to name, our longest chain has 4 carbons, so we're going to have bute featuring. Nitriles, so the CN functional group, are a little bit annoying because when they're present, you have to include the E on butane, methane, etc. And the nitrile needs to feature at the end of the alkane chain name, which sets it apart from all our other examples. But then we just need to deal with the OH, number your carbons. So the OH is on the second carbon, there's only one of them. So it becomes 2-hydroxy butane nitrile. Okay, what about this one now? So what's our longest carbon chain? It's 3, so it'll be prop. What's our principal functional group? Is it the alkene or the halogen part? Using your table, you'll see it's the alkene. Our other functional group is the Br. We've got no additional chains, so to name. Just be a little bit careful when numbering the carbons because the alkene takes priority. We're going to number from this direction. So our longest chain is 3. We know it's an alkene. The double bond occurs at the first carbon, so it's prop 1-ene. And then the bromo is attached to the third carbon, so it's 3-bromo, prop 1-ene. Let's have an attempt at this nasty skeletal formula. What is our longest carbon chain? Here's a carbon 1, 2, 3, 4. So that's bute. What is our principal functional group? It's simply an alkane. There's no additional functional groups. But do we have any additional chains? Yes, we can see we have 3 lots of methyl groups. And if I just number these, you'll be able to see them better. So we're going to call that our first carbon, second carbon, third carbon, 4. So our 3 additional methyl groups you can see would be attached here, here, and here. So to name, the longest chain is 4. It's an alkane, so it's simply butane. And then we have 3 methyl groups, so we need a trimethyl. And then specify which carbons these are attached onto. They're attached onto the second carbon and the third carbon. Now, reaction mechanisms are largely A2 topics, but in the AQA specification, they do just like you to get used to what these dots here mean, what the arrows mean. So I'm just going to give you a brief introduction here. So reactions of organic compounds can be explained using mechanisms. As I've already said, we'll look at specific mechanisms later on when we consider A2 topics. This is taken from my revision guide, hence this point here. Just to be aware, a dot next to an atom represents an unpaired electron, and this is actually called a free radical. We use curly arrows to show the movement of electron pairs as covalent bonds are both made and broken. So that's what these red arrows here are representing. An arrow starting at a lone pair or from another covalent bond shows the formation of a covalent bond, as is the case here, whereas an arrow starting at the bond shows the breaking of a covalent bond. And then you can see here how the new bonds form. A reminder of the definition of isomerism from GCSE. Isomers are compounds with the same molecular formula but a different arrangement of atoms. We're going to start with looking at structural isomers. So to be really specific here, our definition is as follows. They're compounds with the same molecular formula but different structural formula. There are 3 different types of structural isomerism: positional isomerism, functional group isomerism, and chain isomerism. So what do each of these mean? Well, positional isomerism is when the functional group is attached to a different carbon in the chain. So here's our functional group. In this example, our Br. So if I wanted to show a position isomer, I'm going to move that functional group along a carbon. And to prove that they're still isomers, the molecular formula is as follows. So these are both C3H7Br, but the functional group has moved along. In functional group isomerism, the isomers contain different functional groups. So here's a ketone, but over here we have an aldehyde, but they both obey the molecular formula of C3H6O. And then in chain isomerism, we find that the carbon chain is arranged differently. So you'll find branches here. So we'll take a straight chain isomer first of all, of pentane. And then we're going to start branching. So I'll start introducing methyl groups. And then I'm going to reduce that main chain length again. But if we check the molecular formula of each of these isomers, this is C5H12. 1, 2, 3, 4, 5. This is C5H12, and this down here is C5H12. So just to reiterate, to summarize, our positional isomerism is when the functional group is attached to a different carbon in the chain, such as the case of here. We've gone from 1 bromopropane to 2 bromopropane, and they are both positional isomers of C3H7Br. With functional group isomerism, the isomers contain different functional groups. So here's our ketone propanone versus our aldehyde propanal, but they both have the molecular formula of C3H6O. And then down here, chain isomerism, this is when the carbon chain is arranged differently, it contains branches. So our C5H12 can be arranged as 3 chain isomers of pentane, 2-methyl-butane, and down here we have 2,2-dimethyl-propane. What about stereoisomers or stereoisomerism? Stereoisomers have the same structural formulae, but a different arrangement of atoms in space. There are 2 types of stereoisomerism. You've got EZ, otherwise known as geometric isomerism, and you have optical isomerism. To summarize each, EZ isomerism occurs as a result of restricted rotation about the planar carbon-carbon double bond, whereas optical isomerism occurs when 4 different substituents are attached to one carbon, known as the chiral carbon. And this results in 2 isomers that are non-superimposable mirror images of each other. So EZ isomerism in greater detail now. As we've already said, it occurs as a result of restricted rotation about the planar C double bond C, and it really requires a carbon-carbon double bond with 2 different groups attached to each carbon. Now let's look at a simple example of an EZ isomer. One thing to be aware of is being able to recognize which isomer is the E isomer and which one's the Z. And I find it easiest if I write this statement, that enemies are on opposite sides, and then a second statement, which is Z is the same side. I know this is really weird, but whatever helps get this into your memory. So taking a look at this example here on the left, we've got these groups here, they're on the same side, so this is a Z isomer, whereas over here we have the differing atoms on opposite sides, so we have E isomer, enemies are on opposite sides. But what happens if it's not as straightforward as just looking at these various structures in order to work out which one's the EZ isomer? Well, there's a set of rules that helps you identify it once and for all, and therefore allows you to name them fully. And the set of rules is known as the Kahn-Ingold pre-log nomenclature of EZ isomers. So step 1, consider the right-hand carbon of the C double bond C. The adjacent atom with the highest atomic number takes priority. So we'll have a look here. Here's the right-hand carbon. We're comparing bromine and hydrogen. Bromine has the higher atomic number, so that's going to take priority. Step 2, consider the groups joined to the left-hand carbon of the C double bond C. The adjacent atom with the highest atomic number takes priority. So we're comparing chlorine and hydrogen. Obviously, chlorine has a higher atomic number. And therefore, we can see again that this is the same side. So that's why that is the Z isomer. If both adjacent atoms are the same, consider atoms one bond further away until they differ. Okay, we'll use that particular point when we look at a more complex example. Now we'll take the second isomer. Looking at this molecule now, we're looking at that right-hand carbon. Bromine has a higher atomic number compared with hydrogen. So we're going to highlight that. Looking at the left-hand carbon, chlorine has a higher atomic number compared with hydrogen. And if we sit back, we can see that these atoms are on opposite sides. So they are enemies, hence why it's an E isomer. Then we just get down to naming it. So the name of this is Z1-bromo. That means that this chlorine over here is on the second carbon, 2-chloro, and then we have an ethene here. And then over here, that's how we're naming that fully. We'll now have a look at a more complicated example. So here are two isomers, and it's so much more difficult to work out which one's the E and which one's the Z here, so we're going to use these rules to help us. So step 1, we're considering the groups joined to the right-hand carbon. It's here. The adjacent atom with the highest atomic number takes priority. So at this point, we have carbon on each, so we need to move on again. Do remember how these atoms will be arranged. That carbon will then be attached to this carbon here, whereas this carbon here is just attached to hydrogens. So this carbon means that this group of atoms takes priority. If that's a bit complicated, just look at this side which has more atoms if you're not sure, but that's the reason why we're picking that one. And then step 2, we'll consider groups on the left-hand carbon, and then this one's more straightforward, isn't it? Because that carbon has a higher atomic number than the hydrogen. Because these are on opposite sides, we know that it's an E isomer. In terms of naming this, count the longest carbon chain, 1, 2, 3, 4, 5. Okay, we have a methyl group therefore attached to the third carbon. The longest chain is 5, and there's a double bond in there on the second carbon, so it's 3-methyl pentuene. Let's puzzle through the rules here. So looking at the right-hand carbon, those two match, but then we've only got a hydrogen here as opposed to the carbon here, which has a higher atomic number, which means this one takes priority. Now looking at the left-hand carbon, it's easier to see that this one will take priority. Because they're on the same side, we know we have a Z isomer. The longest chain again is going to be 5 carbons with a methyl group attached to the third carbon. So it becomes Z3-methyl pentuene. Let's quickly recap alkanes. So alkanes are the simplest hydrocarbons. They are all saturated. That means they contain single carbon bonds only. The general formula of the alkanes is CnH2n plus 2. The N stands for the number of carbon atoms. The first alkane is methane. It has a molecular formula of CH4. The second alkane is ethane, molecular formula C2H6. The third alkane is propane, C3H8. The fourth alkane is butane, C4H10. Alkanes are hydrocarbons. This means they consist of hydrogen and carbon atoms only. The main source of alkanes is through the fractional distillation of petroleum crude oil. Now, in order to carry out fractional distillation, you need to heat the crude oil until it forms a gas. The vapour is passed into the bottom of a fractionating column. There's a temperature gradient within the column. It's much hotter at the bottom compared with the top. This means that shorter chains with lower boiling points condense at the top where it's coolest, and then the longer chains with higher boiling points condense at the bottom where it's hottest. In terms of the order of fractions, from the top we have refinery gases. This is bottled gas that we use in our homes, particularly in central heating. Next up we have petroleum. This is used as fuel for cars. Then we have naphtha, used as chemical feedstock. Kerosene is used as fuel for planes. Diesel oil is used for fuel for buses and lorries. Fuel oil is fuel for ships. And bitumen is used for road surfacing and making roofs. Comparing the various fractions, at the top I've already said you'll have the lowest boiling point fractions. These are the most flammable, the most volatile, they're most likely to form a gas, they're lightest in colour, and they're the least viscous because they flow easily. Towards the bottom you'll have the higher boiling point fractions. They're darker in colour, they're less flammable, less volatile, but they're more viscous, and that's because they're stickier. Now, alkanes are non-polar with only weak van der Waals forces between the molecules. The larger the molecules, so the higher the MR, the stronger the van der Waals forces, and that means the higher the boiling point. Alkanes with branch chains have lower melting points compared with single long chains of alkanes, and this is because the branch chains can't pack together as closely as the single branch chains, meaning that the van der Waals forces are weaker because the electron clouds can't be distorted as much. As alkanes are non-polar, they're insoluble in water, they do not dissolve, and alkanes are relatively unreactive because they have strong carbon-carbon bonds as well as carbon-hydrogen bonds. Now, cracking is the process whereby we break down longer alkane chains into smaller, more useful alkanes and alkenes. Alkenes are highly reactive and can be used to make plastics. Products of cracking are then separated using fractional distillation. There are two types of cracking: thermal cracking involving heat and catalytic cracking involving the use of a catalyst. Now, in thermal cracking, a high temperature of between 700 to 1200 Kelvin is needed to break the carbon-carbon and carbon-hydrogen bonds. A high pressure of 7000 kPa is used. Free radical intermediates are formed when the carbon-carbon bond breaks. This is known as homolytic fission, and the products of thermal cracking are largely alkenes. What about catalytic cracking? Here we're using a zeolite catalyst. We use a lower pressure, a lower temperature of around 720 Kelvin, and rather than homolytic fission, we have heterolytic fission. The products of catalytic cracking are largely branched alkanes used in motor fuels and aromatic hydrocarbons. As we've already said, alkanes make great fuels. A fuel is a substance which releases energy when burnt. You can burn the fuels either through complete or incomplete combustion. Complete combustion involves a plentiful supply of oxygen and produces carbon dioxide and water. Incomplete combustion involves an insufficient supply of oxygen. The products here are often carbon monoxide, which is a toxic gas because it combines irreversibly with the hemoglobin in red blood cells, stopping their transport of oxygen. It can also produce carbon, which we see as a black powder known as soot. Water is also produced. In terms of the pollutants produced by combustion engines, we've already mentioned that complete combustion produces carbon dioxide. Carbon dioxide is a greenhouse gas which contributes to global warming. It causes sea levels to rise due to the melting of polar ice caps, the destruction of habitats, and loss of biodiversity. Incomplete combustion may produce carbon soot. As I've already mentioned, this causes global dimming and can exacerbate asthma as well as respiratory problems. Carbon monoxide, I've already mentioned, is toxic. Nitrogen oxides are formed when nitrogen and oxygen react in the high temperatures found in car engines. Nitrogen oxide dissolves in water to form nitric acid. This is an example of acid rain. A second source of acid rain is sulfur impurities present in the crude oil that form sulfur dioxide when the crude oil is burnt. Sulfuric acid forms when the sulfur dioxide reacts with rainwater. This is the second source of acid rain. Acid rain damages trees, makes lakes very acidic for aquatic organisms, and damages limestone buildings. We talked a lot about the various pollutants produced by both the complete and incomplete combustion of hydrocarbons, but how can we reduce these pollutants? Well, two main ways. One, flue gas desulfurization. That means removing the sulfur dioxide from any waste gas. Number 2, catalytic converters, and you need to know a variety of equations here. So let's first of all state that it removes sulfur dioxide from waste gas. In the first equation, we have calcium oxide, which is lime, reacting with water, the waste gas which we want to remove, the sulfur dioxide, as well as oxygen. And then a second method is through calcium carbonate, CaCO3, which remember is limestone, reacts with oxygen, the waste gas sulfur dioxide again, to form calcium sulfate and carbon dioxide gas. Both of these will remove sulfur dioxide, and they're both examples of neutralization reactions. What about catalytic converters? Well, these are fitted in the exhausts of cars. They have a ceramic honeycomb structure. The honeycomb increases the surface area, and the honeycomb contains some very valuable metals, including platinum, which is actually used to make some wedding rings, and rhodium. The honeycomb enables these metals to be used in very small quantities. In the case of catalytic converters, we're removing carbon monoxide, the toxic gas, and nitrogen monoxide, a gas which contributes to acid rain. So if we look at what happens from an equation point of view, the carbon monoxide reacts with nitrogen oxide to form inert, unreactive nitrogen gas and carbon dioxide, which is not toxic. A second example of an equation involves octane reacting with the polluting NO again to produce harmless nitrogen gas, carbon dioxide, and water. Remember that activities that produce no carbon dioxide emissions overall are referred to as carbon neutral, but the whole process needs taking into account to declare a particular activity as carbon neutral, such as the carbon dioxide released by lorries, transporting goods, operating machinery, cutting down trees, etc. Now we're going to do a free radical substitution summary, and this is really relating to the chlorination of alkanes, so adding chlorine to alkanes. You need to learn the list of steps and all the equations here. At IGCSE and GCSE level, you'll have learned that this is a substitution reaction, that it involves UV light, but here we'll see how this actually takes place. There are 3 stages. The first stage is known as initiation, the second stage is propagation, and then the third and final stage is therefore known as termination. So starting with initiation, as a summary, we're going to write, in the presence of UV light, halogens undergo homolytic fission. What that means is that each halogen receives 1 electron from the broken bond, and this is going to produce 2 very reactive free radicals. So as a summary, here's our chlorine molecule. Remember, it's diatomic, and as I've just said, it's going to produce 2 chlorine free radicals, and we use that dot there to represent the free radical. Step 2 is propagation. Here, the free radicals you produced in the initiation step react with hydrocarbons, e.g. methane, forming HCl and a methyl free radical. The original chlorine free radical is reformed when the methyl free radical reacts with more chlorine. So to draw equations to summarize, there's our free radical that we formed in the initiation step. Here it is reacting, in this case, with methane to form HCl, which I already told you, plus the methyl free radical. And then that methyl free radical reacts with more chlorine to form chloromethane. And that chlorine free radical. And then the termination step is just about combining these various free radicals that were formed to form a stable compound. You'll find in propagation that you'll always have a free radical reacting with a stable compound, and it will produce a stable compound and a free radical. In the termination step, you'll always have two free radicals reacting to form a stable compound. And by doing so, they'll end the chain reaction. So let's work out what combos we have. We could take two chlorine free radicals and form your original chlorine again. You could take the methyl free radical and react it with another methyl free radical, or you could take a chlorine free radical and react it with a methyl free radical to form the chloroalkane, which is, after all, what I said this reaction is all about. So if I zoom out, you can see a nice summary of free radical substitution, which enables the chlorination of alkanes through the presence of UV light in the initiation step. Ozone, O3, is a vital component of the upper atmosphere. It's so important because it protects the Earth. How does it do that? It absorbs harmful UV radiation. CFCs are very nasty chemicals indeed. They stand for chlorofluorocarbons. They're found in a lot of fridges and aerosols, and they're super harmful because they cause the breakdown of the ozone. They decompose it into oxygen. And this ozone depletion is an example of free radical substitution. So we can put into practice all those steps we learnt before to do with initiation, propagation, and termination. So in our initiation step, chlorotrifluoromethane is involved. As you'd expect, you need the action of UV light, and this forms two free radicals. In the propagation step, the free radicals formed in the initial step reacts with the ozone, causing its decomposition into oxygen. The second free radical produced reacts with more ozone to produce more oxygen and a chlorine free radical. And this is why we say it's a catalyst, because look, the chlorine free radical is regenerated and is unaffected by the process. So it can do this process again and again and again, and it acts as a catalyst by lowering the activation energy. So I'm really going to spell that out. The chlorine free radical is regenerated and is unaffected by the process. Our overall equation, therefore, for this reaction shows the ozone, O3, being decomposed to produce oxygen. The reason why it's the CFCs that are important here is because that CF bond is very, very strong that we see here, and it's difficult to break. So compounds where fluorine is the only halogen do not cause decomposition to the ozone layer. It's only these CFCs that really cause the main issue. So obviously we know that CFCs have a hugely deleterious adverse effect on the environment, but why wasn't their use banned? Well, firstly, because there was a lack of evidence that the ozone was being depleted. Secondly, because we said that they're used in fridges and aerosols and there were a lack of alternatives. Coupled with that, commercial interest continued in the use of CFCs. And really, to make a difference, we need multiple countries to agree to a ban, and that was difficult to get. Let's look at some past paper questions. Halogens are used to make halogenated organic compounds. The refrigerant used in air conditioners is a mixture of fluorinated alkanes. These compounds are made by fluorination reactions. The mechanism for the reaction of fluorine with an alkane is a free radical substitution, similar to the reaction of chlorine with methane. Write the overall equation for the reaction of fluorine with methane to form trifluoromethane. Just to remind you, with the chlorine and methane reaction, remember we had chlorine reacting with methane to produce HCl and CH3Cl. So that was our overall reaction. Let's use that to help us with this particular equation. There's fluorine, it's reacting with methane. We're making HF this time plus CHF3. And now to balance. Let's balance our hydrogens. First of all, we have 4 over here, only 2 over there, So I'm going to start by adding a 3 here. So 3, 4, 4 H's versus 4 H's. We now have 6 F's over here, which means we need to write 3 here. Write equations for the following steps in the mechanism for the reaction of fluorine with trifluoromethane to form tetrafluoromethane. So our initiation step, this is, remember, when we're going to form our free radical. So we start with the halogen in question in order to form the fluorine free radical. We take that fluorine free radical and react it with CHF3 to form HF plus CF3 free radical. Our second propagation step is taking that free radical we just formed and reacting it with more fluorine to produce CF4 plus a fluorine free radical. And then a termination step, make sure it's the one that produces hexafluoroethane. So we'll just take 2 of these free radicals. CFCs were used as refrigerants. In the upper atmosphere, UV radiation breaks down bonds in CFCs to produce reactive intermediates that catalyze the decomposition of the ozone. An example of a CFC is this. Draw the displayed formula. Let's start with the ethane bit. That's 2 carbons. Here's your first carbon, here's your second carbon. We know that we've got 2 fluorines and they're both going to be on the second carbon. And then over here, we know we have 3 chlorines and they're all on the first carbon. And then fill up with hydrogens. Identify a bond in a CFC that is broken by UV light to produce a reactive intermediate. Give the name of this reactive intermediate that catalyzes the decomposition of ozone. Write an overall equation for this decomposition of ozone. So remember, it's the breaking of the CCl bond because the CF bond is too strong. The name of the reactive intermediate, let's name it, it's the chlorine free radical. And the overall equation, remember, takes us from O3 to O2. Chloromethanes, such as dichloromethane and trichloromethane, are produced in industry as they have many uses. Trichloromethane has been used in the manufacture of the refrigerant chlorodifluoromethane. Chlorine can react with dichloromethane to form this. Write an equation for each of the following steps. So the initiation step is always just taking a halogen to form the free radical. The first propagation step is taking that free radical formed, reacting it with the compound they've told us about to form HCl. And then this is your free radical. Second propagation is taking that second free radical formed and reacting it with more chlorine to produce the chlorine free radical plus CHCl3. As always, you've got in the propagation step a free radical on each side of the equation arrow. Give one essential condition and name the type of mechanism. It's UV light and it's free radical substitution. Explain with the aid of equations and the intermediates that form in the ozone layer why the EU has banned the use of CHClF2 as a refrigerant. So why has it banned the use of CFCs? Let's just write exactly what happens. In the presence of UV light, Cl-Cl bond or carbon-chlorine bond breaks, forming the nasty chlorine free radical. This acts as a catalyst, and then that chlorine free radical reacts with the ozone layer, producing a second free radical and oxygen. That second free radical reacts with more ozone to form more oxygen plus a chlorine free radical. So the fact that the chlorine free radical is regenerated shows that it's acting as a catalyst, giving our overall equation as follows. The compound BLA is the refrigerant used in all new car air conditioners. Draw the displayed formula. So we'll start with propene at the end. So that's 3 carbons. We need the double bond because it's an alkene. We know that we have 4 fluorines and they're on the second and there's 3 of them on the third. So there's the third carbon. And then fill up with hydrogens. Give one reason why this is a more environmentally acceptable refrigerant. It's because that CF bond is much stronger than CCl. So no free radical is formed. The refrigerant R410A used in air conditioners is a mixture of two fluoroalkanes. The mechanism for the reaction of fluorine with either an alkane or a fluoroalkane is similar to that for the reaction of chlorine with methane. Name the type of mechanism for the reaction of chlorine with methane. Free radical substitution. Write equations for the following steps and the mechanism for the reaction of fluorine with fluoromethane to form this. So our initiation step is taking fluorine to produce two fluorine free radicals. Our first propagation step is taking the free radical formed, reacting it with our reactant CH3F to form HF plus a free radical. Our second propagation step is taking CH2F, reacting it with more fluorine to produce another fluorine free radical plus CH2F2. And then the termination step, ensuring that we form 1,2-difluoroethane. We'll take two of these free radicals, and sure enough, you'll make CH2F, CH2F, which is difluoroethane. There's your two carbons, there are your two fluorines. Write an overall equation for the reaction of fluorine with ethane to form this. There's fluorine, here's ethane. We know we make HF. Let's get it balanced. So we're going to add a 5 in front of fluorine and a 5 in front of HF. And then we're being asked to find the IUPAC name for this. I'm just going to draw it quickly to show you. And then in terms of naming, we have two carbons, so we have an eth. How many chlorines do we have? There's 4 of them. They're on the first and the second. Remember to keep it in alphabetical order. So it becomes 1, 1, 1, 2 tetrachloro. Never have enough space. 2, 2 difluoroethane. Halogenoalkanes are more reactive than alkanes. And the reason for that is because they contain polar bonds. So just to show you in bromomethane here, this bromine is slightly negative, it's electron rich. This carbon is electron deficient, it has a slightly positive charge, and that means that that whole bond there is polar. In terms of the kind of reactions they can undergo, halogenoalkanes can undergo nucleophilic substitution reactions as well as elimination reactions. General properties of the halogenoalkanes: they are insoluble in water, and their boiling point increases with increasing carbon length chain. Halogenoalkanes have the general formula of CnH2n plus 1x, and that x represents the halogen. Now the carbon attached to the halogen bond gets weaker as you descend group 7, and that's because the halogens are larger, meaning that the outer shell electrons are further from the nucleus, and that therefore helps to explain why the reactivity increases down the halogen group. So the CX bond as you descend group 7. In terms of understanding how the halogenoalkane is involved in reactions, this electron deficient carbon is going to be very important because it's likely to be attacked by reagents that have electron rich areas. So that could be something like a negative ion or a compound containing a lone pair of electrons. These negative ions and lone pair of electrons are known as nucleophiles, hence the use of the word here, nucleophilic substitution. How do we distinguish between primary, secondary and tertiary halogenoalkanes? So starting with the primary. This is identifiable because the halogen is situated at the end of the carbon chain. You'll also expect to see the carbon in the carbon-halogen bond is attached to another carbon. So there's the carbon of the carbon-halogen bond. So as we can see here, it's attached to another carbon, and that's the easiest way of identifying a primary halogenoalkane. Let's practice naming this one. The longest carbon chain contains 3 carbons. There's a bromine on the first carbon, so it's 1-bromopropane. Turning our attention now to identifying secondary halogenoalkanes. So as you might expect, the halogen is attached to the second carbon. So it's located in the body of the carbon chain. This time the carbon in the carbon-halogen bond is attached to 2 carbons. Let's name this. Longest chain again is 3-propane. There's a bromine attached to the second carbon, it's 2-bromopropane. And then finally, our tertiary halogenoalkanes. The main thing to notice here is that the carbon in the carbon-halogen bond is attached to 3 other carbons. So there it is, look, it's attached to 3 other carbons. There's the halogen, complete the structure. Longest chain is 3-propane. Notice we have a bromine and we have a methyl group, get it alphabetical. So it's going to be 2-bromo, 2-methyl, propane. I'm going to run you through the nucleophilic substitution reaction mechanism, showing you the reactions which occur with hydroxide ions, cyanide ions, and lastly ammonia. It's always useful to bear in mind what various words mean. So what is a nucleophile? Why is it called nucleophilic substitution? It's because a nucleophile is an electron pair donor. So examples of nucleophiles include OH-, CN- and NH3, ammonia. Nucleophilic substitution reactions involve halogenoalkanes. I'm going to take you through an example of the hydroxide ions reacting with bromoethane. So there's your halogenoalkane. And you want to follow these steps when you're asked to outline the mechanism. So we'll start with the displayed formula bromoethane. There's 2 carbons. We have a bromine attached. I'm going to complete with hydrogens. We now need to add our nucleophile, which I've just told you is the OH-. Do make sure you show the lone pair of electrons on the OH-. The next important thing is to show the fact that the bromine here is electron rich, so it's delta negative. This means that the carbon here is electron deficient, so it's delta positive. You must always draw curly arrows here, and it must start from the lone pair, and it's attacking the carbon here. This causes the breakage of this bond, and so we can now draw the second stage of the mechanism. The bromine has been substituted for the OH, hence the name of this mechanism, nucleophilic substitution. We've lost this bromine here, so we need to draw it as the product, and it has a lone pair of electrons. We've taken our bromoethane, and actually what we've done here is produced an alcohol, which is ethanol. They might ask you about various reaction conditions. With hydroxide ions, you need aqueous ethanol to be used as a solvent. This time we're looking at cyanide ions and chloroethane. So a second example of nucleophilic substitution. It's very similar from what we've just done. We'll start with the chloroethane. This time we've got a slightly negative chlorine, a slightly positive carbon. Let's show the cyanide ion. Remember, that is a triple bond. It has a lone pair here. It's negatively charged. We know the lone pair will attack at this electron deficient carbon, causing the breakage of this bond. Draw the new product form. In terms of naming, we have gone from chloroethane, but look here, we now have 3 carbons, so the carbon chain has increased. So we have propane. And then remember, it's very important when you're naming nitriles, you include that E. So we have propane nitrile over here. You might be asked about the source of the cyanide ions. These are produced by potassium cyanide in aqueous ethanol. I will write that here for you. We avoid using hydrogen cyanide because it produces a toxic gas. And then our third example of nucleophilic substitution is this time with ammonia. I'm going to take chloroethane as my halogenoalkane. In terms of conditions, we need excess concentrated ammonia in ethanol. The reason why it needs to be in excess is to minimize further substitution occurring. So let's show the mechanism. Here's chloroethane. Here's my slightly negative chlorine, slightly positive carbon. Let's show the bonds on the ammonia. There's no charge, it's neutral, but it does have that lone pair. That's going to attack the slightly positive carbon, causing the breakage of this bond here. And then this nitrogen is positive. We can't leave it like this, so that's why the excess ammonia is needed. The lone pair is going to attack one of the hydrogens. Doesn't matter which one, causing the breakage of that bond to form this is the final product. So we've lost one of the hydrogens. We have an NH4 plus an ammonium ion left over, as well as a halide ion. This could also be represented as an ionic compound like this. So be warned. What is the name of this substance? It's got 2 carbons. It's got an amine group. It's ethylamine. The reason why this is a slightly different example compared with the 2 above is because before you had a negative ion donating an electron and therefore becoming neutral, as we see here, whereas here you have a neutral molecule, ammonia, which donates an electron pair, and that's why it becomes positively charged. So it is important that you're aware that each step of a reaction mechanism must balance, both in terms of atoms and charges. Bromoethane reacts with potassium cyanide to form compound D. Outline the mechanism for this reaction. Remember that this is a nucleophilic substitution reaction. It's important you know the name of the reaction because it will help when it comes to drawing out your mechanism. So I'm going to draw the displayed formula of the bromoethane to make it easier to see. Here's your all-important nucleophile with that lone pair of electrons, which is going to do the attacking. Label your electron-deficient carbon, your electron-rich bromine, and then show the lone pair attacking the electron-deficient carbon. So there's my curly arrow, and that's going to cause the breakage of this bond here. This allows the CN to join and replace the Br. You can see very clearly here that the carbon chain has increased in length by 1, and we'll have a Br minus left over with a lone pair. Now we need to name this. So as I've already said, we have 3 carbons. This here represents a nitrile, so we have simply propane nitrile. Don't forget that you've got to put that E in there. That's the difficult thing when it comes to naming nitriles. 2-methyl-propan-1-ol can be prepared by reacting 1-bromo-2-methyl-propane with dilute aqueous sodium hydroxide. Name and outline the mechanism. Again, we have nucleophilic substitution. Be very careful. Here's your reactant. So start with your 3 carbons. We know we have a Br group on the first carbon. We know we have a methyl group on the second carbon. I'm just going to draw it like that because it won't be involved in the reaction. I'm going to complete my hydrogens. Now I'm going to draw my nucleophile, the OH, minus. There's the lone pair. There's my slightly positive carbon, slightly negative bromine. We know the lone pair will attack the slightly positive carbon, causing the breakage of this bond. The hydroxide adds itself. The rest of the molecule remains unchanged. And we're left with a Br minus. Previously, we looked at nucleophilic substitution reactions and halogenoalkanes. This time we're looking at elimination reactions. So we need to ask ourselves, why do elimination reactions occur? And that's due to a change in conditions. For elimination reactions to occur, we need hot ethanolic conditions. And I can hear you say, what does that mean? It means that there's no water present. We're still using hydroxide ions, but due to these hot ethanolic conditions, the hydroxide ions act as a base. Remember, a base is a proton acceptor. So we're going to take the reaction of bromoethane and hydroxide ions. Here's our bromoethane. Here's our hydroxide ion, still with its lone pair. The lone pair is going to attack one of the hydrogens surrounding the carbon not attached to the bromine. And then what you'll find happens next is the electrons from the carbon-hydrogen bond move to form part of a C double bond C. And we're going to lose this bromine. It's going to be eliminated as a halide ion. So the key difference here is in an elimination reaction, because you're eliminating an atom, you're going to introduce a double bond, and actually we go from bromoethane to ethene. Don't forget your byproducts, and there's your halide ion. So elimination reactions in halogenoalkanes produce alkenes. And you can see that the carbon in the CX bond, in this case the X is bromine, goes from having 4 bonds attached to just 3, and that means that one must have been eliminated. Now these elimination reactions occur more readily in secondary and tertiary halogenoalkanes. So remember, that's when your carbon is attached to 2 carbons, and then the tertiary halogenoalkane is when that central carbon is attached to 3 carbons. So elimination reactions are far more likely with secondary and tertiary halogenoalkanes. If you have a primary halogenoalkane, it's more likely to partake in the nucleophilic substitution reactions we met earlier. Do be aware though that a mixture of isomeric products is sometimes possible in an elimination reaction. I'll show you how now. So we're going to start with 2-bromo-2-methyl pentane. There's our halogenoalkane. So we have 5 carbons in a line. We've got bromine on the second carbon and a methyl group on the second carbon. Just to point out, look, that central carbon there is attached to 3 carbons, so it's a tertiary halogenoalkane. So to show how isomeric products may be formed, I'm going to show you what happens in this case when the lone pair attacks this hydrogen here, forming the double bond down there, and we lose this bromine. So there's the formation of our double bond. Then continue the chain. So in this case, let's name it. The longest chain has 5 carbons. The double bond is on the first carbon, so it's pent-1-ene. And then we have a methyl group on the second carbon, so it's 2-methyl pent-1-ene. But let's take scenario 2 with 2-bromo-2-methyl pentane. So we have 2-bromo-2-methyl pentane again. But this time, rather than attacking this hydrogen here, I'm going to attack this hydrogen over here. So my double bond will form here instead. So because it attacked a different hydrogen, in this case, we have formed 2-methyl pent-2-ene. And do draw that full displayed formula if you're not sure how I'm naming that. So we can see what's happened here is that because our halogenoalkane was asymmetric, a mixture of products can be produced depending on which hydrogen is removed. And don't forget that our conditions here are hot and ethanolic. Haloalkanes are used in the synthesis of other organic compounds. Hot concentrated ethanolic potassium hydroxide reacts with 2-bromo-3-methyl-butane to form 2 alkenes that are structural isomers of each other. The major product is 2-methyl-but-2-ene. Name and outline a mechanism for the conversion of 2-bromo-3-methyl-butane into 2-methyl-but-2-ene according to this equation. So the name of the mechanism, it's an elimination reaction. So let's start by drawing 2-bromo-3-methyl-butane. Here's our hydroxide ion. You do need to bear in mind your final product to make sure that you are actually making 2-methyl-butenes, so that will dictate which hydrogen the lone pair attacks. It will cause the formation of the double bond there, and we'll lose this bromine. That will be eliminated. So to draw the product, here's our double bond forming, and then everything else remains the same, noticing we've lost the bromine. And here are our remaining products, including the halide ion. So just to double check, have we produced the right product? 4 carbons, the double bond is on the second carbon, yes. So there's our butene, and the methyl group is on the second carbon. Draw the displayed formula for the other isomer that is formed. Okay, so let's attack a different hydrogen. How about if we were to attack this hydrogen over here? Well, then you'd get your double bond forming here. And then state the type of structural isomerism shown by these 2 alkenes. Well, the functional groups moved along, so it must be positional isomerism. Reaction of A with hot ethanolic potassium hydroxide gives alkane C. This is A, by the way. Name the mechanism, state the role of the hydroxide ions, outline the mechanism using structure of A shown, include the structure of the product C. So it's elimination. I already taught you previously that the hydroxide ions in this case are acting as a base. Here we're going to outline the mechanism. Look for where your halogen is attached. I'm going to attack this hydrogen here using the lone pair. There's my curly arrow, causing the double bond to form here, and we'll lose the chlorine. It will be eliminated, and then just replace your atoms. Here's your double bond. That hydrogen remains. Alkenes are unsaturated hydrocarbons. Remember, that means they contain a carbon-carbon double bond. Like alkanes, they are hydrocarbons. This means they consist of hydrogen and carbon atoms only. Don't forget their general formula, CnH2n, where n equals the number of carbon atoms. There's no such thing as an alkene with 1 carbon atom because you need a minimum of 2 to accommodate the double bond. So in effect, the first alkene is ethene. Here's its displayed formula. C2H4 is its molecular formula. Then I'm going to draw propene next door. C3H6. And then you have butene, pentene. And when you get to butene and pentene, etc., you need to start specifying where the double bond is. So just to show you, if the double bond here is on the first carbon, then you have but-1-ene. If you move it to the second carbon, then it becomes but-2-ene. Some more key notes here. Alkenes are non-polar. They have only weak van der Waals forces between the molecules. Notice that the larger the molecule, so something like but-2-ene compared with ethene, but-2-ene will have stronger van der Waals forces, meaning that they have a higher boiling point. You'll find that alkenes with branch chains have lower melting points than straight chain alkenes, and this is because the branch alkenes can't pack together as closely, meaning that the van der Waals forces are weaker. This non-polarity means that they are insoluble in water, and then the presence of that C double bond C means that they are fairly reactive because they will be attacked by electrophiles, and we're going to talk a lot about electrophilic addition reactions. If we look more closely at the shape and properties of alkenes, I'm taking ethene again. You'll find that there's restricted rotation here around the double bonds, and that explains why alkenes can have geometric isomers. And geometric isomer just refers to the fact that these compounds have the same molecular formula but a different arrangement of atoms in space. There's that C++C, which has a high electron density, meaning that they can partake in electrophilic addition reactions. You'll find that the C++C is planar, and that means you have bond angles of approximately 120 degrees. In terms of bond length, you'll find that the single bonds have longer bonds compared with double bonds, and you'll find that single bonds are weaker in strength compared with double bonds. Don't forget that alkenes burn in excess oxygen in complete combustion reactions to form carbon dioxide and water. So as I've already mentioned, alkenes partake in electrophilic addition reactions. You'll probably have met this at IGCSE and GCSE. You'd be given something like ethene, and then you'd be told that it would react with a halogen such as bromine, and then an addition reaction would occur where the bromine molecule is added to the alkene. But at A level, we just need to take that step further and show the actual mechanism. So in terms of these electrophilic addition reactions, there's three kinds they could ask you about. The reaction of alkenes with hydrogen halides, such as HBr. Reaction with halogens, like the example I just showed you, such as Br2. And then lastly, with concentrated sulfuric acid, H2SO4. The mechanism will be the same for each. Don't stress about it, you just need to learn the method and then you can apply it to whichever reaction they ask you about. So let's go with the reaction of ethene with the hydrogen halide HBr. So here's our ethene drawn out as a displayed formula. It's reacting with HBr. Notice that this is an electrophilic addition reaction, so it's always worth knowing what these words mean. So an electrophile is an electron pair acceptor, such as H+, HBr. So here's our electrophile, and it's going to accept a pair of electrons from this double bond. According to this definition, it is an electrophilic addition reaction. We'll use our all-important curly arrows to show the movement of electrons. Remember that the bromine here is electron rich, so it's slightly negative. Hydrogen is electron deficient, so it's slightly positive. We're going to show the movement of electrons from the double bond to the electron deficient hydrogen. This curly arrow here represents the breaking of a covalent bond. So what you can see, it's a kind of game of spot the difference. What you can see is that a new CH bond is formed by one carbon in the double bond, this one here, and the other carbon is left with a positive charge. This carbon that's positively charged is known as a carbocation. You'll also notice the formation of a negatively charged ion, in this case a bromide ion, and it forms a bond with the carbocation intermediate. So we're going to show a curly arrow going from the lone pair here to the carbocation intermediate. So then our final product looks like this. And so our final product here is called bromoethane. Let's take a second example now. We're now going to have a look at ethene reacting with a halogen bromine. So showing how that GCSE and IGCSE reaction is brought about. So here's our displayed formula of ethene again. We have our electrophile, this time it's bromine. Now you have a delta positive bromine and a delta negative bromine, and the reason for this is because at any instant a halogen molecule will have an instantaneous dipole. The electrons in the alkene double bond here are attracted to the delta positive bromine and they repel the electrons in the Br-Br bond, which strengthens the dipole of the bromine, really meaning that that delta positive and delta negative is established. So that's the reason why we draw this. So it's exactly the same mechanism as before. So now we'll look at our intermediate. We know from the previous example we'll have a new CH bond formed around the double bond. There's our carbocation intermediate, and then the bromide with the lone pair, which attacks the carbocation here to form our final product. And this really does show the addition of that halogen. Always bear in mind the end goal. And so if we were to name this, we have 1,2-dibromoethane. And just remember, this reaction here can be used for the test of a double bond, for the test of an alkene. When you add ethene to bromine water, it should turn from orange to colourless because you no longer have the presence of that bromine. Let's take an example now with ethene and concentrated sulfuric acid. You'll see it's exactly the same mechanism. Do pause this video and practice doing this without me. You might struggle a little bit though with the sulfuric acid displayed formula. It is quite difficult because you do really want to show all the bonds so you can show the movement of electrons. First of all, we want to work out which atom is slightly positive and slightly negative. So this oxygen here will be slightly negative. This hydrogen here will be slightly positive. Add your curly arrows in exactly the same place as the previous examples. Make sure you add that hydrogen to one of those carbons in the double bond. There's your carbocation. Draw this nice and carefully. And then your final product looks like this. And this is called ethyl hydrogen sulfate. The only slight complication comes if we have an unsymmetrical alkene. So obviously ethene was the most straightforward mechanism we could look at. But what happens if you have something like propene? You can clearly see when I finish drawing the displayed formula is asymmetric. What happens here is that you can produce two possible products. So just to write a couple of notes, there are going to be two possible products. We call one of those products the major product. That means that there'll be more of it produced. And one of them the minor. And it's important that you know the major product comes from the most stable carbocation intermediate. And you find that it's the tertiary carbocation which is more stable than the secondary, which is more stable than the primary. So when we look at the intermediate, we'll have to identify if it's primary, secondary or tertiary, and then based on that, that will tell us if it's the major or minor product, but it will be far more straightforward if we look at an example now involving propene. So I'm going to react propene with hydrogen bromide, label the bromine as slightly negative, hydrogen as slightly positive. We know that the curly arrow runs from the double bond to the hydrogen, breaking that covalent bond. Because it's an asymmetric alkene, we have two possible carbocation intermediates. Here's the first one. Here's the second one. Just have a look at them, what type of carbocation they are. Look, it's attached to two carbons, so it's a secondary carbocation. This one down here is only attached to one carbon, which means it's primary. According to the rules I just specified, it means that this one is the more stable intermediate, meaning that it will produce the major product. Remember that you're going to have that halide ion with its lone pair that attacks the carbocation. Same is true down here. So then the final products, let's name them. The bromine's on the second carbon, so we have 2-bromopropane. Here the bromine's on the first carbon, we have 1-bromopropane. Just to repeat, this is the major product, this is the minor product. If they ask you for a reason as to why this is the major product, it's because of the positive inductive effect, which is when the alkyl groups, the hydrocarbon chains, release electrons to stabilize the positive charge of the intermediate carbocation. I will write that for you. But-1-ene reacts with a reagent of the form HY to form a saturated compound, suggest a reagent of the form HY which reacts with but-1-ene. So you need an electrophile because remember this is an electrophilic addition reaction. And what I just taught you was you could either have a halogen, a hydrogen halide or sulfuric acid. Because they want it in the form HY, you're going to have to use the hydrogen halide or sulfuric acid. So I'm just going to go for HBr here, hydrogen bromide. Name and draw a mechanism. So I already said it's electrophilic addition. So we'll start with but-1-ene. Here's my HBr. Br is slightly negative, H is slightly positive. Just draw my curly arrows in the correct place. There's my carbocation. There's my bromide ion with its lone pair that attacks the carbocation. And there's my final product. Isomer 4 reacts with hydrogen bromide to give two structurally isomeric bromoalkanes. Name and outline a mechanism for the reaction of isomer 4 with hydrogen bromide to give 2-bromo-2-methyl-butane as the major product. So there's isomer 4. The name of the mechanism, electrophilic addition. Here's my HBr, slightly negative Br. Let's now draw our carbocation. Remember, we need the more stable intermediate, so we need one that's the tertiary version. If we count these carbons here, we can see that that is a tertiary carbocation. Here's our bromide ion attacking that carbocation. And then just double check. Do you have 2-bromo-2-methyl-butane? You have 1, 2, 3, 4. And the methyl group and the bromine are both on the second, so yes, you do. The minor product in this reaction is a mixture of 2-bromo-3-methyl-butane. Explain why this bromoalkane is formed as a minor product. So you just want to say this reaction involves a secondary carbocation intermediate, which is less stable than the tertiary one above. Now we're going to talk about addition polymers. This really means when alkenes join together to form plastics, polymers. A small subunit, the alkene, is known as a monomer, joins to form a large molecule polymer. Let's look at some various examples. So starting with the simplest, here's our first monomer, ethene, C2H4. When many ethene molecules join together, they form polyethene, polythene. In order to draw that polymer, you need to break the double bond, elongate the bonds, add the hydrogens back in, and add square brackets. The N represents the fact that there's an awfully large number of these repeat units. They could ask you for uses of polythene. You'd want to say something like carrier bags and washing up bowls. What about if you have propene, C3H6? There's the monomer propene. Many propene monomers join together to form polypropene. Again, we break that double bond, elongate the bonds, add everything else back in, include square brackets. Your use of polypropene or polypropylene is yogurt pots and car bumpers. What about if you had chloroethene? So one of the hydrogens is replaced with chlorine. Same old story, break the double bond. This is polychloroethene. And this is used to make drain pipes and vinyl records. Do remember that addition polymers such as these are very unreactive, they're inert, and the reason for that is because they're non-polar chains. They have lots of strong carbon-carbon bonds, and as a result, addition polymers are non-biodegradable. Remember that biodegradable means that something can be broken down using microorganisms. So these plastics here, the addition polymers, can't be broken down through the action of microorganisms, which means they contribute to landfill, so they occupy landfill, and they release toxic gases when burnt. Sometimes you're asked to deduce the addition polymer from the monomer. So this is a good example. Give an equation showing the structural formulas for the conversion of this into the corresponding polymer. So we're including an N on the left-hand side to show that many monomers are involved. Here's my structural formula. And then it's just the same as before. Break that double bond, elongate the bonds, And in terms of naming, here's 2-methyl-butene. Why? Because the double bond occurs between the second and the third carbon, and the methyl group here is attached to the second carbon. What do we have over here? We have poly 2-methyl-butene. If they ask for the repeat unit, you're simply drawing the smallest group of atoms that produce the polymer when repeated over and over. So basically you repeat this, but there's no need for the square brackets or the N. Sometimes they ask you to deduce the monomer from the polymer. So here's our polymer in question. In the question, they tell you that the particular polymer has been produced from 2 different alkene monomers. So you just have to work out, draw a dotted line where the 2 monomers separate. Remember that each monomer, being an alkene, must contain a minimum of 2 carbons to form that carbon-carbon double bond. So it makes sense there for me to draw a dotted line there, and then I'm going to add the double bonds back in, making sure I obey the rule that each carbon forms 4 bonds, each hydrogen forms 1 bond. Now we'll turn our attention to alcohols. Remember, they have the functional group of OH. In terms of their general formula, it's CnH2n plus 1 OH. That functional group is there. Now, the OH group in alcohols means that hydrogen bonding occurs between molecules. Remember, hydrogen bonding occurs between hydrogen and a highly electronegative element, such as oxygen. Alcohols therefore have higher melting and boiling points than alkanes of similar relative molecular mass, because hydrogen bonds, remember, are stronger than London forces, van der Waals forces. Short chain alcohols are soluble in water, again due to the presence of that hydrogen bonding. Longer chains are less soluble, and that's due to the extra long non-polar hydrocarbon chain present in those longer chain alcohols. But how do we go about naming alcohols? We'll start with the primary alcohols. So this is a primary alcohol because the OH functional group is attached to a carbon that itself is only attached to one other carbon. Let's name it. Well, this functional group is attached to the first carbon. We have 3 carbons, so it's propan 1-ol. What about a secondary alcohol? This time we're going to attach that OH group to the second carbon. That carbon here is attached to 2 carbons, hence why we have a secondary alcohol. The name of this alcohol is propan 2-ol. And now tertiary alcohols. What you can see true of a tertiary alcohol is the carbon that the functional group is attached to 3 other carbons. Let's name it. The longest chain has 3 carbons, so it's prop. The alcohol is on the second carbon, so it's propan 2-ol, but we have a methyl group also attached to the second carbon, so it's 2-methyl propan 2-ol. If you have 2 H groups, you have a diol. If there are 3, you have a triol. So let's name this. 3 carbons in a row, so propan, and we have the alcohol functional group on the first and second carbon, so it's propan 1,2-diol due to the presence of the 2 OH groups. Skeletal formulas, I know people find this difficult. In terms of how we go about naming this skeletal formula, notice we've gained another functional group. We've got the alcohol functional group, but we've also got a carboxylic acid. And what happens then is we use hydroxy to represent the alcohol. Count the number of carbons. It's 1, 2, 3, 4. So we have butanoic acid representing that carboxylic acid, and then we have the alcohol functional group present on the third carbon because we're counting in this direction 1, 2, 3. So it's 3-hydroxy butanoic acid. That is difficult. There's 2 methods of producing alcohol you need to be aware of that you'll have met at IGCSE and GCSE most likely. The first one is the hydration of ethene. That means adding water to ethene. Fermentation is your old school approach for making alcohol. So be aware that your raw material for the hydration of ethene is obviously ethene, and this comes from crude oil, which means it's a non-renewable resource. This will run out. As I've already said, ethene is then hydrated. Water is added across the double bond by reacting with steam. We need a catalyst of concentrated phosphoric acid. The reaction is fast, it's continuous, it makes the ethanol continuously, and the ethanol produced is pure. This is in comparison with fermentation. Fermentation uses sugarcane containing glucose as its raw material. Because that sugarcane is grown, we can say that it's a renewable resource. You're going to add yeast because the yeast contains the enzyme zymase, which causes the conversion of glucose into ethanol due to the anaerobic respiration of that yeast. Remember, anaerobic refers to the lack of oxygen. We need an optimum temperature for the enzymes of 35 degrees. As a result of this lower temperature, we're going to have a low rate of reaction. A batch process takes place, and we're going to have an impure product, which we can purify through use of fractional distillation. Let's look at a mechanism for making ethanol through the hydration of ethene. So here's my ethene displayed formula. We've got the presence of H+. Remember, acids such as phosphoric acid, sulfuric acid are H+ donors. So that's where the H+ comes from. It's going to act as an electrophile, which remember is an electron pair acceptor, which is why the curly arrow goes from the double bond to the H+ ion. As I showed you in electrophilic addition, we have the addition of a hydrogen to one of the carbons in the double bond. We have the formation of a carbocation. And then just be careful here, withdrawing the water, which I said was also present in the hydration of ethene. That oxygen molecule is delta negative. This hydrogen here is delta positive. The lone pair on the water attacks the carbocation, another curly arrow. Now, because that oxygen is positively charged, we have the movement of the electrons in this bond to the oxygen. I feel like I take up so much space, but here's your final product. As you'd expect an alcohol, it's ethanol due to the two carbons, and that H+ is regenerated, hence why it's acting as a catalyst. And then in terms of a high yield, you want a high temperature of 450 degrees Celsius and a high pressure of 75 atmospheres. I'm just going to write the equation for fermentation up here. If you do biology, you'll probably be familiar with it. But we're going to first of all show the formation of glucose by the sugarcane through photosynthesis. So carbon dioxide reacts with water to form glucose, C6H12O6, plus 6 lots of oxygen. And then we take that sugarcane, that glucose, and through the anaerobic respiration of yeast, you produce ethanol plus carbon dioxide. Remember, yeast can be used to make bread dough rise due to the production of carbon dioxide. We must keep that temperature of around 35 degrees Celsius to stop the yeast from denaturing. And then I've stolen this from the revision guide I've written, available on the website SWH Learning. Carbon neutrality. So when the ethanol produced by fermentation is burnt in oxygen, so complete combustion, as you'd expect, carbon dioxide and water is produced. This means that for every 6 moles of carbon dioxide absorbed from the atmosphere by photosynthesis, which remember was responsible for making the glucose, 6 moles of CO2 are released. That's due to 2 moles from anaerobic respiration and 4 from combustion. The use of ethanol as biofuel can therefore be said to be carbon neutral, as there's no net gain of carbon dioxide into the atmosphere. However, we can challenge this due to the various processes involved in planting the sugarcane, harvesting it, transporting it. Often those vehicles involve the burning of fossil fuels, which remember releases carbon dioxide. So it's probably unfair to say that using ethanol as a biofuel is entirely carbon neutral. Now, I've already said that fermentation produces impure ethanol. So how can we purify it? Well, we can use fractional distillation. So here's our impure ethanol containing water. Remember that water has a boiling point of 100 degrees. Whereas ethanol's boiling point is much lower at 78 degrees. So what happens when you heat that round bottom flask is the ethanol vaporizes first, it passes up the fractionating column, and then the water and ethanol are separated in the column because the water condenses back into the flask. Let's consider the oxidation of alcohols. And the type of substance produced by the oxidation of alcohols will very much depend on if you've got a primary alcohol, secondary alcohol or a tertiary alcohol, because primary alcohols, remember, are oxidized to form aldehydes, which can further be oxidized to form carboxylic acid. Whereas those secondary alcohols will go on and produce ketones. And then the thing about the tertiary alcohols is that they're not easily oxidized. So I like to kind of use this basic flow diagram just to remind myself, okay, the primary alcohols will first of all be oxidized to aldehydes. They can then be oxidized to form carboxylic acids. In order to enable that further oxidation, you're going to need the reaction condition of heating under reflux. Secondary alcohols are oxidized to form ketones, and those tertiary alcohols will not easily be oxidized. So we're going to look more carefully at some of the required practicals. So the oxidation of ethanol, which is a primary alcohol, to form the aldehyde ethanal. So there's our primary alcohol, ethanol, and our aldehyde ethanal. Be aware of those functional groups for me. So what's our method to do this? Well, you're going to use distillation. You're going to need to remember the reactants are sulfuric acid and potassium dichromate 6. So these are going to be mixed with your primary alcohol. So if we go over a simple method, our mixture is going to be heated. If we take our ethanol, this represents our oxidizing agent, which is potassium dichromate 6, produces ethanal, our aldehyde. Notice the state symbols. I'll just label these quickly. So there's your ethanol. Here's your ethanal. Now the ethanal that forms vaporizes as soon as it's formed and is distilled off immediately. And why is that? Well, it's to prevent further oxidation to form the carboxylic acid, ethanoic acid. I just want to show you a diagram from our beautiful revision guide that's available on the website. So a few things to notice with the apparatus. First of all, the water bath is used as opposed to a naked flame because that ethanol alcohol is highly flammable. We have anti-bumping granules present in the pear-shaped flask to prevent very large bubbles forming, which would potentially mean that the mixture boils over and contaminates our distillate, which is in this case the ethanol aldehyde. Here's the condenser with cold water running through it in order to help that ethanol turn from a vapor back into a liquid. Notice the colour change, and this is commonly used to differentiate a primary and secondary alcohol because you see a colour change from orange to green. Now we want to talk about the oxidation of ethanol to ethanoic acid. So we're going from that primary alcohol to a carboxylic acid. So the name of this method is reflux. So the key thing to notice here is that it's an excess of acidified potassium dichromate 6. And that's going to be mixed with the ethanol. The method point you need to be aware of is that this mixture is heated gently under reflux. But what does this heating under reflux really mean? Heating under reflux basically means that none of that ethanol that's produced escapes. It's effectively forced to stay within the round bottom flask until all of it is oxidized to form ethanoic acid. So in terms of the stages of oxidation, you go from ethanol to ethanal to ethanoic acid. So that takes you from your primary alcohol to your aldehyde
to your carboxylic acid. Here's the structural formula of ethanol, your oxidizing agent to form ethanoic acid and water. This ethanoic acid is separated from the remaining solution using fractional distillation. To show you the diagram, here's your round bottom flask which contains your mixture of ethanol, sulfuric acid and potassium dichromate 6. We've got those anti-bumping granules again in order to stop large bubbles forming. As you heat that mixture, the ethanol vaporizes and will want to escape, but because you're heating under reflux, it will return to that round bottom flask where it continues to be oxidized to form ethanoic acid. And as I already said, that ethanoic acid can be separated from the remaining solution using fractional distillation. Secondary alcohols will be oxidized to form ketones. You're going to be using acidified potassium dichromate 6. The colour change will be from orange to green. So just to show you an example, here's propantuol. It's a secondary alcohol, and here's your propanone, the ketone. Like I said, the colour change will be from orange to green. Those tertiary alcohols will be very difficult to oxidize, so no visible change will be seen when you heat it with potassium dichromate 6. So the solution remains orange. So to summarize, those primary alcohols will be oxidized to aldehydes and then to carboxylic acids. For example, there's ethanol plus that oxidizing agent to form ethanal, the aldehyde, and the reaction condition needed for that is distillation. What about if we take that ethanol, oxidize it further using the conditions of reflux? Heating under reflux will form that carboxylic acid. So there's your carboxylic acid, it's ethanoic acid. So there's the summary of what happens with a primary alcohol. With a secondary alcohol, there's propantuol again. Be oxidized to the ketone. Look, there's the ketone functional group with the two R groups attached. So this is propanone. The following pairs of compounds can be distinguished by simple test tube reactions. For each pair of compounds, give a reagent or combination of reagents that, when added separately to each compound, can be used to distinguish between them. State what is observed in each case. So we have butan-2-ol and 2-methyl-propantuol. So just quickly draw those out. I'm not going to draw the whole thing, but I just want to get an idea of where the functional groups are. So we can see that that's a secondary alcohol. This is a tertiary alcohol. So the reagent we could use is acidified potassium dichromate 6. And remember, with a secondary alcohol, it will go from orange to green. Because that tertiary alcohol isn't oxidized easily, it will stay orange. Or you could write no reaction. What about to distinguish between the alkane propane and the alkene propene? You want to use bromine water. With the alkane, it will stay orange. With that unsaturated hydrocarbon, it will turn from orange to colourless. Propanone, so that's a ketone, is also formed by the oxidation of propantuol. Write an equation for this reaction using O to represent the oxidizing agent. It's fine to draw their displayed formula if you find that more straightforward to draw their structural formulae. So let's start with propan-2-ol. It's CH3, CH, OH, CH3. There's our oxidizing agent. And then here's propanone. And you're going to produce water as your byproduct. State the class of alcohols to which propan-2-ol belongs. You can see here that that alcohol is the secondary alcohol. The dehydration of alcohols, this produces an alkene. The mechanism is an elimination reaction. In terms of reaction conditions, you need hot concentrated sulfuric acid or concentrated phosphoric acid. Now let's take a look at the mechanism. So obviously we're taking an alcohol. In this case, I've got ethanol. There's a lone pair of electrons on the oxygen, which are donated to this hydrogen ion. Remember that hydrogen ion comes from the presence of the concentrated sulfuric acid. I just want to talk you through what's happening here. The electrons from this carbon-hydrogen bond are donated to form a double bond here. And because the oxygen has a positive charge, the electrons from the carbon-oxygen bond move towards the positively charged oxygen, meaning that the water is eliminated. So this is how we dehydrate our alcohol. We remove the water from it. After all, that's what dehydration means. So there's the water, and then we regenerate the H+, hence why the sulfuric acid is acting as a catalyst, because it is not used up. Now this method is actually becoming a more popular way of producing our alkenes, because remember they come from crude oil usually. Crude oil is a finite resource. The sugarcane used in fermentation, remember, is a renewable resource. This is why this method is becoming a more common way of producing alkenes. In terms of how this process actually takes place in a laboratory, it's through a distillation method. You're going to add your alcohol and concentrated acid to a flask. You're going to heat the mixture and collect the liquid that distills at temperatures below 100 degrees. You'll pour the distillate into a separating funnel and wash by shaking with sodium carbonate solution. Separating funnels are used to separate these immiscible, non-mixable liquids. The purpose of the sodium carbonate was to neutralize and remove the acid. Then we keep turning that separating funnel upside down. We open the tap, and that enables pressure to be released, prevents the stopper from blowing out. We then discard the aqueous layer and dry the final organic product using anhydrous calcium chloride. That anhydrous calcium chloride absorbs water and doesn't react with the alkene. And after product has dried, we remove the drying agent by filtration under reduced pressure, and this is done using a Buckner funnel and Buckner flask. I know that this method is very long, it's tedious, but unfortunately in the exam they could ask you very specific details, so it is worth writing this out on your flashcards or whatever revision technique you're using. Alcohol A undergoes reactions separately with acidified potassium dichromate 6 and with concentrated sulfuric acid. Deduce the IUPAC name for alcohol A. Do feel free to draw it out. I'm just going to pop it here. So count the number of carbons. 1, 2, 3, 4. So we're going to have butane. Check the functional groups. We have an alcohol here. Notice there's methyl attached here. The alcohol takes priority, so we're going to say that that's on the second carbon, which means that if we count that as the first carbon, second, third, it's 3-methyl butan-2-ol. Draw the structure of the organic product B formed when A is oxidized in the reaction with acidified potassium dichromate 6. I'm just going to bring back that structure actually so you can see it a bit more clearly. Have a look, count the number of carbons that the alcohol carbon is attached to. It's 2, so it's a secondary alcohol. Remember, secondary alcohols are oxidized to form ketones, but you can also see, look, the alcohol functional group is attached here, so the only thing that makes sense is for this to turn into a double bond O, giving us the functional group of a ketone as opposed to an aldehyde. So I'm just going to alter this. So that's done. 2 isomeric alkenes, C and D, are formed when A is dehydrated in the reaction with concentrated sulfuric acid. Name the mechanism. Remember, that is elimination when you're dehydrating an alcohol. Draw the structure of each isomer. So remember, when you dehydrate, you produce an alkene. I have got my structure of A back here again, so we just need to work out where that double bond is going to form. Remember, we lose water. It therefore makes sense that the double bond forms here or here.
Name the type of structural isomerism shown by C and D. You can see here that the only difference between these isomers is the location of the functional group. That means that this is a position isomer. List alcohol A, product B, and isomer C in order of increasing boiling point. So alcohol A here, remember, is the secondary alcohol. Here's a ketone, and then we have an alkene. Remember, the alkene will have the lowest boiling point because it's only got van der Waals forces. So it will be C, followed by our ketone. That ketone here, remember, has dipole-dipole forces, so that's why they're stronger than the van der Waals forces found in the alkene. But then the alcohol, A, over here, remember that has hydrogen bonding, which is the strongest of the intermolecular forces. Draw the structure of the isomer of A that is not oxidized by acidified potassium dichromate. So you're after a tertiary alcohol. Let's just steal this structure here, this displayed formula. So I need to rearrange the atoms to form a tertiary alcohol. So here is our tertiary alcohol. Look, it's tertiary because the alcohol group is attached to a carbon that itself is attached to 3 other carbons. Tertiary alcohols, remember, can't be oxidized by acidified potassium dichromate 6. And then finally, draw the structure of the isomer of A that cannot be dehydrated to form an alkene by reaction with concentrated sulfuric acid. I've drawn out the answer here. This is a difficult one because you need to think about what happens in order to eliminate the water. And if you look back at the mechanism I drew for elimination, you'll realise that the adjacent carbon to the one with the alcohol functional group must have a hydrogen attached, so that hydrogen-carbon bond can donate its electrons to form the carbon-carbon double bond. Because this carbon here has no single hydrogen attached to it, we don't have all the necessary components required for an elimination reaction to occur. Now we're going to consider how we go about analysing organic compounds, starting with mass spectrometry, which can be used to determine the molecular formula of a compound. It gives the relative molecular mass of organic compounds. I'm going to run you through how to read a mass spectrum. So we're taking this ester here with a relative molecular mass of 102. Here's the displayed formula of the ester. So the fragments we are looking at on this particular mass spectrum includes one here with an MR of 43. This accounts for the COCH3 plus ion. The MR down here at 71 represents this particular fragment. We're always super interested in the right-hand side of the mass spectrum. The taller visible peak represents the molecular ion. It is the peak produced by the molecule with a single positive charge, and therefore allows us to find the molecular formula of the molecule, which in this case, as we know, is MR of 102. This tiny peak over here, which is found on the right of the molecular ion, is caused by ions containing other naturally occurring isotopes, such as carbon-13 and chlorine-37. Now we'll look at high-resolution mass spectrometry. High-resolution mass spectrometry is when masses are given to 4 or more decimal places. High-resolution mass spectrometry allows molecules with the same MR when given to the nearest whole number to be differentiated. So we'll look at this particular example. Standard mass spectrometry of a sample of propane showed a molecular ion peak at 40. However, high-resolution mass spectrometry of the same sample indicated that it was contaminated with traces of carbon dioxide. Use the data in the table to show how precise MR values can be used to prove that the sample contains both of these gases. What you have to do here is write out the molecular formula of each substance, then calculate its MR using the exact numbers provided in the table. So you'll get an answer for propane, which, as we know, to the nearest whole number was 44, but once we work it out here, gives us this very precise number. We do the same with carbon dioxide to give this number, and therefore, through the use of the high-resolution mass spectrometry, we can see that they do indeed have different MRs, and therefore you'd expect 2 molecular ion peaks to appear in the spectrum. A second type of analysis used to identify organic substances is infrared spectroscopy. This relies on the fact that different types of covalent bond vibrate at different frequencies. Each type of bond can absorb infrared radiation at the same frequency as this so-called natural frequency. If a beam of infrared radiation with a range of frequencies is passed through the sample, then an infrared spectrum can be produced showing the frequencies absorbed and therefore which bonds are present. So you'll get a table very similar to this on your data sheet, and notice that each of these bonds has a specific wave number. This wave number is proportional to its frequency and is therefore characteristic for each type of bond. What I'm going to show you next is various infrared spectrums with their characteristic peaks and how you can use these spectrums to identify various bonds found within a sample, which will enable you to work out the type of functional group contained within a particular organic substance. So we'll look at some infrared spectra now, and I'll talk you through some very distinctive peaks and troughs. Notice this super broad wide trough here is very representative of an OH peak found in a carboxylic acid, and you'll see it located between 2500 and 3000. So you look at your data sheet, you have a look at the range, but also the fact that it's super broad does tend to represent the fact that you have a carboxylic acid. If we look at this second example here, cyclohexene, yes, you have an awful lot going on here with a peak located at just less than 3000, but all that represents the fact that you have a carbon-hydrogen bond, which, as you are aware, will be present in all of the organic substances. So instead, we need to look at this peak here, which represents the presence of a carbon-carbon double bond, so an alkene. And again, just cross-reference to make sure you're happy. Yes, that features between 1620 and 1680 here. Whereas before we saw a very broad peak with the carboxylic acids, here for alcohols you'll see a very narrow peak, and the range will be between 3230 and 3550. Below 1500, so towards the right-hand side of the infrared spectrum, you'll see what's known as the fingerprint region. This is unique to every molecule, and what computers can do is they can read this in order to deduce a more precise structure within a sample. And then again, looking at propane nitrile, this peak here represents the presence of a CH bond, so not very useful for identifying any particular functional groups, but you see this very distinctive peak located at around 2250, and so that fits nicely in the nitrile C double bond N functional group. So once we use the infrared spectra to identify various functional groups, we can then confirm these samples by comparing the infrared spectrum with that of a known spectrum of a molecule to see if there's an exact match, and they often like this exact type of wording in a particular exam question, as well as you stating the bond's wave number in terms of what you can identify off an infrared spectra. Compound K has the molecular formula C4H8O. Figure 1 shows the infrared spectrum of K. Right, I've copied in the infrared information about the bonds here, which you'll have on your data sheet. First thing we need to look at here is this peak around 3000. Now, obviously there's quite a few different bonds which correspond to that, so it's important that you're aware that we don't have a carboxylic acid or alcohol because of all the distinctive features I pointed out in the video before. So then we move to this peak here, which we can see sits at 1700, and therefore we can identify that as a C double bond O, which is a carbonyl functional group. Describe fully how infrared spectra can be used to distinguish between isomers R, S and T. So we're using this table to help us answer this. So we'll look at RS and T. So here's RS and T. We can see that R is an alcohol due to the OH. S is an alcohol for the same reason. So here you would simply need to say that R and S have OH alcohol peaks, and then just specify the number, the wavelength from this table. T, we can see here, has a carbonyl functional group. So again, we'd point out that you'd see a wavelength between 1680 and 1750. And then because these are very similar, aside from the position of the OH group, remember you need to consider the fingerprint region, which occurs below 1500. This is unique to every molecule, and therefore computers can read this to deduce a more precise structure of the sample, which you can then compare to a database of known spectra. The infrared spectrum of an organic compound is shown, which compound produces this spectrum. So let's have a look here at this peak that occurs around 3400. Notice that this is a very distinctive alcohol-shaped peak, and look, the wave numbers match up. So we know we have an alcohol, but then look carefully along here. That hydroxy represents an alcohol, and those two obviously represent an alcohol. So we've only gotten rid of ethanoic acid as an option. So have a look here, read this off carefully. We can see that this peak is around 1680, which corresponds to the carbonyl group, which is present in ketones. So the answer here is B.